Okay, great. I think we are almost at the time to start. Welcome everyone. Can anyone type in the chat box if you can hear me okay and see the slides okay? Great, thanks. Okay, let me get started. Okay, so I'm so excited to welcome all of you to join us today for the first workshop on structural and compositional learning on 3D data. I'm Kai-Chun from Stanford, and on behalf of all the workshop organizers, we warmly welcome you and assure you that you will enjoy the workshop content today. I'm here to give you a short introduction to the workshop, and also I will detail some workshop logistics. I will also be able to see, so you will also be able to see most of the other workshop organizers hosting different sections during this full day workshop. Please don't hesitate to come to us if you have any questions, encounter any technical issues, or just want to say hi to us. We live in a 3D world. We perceive the world in 3D, interact with objects in 3D, and accomplish everyday tasks in 3D. A wide variety of applications in different fields does require capturing, modeling, and analyzing data in 3D. We have been seeing great advances of 3D methodology in recent years in autonomous driving, robotics, augmented reality, and medical image processing. However, the huge complexity of 3D data still prevents us from scaling up and deploying this developed 3D technology to unstructured real-world scenarios. We argue that one challenge we are facing now is how to deal with the structural and compositional complexity of 3D data. As you can see here, a simple chair can be decomposed into 20 semantic parts, where which geometric and physical constraints have to hold for a functionally correct chair. Similarly, if you look beyond a single object and check the scene or building level 3D data, the structure of the data can be even more complex. So how to develop algorithms to infer, model, and represent such compositional, irregular, and complicated 3D data structure puts big challenges to the state-of-the-art learning system. The concept of compositional learning can also extend beyond modeling explicit 3D data structure. For example, here I'm showing you that learning some latent or implicit components may help you do better 3D shape reconstruction, even though the shape part do not have to be explicitly defined. Also, in many robotic applications, it is a hot research area how to actively perceive the world, compositionality, and learn better policies for robotic manipulation and navigation. With all of this motivation and challenges we are facing, we therefore present this workshop to you to give you an overview to the current state of art on these topics. Hopefully, our workshop can help you get started thinking regarding many of these open questions, and we are very eager to see your future research works. Okay, so this is the schedule of this workshop. This will be a full-day workshop featuring 4 talk sessions, 2 poster sessions, and 1 panel discussion. The talk sessions and panel will be on Zoom, and we will switch to Gatherly for the paper poster sessions. For the 4 talk sessions, we have 4 subtopics. 2 of them will focus on discussing structural representation for 3D scenes and shapes, while section 2 will pay special attention on compositional structure in robotic applications. And session 4 will then focus on using implicit compositional 3D structure for vision or graphics applications. Two of the workshop organizers will host each talk session and help arrange the presentation and Q&A in that session. So again, please don't hesitate to contact them if you have any question or technical issue. Each talk section will last for 2 hours and feature 4 talks. So 2 of them are 30-minute keynote talk from professors or senior researchers, while the other 2 are 10-minute spotlight talks from students or junior researchers. Our idea is that to have these 2 groups of speakers complement each other in that the senior researcher will give you big pictures, roadmaps, and visions to the problems and challenges, while junior speakers will give you concrete examples about the problem formulation and technical approaches of their latest work. We are very honored to have 8 well-established senior researchers working in different fields to join us today, such as the vision, graphics, and robotics, so that we will give you a complete picture of the problem scope. We are also very thankful for having 8 student speakers to present their recent research works as the concrete examples to you. During a talk, please don't hesitate to ask questions. However, to avoid Zoom bombing, we mute everyone by default, so please try to ask questions in the Zoom chat box, please. You are also welcome to request to be unmuted if you want to directly speak to the speaker to ask your question. So just type in the chat box that I need to be unmuted or so, and then we'll unmute you so that you can directly speak. You can also leave your question in the ICCV official Q&A system, and we will gather your questions and ask the speakers during the final panel discussion. So besides the talks, our workshop also have 2 paper poster sessions featuring 14 research paper presentations. There will be 2 30-minute poster sessions in Gatherly. Please join to chat with the paper authors. There are 3 archival long paper publications and also 11 non-archival short papers that will be presented in the poster session. All the works have been peer-reviewed at the highest standard by the program committee members listed here or previous conference reviewers. We want to thank all the reviewers because without you, we cannot host the paper session today. So if you check the paper page on the website, you can read the paper abstract, the full paper PDF, and watch the video presentation prepared by the authors by clicking this button. To join the live poster session to interact with the author, please check author's availability as marked in red. We are using Gatherly for hosting the poster session. Please log into Gatherly using this link and find our Structural 3D workshop space to talk to the paper authors. So concretely, please, if you look at this interface, after you log in, you will put on this starting page. You can first navigate yourself to the elevator icon, then click our workshop name, and then you will see the 14 papers. And you can navigate yourself to each paper to join the discussion with that paper author. So the last but not least, we will be hosting an hour-long panel discussion to talk about open problem and researchers to do in the next steps. The panel discussion will be hosted by Shubham and Niloy, 2 of our organizers, and we will have most of the invited keynote speakers to be the panelists. In the panel, we will be discussing regarding these open questions and hearing different opinions from researchers working in different fields. We will also take the audience questions and hope to present you a fruitful discussion in this panel. With this, I'm going to stop here and hope you enjoy the talks, papers, and panel in our workshop. Okay, so maybe let me hand over to Kai to kick off the first session.
Can you hear me, Tyson? Hello?
Yeah, your volume is pretty low. Maybe you can increase the volume.
All right, let me see. Is this better now, or should I do something?
Yeah, I think you are good. Yeah.
Okay, so Aldred, cool. All right, let me try to put up the top then. Share screen. Okay, sorry, I have some slight difficulties that I need to handle. My apologies. Can people see my screen now?
Yes, yes.
Cool. Okay. So welcome to the first session of structural 3D workshop, structural representations for 3D scenes. In this session, we explore the structures and compositionalities that exist in 3D scenes. 3D scenes are naturally structured, but when looked at this living room, for example, when we immediately recognize that it contains a coffee table surrounded by multiple sofas. And similarly, this bedroom contains a bed and a nightstand sitting next to each other. Structures exist not only in room-level 3D scenes, but also on scenes of other scales. For example, one can also decompose an entire floor into graphs containing multiple individual rooms. Or one can go even further, try to define a multi-hierarchy representation of, say, an entire building, breaking down a building into rooms, breaking a room into places, places into objects, and so on. In this session, we explore different ways to handle such structures. This includes different ways one can represent those structures. Do we represent this with a graph, with edges representing various types of relationships between individual objects? How do we define the relationships that exist in such graphs? Or should we represent a scene as a hierarchy, breaking down a large portion, a large region into smaller, semantically related smaller regions, or trying to come up with even programs to describe the scenes? And having defined the structures, what are the tools we can use to model these structures? Should we use, for example, a graph neural network to encode the scene graphs with other components that map different types of geometric or semantic information of the objects into the graph? Or what about using a recursive neural network, which is very good at handling hierarchical definitions and hierarchical information? Or say, transforming such structures of scenes into a sequence and then using some of the existing sequential models, such as a transformer, to handle the structure. The 4 invited talks in this session aims at addressing some of these problems and other issues that I have not listed in this very short introduction. And without further ado, let's proceed to the first spotlight talk of this session. It is my pleasure to introduce the first speaker, Helisa Darmo. Okay. Hi. Helisa is a PhD candidate who is finishing her studies at Technical University of Munich. She works on ambiguous aspects of scene understanding, such as generating occluded regions and semantic manipulation. She has published several pretty well-received papers on different scene compositions, such as layered depth images or scene graphs. Today, she will be giving a talk about using semantic scene graphs to describe the 3D indoor scenes. Thank you. Welcome.
Okay, hello everyone. I hope you hear me well. I'm Helisa, and I'll be presenting my work on describing 3D indoor scenes via semantic scene graphs. And I would first like to thank the workshop organizers for inviting me here, and it's a great pleasure for me to present. So first of all, a note on scene graphs. As the organizers also mentioned, there are a lot of scene graph definitions out there. So I just wanted to make clear that we are interested in semantic scene graphs that describe the scenes as a set of nodes that represent objects and edges that represent their pairwise relationships. And these are all semantic labels. So the 2D community has been investigating a lot of interesting tasks using such graph representation. So we wanted to do the same in 3D. Basically, this is the outline of my talk. I'll first introduce our data set, 3D SSG, a real 3D data set which we annotated with scene graphs, and then I will iterate through all the tasks that we made possible and we tried using this data. So first, the dataset itself, it extends the 3R scan dataset, which is a real-world dataset with changing 3D reconstructions. And we annotate relationships between the instances of the scene and their attributes. And as you can see, the graphs are quite dense, and we are aiming for also semantic diversity here. And we annotate 500K edges in total in a semi-automatic way. So here are more details about how the dataset looks like. First, unlike common datasets that contain one label per object, here our nodes contain a hierarchy itself of semantic classes, and we extract this hierarchy using WordNet and word definitions, so that we know that, okay, even though we happen to annotate this as an armchair, it is actually also a chair. So one can draw interesting connections from there. Second, we have diverse set of attributes, which are object properties, and we categorize these in static, dynamic, and affordances or functionalities, that what you can do with the objects. And interestingly, the dynamic attributes fit very well to this changing data set. And you can see in this example, two instances of the same scene where the bed appears once messy and one tidy, so one can reason about human activity in the future. And last, the relationships are categorized also in three. We have proximity, support, and comparative. And while the other two can be obtained automatically using geometric rules, for support relationships, we relied on careful manual annotation. And this is done to ensure a rich set of labels like leaning against, hanging, lying on, and so on. And also to deal with faults in the data set and missing information, we couldn't just use points of contact to extract this automatically. So now we obtain this data, so what can we do with it? And the first thing that comes to mind is, of course, let's generate scene graphs from our 3D scenes to understand them. So starting from a point cloud of a scene, and we also assume to have instance segmentation given, what we want to do is we want to predict the class labels for objects and their edges. And we do so in an architecture that consists of two branches. The first one processes every instance separately to obtain a node feature, and this is implemented as a point net. And the other one takes pairs of objects and extracts the union bounding box of a pair and processes the point set inside this union box to obtain what we call an edge feature. So this is another point net, and these are stored in a graph structure to further be processed by a graph neural network that generates labels. And one interesting thing that we chose here to model edge prediction is that we want to allow multiple of them to be possible, given that a guitar can be on the right of the couch, like we see in this graph, but it can also be close by. So everything is valid here. And therefore, we don't use a standard multi-class classification, but we formulate this as multiple binary predictions, each of them being independently predicting for a certain class label. And we use focal laws for both components, nodes and edges, to mitigate issues related to class imbalance. And here is one example result. For your clarity, green edges mean that we predicted them correctly and red means wrong, so to get an idea visually. And one interesting thing that I see here is that even when we have wrong predictions, usually they are not so bad. So saying that the desk is actually the prediction and the ground truth is a table is not so wrong in the end. And also we notice that sometimes ground truth is missing for the edges, but the predictions are still correct. So the green chair is indeed on the right of the orange one from our perspective. So actually, this is one reason to not penalize these cases, that the community in 2D has been using recall-based metrics to evaluate these works, and that's what we also do here in 3D. And basically what we can observe in this table is that our GCN model is superior compared to a simpler MLP-based baseline that considers relation prediction separately. And also we see that the multi-predicate variant performs better than the single predicate variant, what I explained before with the multiple binary cross entropies for edges. And now I want us to have a brief look at applications that we also tried. So first, we introduced the task of domain agnostic scene retrieval using scene graphs. And the idea is that we are given a database of 3D models, and we assume we also have obtained their scene graphs for each of these scenes. And we are given a query photo from which we want to know where this picture is taken, for example. But keep in mind that there have been illumination changes since the 3D scenes were recorded, and also objects typically change their position slightly due to human activity. So we didn't want to directly compare texture, one-to-one comparison here, but we thought let's do a high-level comparison at the scene graph level as a criteria for the best match. And then we, using this criteria, we obtain the best matching scene. And practically, this is implemented as a database query based on a set of objects and another set of relationship triplets. And we need a metric that tells us how to basically sort all the database models and obtain the best one. So practically, we can do the same with a 3D scene instead of a photo as well. And therefore, we obtain two different tasks of retrieving from 2D or also from 3D. And I guess what we can extract from this table is that if we use just a set of nodes as opposed to using the graph that also contains the edges for our matching, then we obtain better results. So edges make sense. And also, if we compare against the baseline, the simpler baseline from before, in general, we perform better than this baseline in both tasks. And now I want to give a very brief overview on our last work that closes the loop of going from scene to graph and the other way around. So here we are given an input scene graph, and we want to generate a scene that respects the constellations in this graph. So the idea is that we represent the scenes as a set of shape encodings and bounding boxes, so for every object, and we get the shape vectors from generative models on shapes and practically experimented with AskClassNet and DeepSDF. So we base the model on a variational autoencoder, and we have two branches, one for shapes and one for layout. And what is important is that we observe that using a shared encoder that gives us a latent graph that is aware of both shapes and layout can improve performance. So this is kind of a fact that encourages us to keep doing fully generative models and experiment with fully learned shapes. And last, here are some examples of scene graphs that we receive as input. And here are scenes that our model has generated. And interestingly, we can also support an additional task that is scene manipulation. So now from left to right, I will induce some changes in the graph, and you will see these changes also happening in the scene. So I'm adding a pillow or changing the relative sizes of chairs, repositioning the TV, and adding a cabinet. So that's it. Thank you for your attention.
All right, thank you very much, Elisa. I guess we can spend some time, some minutes for some questions from the audience. Let me see, there's something in the chat.
Yeah, maybe while we are waiting for audience to type their questions, so maybe I can start with one. So thanks, Halisa, for the nice talk. And you introduced 4 papers in 10 minutes. It's a lot of information. And can you briefly talk about some of the difficulties that you encountered, and or in other words, the failure cases? What type of relationships are harder to predict? And can you make some suggestions to the audience if they want to follow up regarding this direction? Thanks.
So in general, I would say in 3D, relationships like left or right or front or behind are very obvious, let's say, because you can clearly separate them. You can even get them automatically if you want. While other, what we call more semantic relationships, so the support relationships, often we encounter problems in getting some of these ones right. And this is especially because the data set itself contains a lot of noise. So sometimes let's say the boxes will be detached from each other, even though they should not be, because the legs of the chair are not reconstructed. So I would say it makes sense to pay some more attention to this and maybe make some improvement on the data set side, like replacing with CAD models, like as it has been for ScanNet, for example. I would say, yes, the most difficult part is support relationships. And also sometimes they're ambiguous by nature, like saying that the object is leaning to another object. And also for a human, this is sometimes maybe hard to determine fully. And I would say that this tendency is also visible when we generate scenes from a scene graph, so the opposite task. And one can see that left and right, it's kind of easy to place objects left and right there, but we get more failure cases usually related to support relationships.
I see. Thanks.
I don't think there's any question in the chat, if I'm not missing anything. All right, well, that was a great talk. Thank you very much. And I think I will present the next speaker. So our next speaker, is Xiyuan Huang. He did his PhD at UCLA on human-like holistic 3D scene understanding. His work includes a Best Paper Award at ICML and several oral presentations at ECCV, ICCV, and CVPR. He has also co-organized 3 workshops on 3D scene understanding, which I really recommend. And today, Xiyuan's talk will be about the compositional structure in 3D vision and language. And so without further ado, let's give the floor to Xiyuan. Thanks.
Can you hear me?
Yep.
Okay, great. Then I will start. So can you see the screen like normally? You see the screen?
I think we are seeing the presenter slide though, the presenter screen.
Oh, then I used normal.
Yep.
It's okay right now.
You can also just share, if you go into the advanced option, there's an option to share a portion of the screen, which is what I use to show myself the notes while in presenter view.
Okay, I'll try for 1 minute. Sorry. I think it doesn't work. I will start from here. It's okay for me. Thank you for the advice. Okay, so thank you for inviting me to this wonderful workshop, and thank you for the introduction. My name is Xiyuan Huang, and I graduated from UCLA, and I'm currently a research scientist at Beijing Institute of General Artificial Intelligence. And today my topic is compositional structures in 3D vision and language. So at the beginning of my talk, I want to emphasize that vision is not only about recognition, and it is the tool to model the 3D world and the physical world from the visual perspective. And also it is the key component that builds the intelligence, including how to understand the physical and social world, how to do the problem solving, and how to do the task planning. And also they can help to connect to the other modalities such as language and mind. So in all of these directions, I think compositionality is the key ingredient for the true intelligence. And let's recap how the compositionality affects different domains in AI. So in the left image, we show that in vision, we can decompose the things into objects and parts and events so that we can have a hierarchical understanding of the 3D world. And in the right image, I show that in the language domain, we can also compose different words into the sentences, and we can analyze the syntax, semantics, and pragmatics for the sentences. And beyond this, the sentence can also be composed to paragraph, article, and a magazine. And also in reasoning, the compositionality is also important for doing the abstraction and generalizations. More importantly, in robotics and in task planning, we can have the decomposition of tasks into actions and atomic actions. And then we can also have goals and sub-goals that can help us to understand the different hierarchies in tasks and help us to do the planning. And in the previous literatures, we have a bunch of machine learning models that can help us to capture the compositionalities in AI. And I list several here. For the left image, we have the logics and programs, which can help us to precisely capture the relationship between different entities and can capture the hierarchies. And in the middle is the grammar models, which can use the production rule to describe the relationship between the nodes and entities. And they can form in hierarchies to have a more holistic understanding of the sentences and 3D things. And in the right is the graph neural network that is very popular today, and it can be used to model the complex distributions in complex sensory input, such as images and like some other like physics data. So besides these all models, the problem I want to introduce today or want to explore today is how to bridge the vision and language for a better understanding, structural understanding of the 3D world. And this is a paper accepted by ICCV this year, and it's called VR Grammar, Grounded Grammar Induction of Vision and Language. And this is a joint work with Yining, Qing, and Songchen. So how to analyze and how to learn the visual structures from images has been a long existing problems in computer visions. So for the left image, we can see that Songchen in 2006, he proposed a method called ethnograph that can help us to understand the hierarchies in images and understand the relationship between different entities. And in the middle of image, we see that a paper in 2017 in Science that trying to solve the problem of captures with a hierarchical computer vision models. And it requires high data efficiency and requires good capabilities in generalization to new instances with limited examples. And in the right image is an image from Jeffrey Hinton from his recent papers, how to represent part-whole hierarchies in the neural networks. So it basically explores and discusses how to model the part-whole hierarchies with transformers or with other techniques, just like his capsule paper. So I listed 3 challenges in learning the visual structures from the images. So first is how to represent the flexible part-whole hierarchies that varies with images, but with an identical model. And second is how to learn the structure automatically without predefined template. And third is how to avoid ambiguities in structural learning. We have seen a lot of advances or progress in natural language that can model the sentences and language with grammar models. And here I show 3 papers that's trying to combine the recent neural networks or RN with the grammar induction models that can try to produce or generate good grammar models from language without any supervision. And from a cognitive perspective, it's called, we know a model called cognitive grammar, and it suggests that we should analyze the grammatical units with reference to their semantics, which is grounded and structured by patterns of perceptions, such as vision. So basically, it suggests that we should not only learn the grammars from the language, but also we should have a grounded perception, which is the vision. And below is a paper from 2019 that it introduced a method that can learn from 2 modalities, the images and also the sentence. The basic idea is that it can use a parse tree to describe a sentence, which is what people usually do in NLP. And then it also encodes an image into a dense vectors. And it finds the correspondence between the parse tree and the dense vectors of image to find alignment between 2 modalities and try to understand the language better with the constituents and with the images. And however, there is a problem in this approach is that it don't have fine-grained captures or fine-grained modeling of the image. It only models the image into an entire patch, but don't have the details. For example, the parse information and the relation between the parts, which is critical, and it's a topic of our workshop today. So recap the cognitive grammar, it also suggests that we should not only learn from the detailed constituent from or tokens from the language, we should also find the alignment or find the relationship between the language and other domain. For example, the vision domain. And here we see an example of how to align the grammar or how to align the structures between the image domain and the language domain. And we have a chair and we have a sentence of descriptions about this is a chair with an irregular back and so on. So we want to parse the images into different or various parts, and we want to parse the sentence into detailed tokens and constituents. And then we can find alignment between the images and also the sentence that can help us to better understand the relationship between the 2 domains and also help us to capture or to induce the structures from the alignment. So to address this problem, we collect and annotate the party dataset. So the party dataset is, it comes from the partner dataset, which is proposed by Kai-Chun, and it has fine-grained part semantics with 3D shapes. So we ask the annotators to annotate the detailed descriptions about the 3D shapes. For example, from the right image, we can see descriptions about a chair and a table and a bed. So we ask annotators to describe the detailed parts and their relationship. So that can help us to understand the detailed or fine-grained relationship between the parts and also the sentence token. And this dataset is also suitable for other tasks, such as the image captioning, the language-guided part segmentation, and also 3D reconstruction. In this figure, we show the overall framework, which is composed by 3 parts. And the first part is a language parser that can parse the language sentence into a language parse tree. And it has, it can connect the language tokens into more like mid-level sentences and mid-level structures. And another module is the visual module. So basically we have visual input with the entire images and also the part information. And we want to build an image parse tree that can parse the hierarchical structures in the image. So basically the language and image, they can both describe the structures in an image, for example, a chair. But the third module is try to find alignment between the language input and visual input. And they can ease the ambiguities in structured learning, and also they can find the correspondence between 2 modalities, and that can improve the grammar inductions from two modalities. And before introduce the method, I want to briefly introduce the context-free grammar. The context-free grammar is a tool to capture or describe the hierarchical relations in natural sentence or in other modalities. It can be defined by a 5-tuple, including the star symbol, finite set of non-terminal and terminal nodes. In the right image, we show how a language or natural language can be decomposed or can be parsed by context-free grammar into different hierarchies, different levels of hierarchies. But the context-free grammar is it also has some limitations. For example, it should be very hard to model some complex domain, such as the image. So we introduced the probabilistic context-free grammar that is trying to have a probabilistic distribution for each production rule. And then we have a compound PCFG, which is trying to use a latent variable model, the Z, to encode the complex context in the terminal or between the terminals. And the compound PCFG can have a more flexible representations to capture the complex relationship between the terminals. We use an MLE with elbow to estimate or to learn the grammar inductions from the language, which is composed by a reconstruction loss and the KL divergence between the prior distribution and the posterior distribution of the latent variable Z. And similarly, we can have the compound PCFG for the image. The idea is similar. We want to decompose the entire image into different 3D parts and try to have a parse tree to describe the hierarchical relationship. And similarly, we can also have compound PCFG to describe the production rule and how the terminal node, what is the relationship between the terminal and non-terminal node. But the difference for the image and language is that for language, we have a fixed vocabulary for learning certain semantics. But for image, we don't have the supervision for the parts. So we need to do an initial clustering to generate a label for the parts. And then we can do the bottom-up perception by grouping those terminal nodes into subtrees, and then we grow up the subtrees into an entire parse tree that can describe the image. The image grammar is also learned with an MLE with elbow, similarly. And the third module is also the last module is the joint learning by alignment. As I introduced before, the key spirit of this work is that we want to use the alignment between language and vision to ease the ambiguities in structured learning. So in this part, we measure the distance or alignment score between a part and language constituents by a cosine similarities between two vectors. We also can evaluate or calculate the loss or the alignment score between an entire image and a sentence by enumerating all the possible alignment between the parts and language constituent. So that's all about our approach. We evaluate our methods on the party dataset. The table shows the results of the grammar inductions. So basically for the vision grammar and for the language grammar, we individually evaluate the performance of language grammar inductions and visual language grammar inductions. From the table, we can see that our results outperform previous approach a lot with a VL grammar. And we also show that without the scan, or the scan is an unsupervised clustering algorithm. Without scan, the performance will degrade by about 5 to 7%. We also want to demonstrate how our model can be applied to downstream tasks, because we learn the grammar models or learn the joint grammar models unsupervisedly from vision and language. So that is important for us to apply this knowledge or apply this inductive bias to the downstream task. So we tested on 3 downstream tasks, including the unsupervised part clustering and the image retrieval task. And we also test the generalization capability of the proposed method. So the generalization capability requires us to generalize the chair or generalize the object from seen to unseen scenario, and capture the compositionalities of the objects is the key for the generalization. And we can see the result that our method also outperformed previous method a lot in the generalization test. At the last, we show some qualitative results on the party dataset and also the results in transferring to the real images. In the future, we want to extend the parties dataset into a fully 3D dataset with detailed part informations, which are also more corresponding to the topics of our workshop. And also we want to learn a 2D grammar that can capture more sophisticated spatial relationship from the images and or 3D point cloud or 3D mesh. Thank you.
Thank you, Steven. I think we have time for one really quick question. Is there anybody in the audience who want to ask one?
And if you have any question, you can also email me like after the presentations.
All right, I think we can then move on to the first keynote of the session. And the first keynote will be given by Professor Daniel Ritchie, who is an Aliel Horowitz Assistant Professor of Computer Science at Brown University, where he co-leads the Brown Visual Computing Group. His research sits at the intersection of computer graphics, AI, and machine learning, building intelligent machines that understand the visual world and help people to be visually creative. His group currently focuses on analyzing, synthesizing, and manipulating 3D scenes and the 3D objects that comprise them. Daniel has served on the program committees of multiple major conferences, including SIGGRAPH, SIGGRAPH Asia, NeurIPS, ICAR, and so on, and is a recipient of the NSF Career Award. Today, he is going to give a talk about learning to infer and generate programs for 3D shapes and scenes. Anthony, do you have the videos for his talk?
Yes, I will share with you the video of Daniel, but I have to figure it out how to share from video directly, which I don't think I find the option here. Let me see.
Yeah, I think you need to share the screen first, and then you can see the option to share computer sound.
Let me see if I managed to do it. Okay, so I'm sharing right now the video, but that's not the ideal way.
Yeah, and if you can see the bar at the top, and there is a more option. If you click on the green bar, if you're really like you're sharing the screen, and there will be the option. If you go to click the 3 dots, like the more, you might see share computer sound.
Yeah, it's that I don't see that option though. It's like I'm in let's see, I'm in more, and I see chat, reactions, pause recording, stop recording, meeting info, breakout rooms, high video panel, high floating media controls, optimized for video clip. Maybe it's that. Yeah, no, I don't see the from video, and I agree that this should be such thing.
Yeah, so take your time. So maybe in the meanwhile, I will try to download the video, and if I can play.
Let's do that, because I don't really see that option here. Maybe I don't have the right Zoom for that. Or maybe I'm missing some permissions. Could that be? Oh, I think I found it. Let's see. Okay, do you guys see the video only?
Yeah, I can see the video, but it's not
Okay.
playing. Right?
All right, now I'll play it now. Can you hear the audio from the video as well?
Today, I'm going to be trying to.
Perfect. Okay, let's do this. Yeah. Okay, thank you.
Thanks.
Okay. Well, thanks for having me at this workshop. Today, I'm going to be trying to convince you why I think you should use programs as a representation for inferring and generating 3D shapes and scenes. So the motivation for this research, and for really all of my research, is the increasing demand for 3D content in the world these days. I'm a computer graphics guy originally, so a lot of my heart still lies there. And in graphics, our kind of traditional driver of demand has been the entertainment industry, things like games, virtual reality, visual effects, and animation. And this is still an increasing source of demand today. We still have games that are becoming increasingly large, open world, players demanding more and more frequent updates with new content. So this is still ongoing. We're also seeing demand for 3D content from places like the e-commerce industry, particularly in furniture and interior design. Here is an example image from Wayfair.com, which is an online furniture retailer, where all of this imagery is in fact not photographed, but is computer generated. The company has decided that creating this imagery virtually is a lot cheaper and more flexible than trying to physically set it up on a stage and photograph it. Probably closer to home for most people in this audience, given that this is a workshop at a computer vision conference, is this idea of graphics for AI, using computer graphics to synthesize training data. For example, for semantic segmentation, I can render a scene in a somewhat photorealistic manner. And because I know all of the objects that went into creating that scene, I get ground truth semantic segmentations automatically without having to have someone annotate them by hand. We can even go further and look at things like Facebook's Habitat platform, which is this embodied first-person simulation environment where we can simulate an agent actually navigating around in these virtual spaces, performing goal-finding tasks and so on. So this is not just generating training data offline, but actually having these online interactive training environments. And here's an example, another robotics related example from the robotics lab here at Brown, where we have this robot with an onboard depth sensor, which is scanning this microwave. Here's the scan that it produces. And those red and blue cylinders indicate the position and orientation of where the robot thinks the hinge for the microwave door is. And the way it was able to learn how to do that, how to make that prediction, is by training on a bunch of these synthetic articulated 3D models. So once again, we were using computer graphics to generate training data for the system. Now, the current practice of how 3D modeling is done and has been done for decades really doesn't really scale to meet this increasing demand for 3D models. If manual 3D modeling is still quite slow and hard to learn. So if you have ever attempted to make 3D models in something like Maya or Blender, or if you're maybe more on the engineering side and you've ever tried to design objects in something like SolidWorks, you know that these tools are extremely complicated and idiosyncratic and require a lot of training to get comfortable with them. And that's just not quite an option for most people who want to make this kind of data that we're interested in. So my high-level research goal is really to try to make it easier to create and edit 3D content. And the way I go about approaching this is looking at generative models, things that can synthesize 3D structures like 3D objects or 3D scenes, and then also closing the loop by looking at the inference side of how do I infer, given some 3D structure in the world, how do I infer the underlying generative process that gave rise to that structure? So we can see here in this box about generative models that I have deep networks, which we're all familiar with, we all know and love these days, but also programs. And I want to spend the rest of this talk convincing you why I think programs are a good representation for modeling 3D shapes and scenes for generation and inference purposes. There's a few reasons that I'll highlight. I'm going to go through several several reasons why I think these are a good representation and highlight examples from each of them, from my own work and from the work of others. So the first is that they provide a strong form of structural regularization. They're interpretable and editable. They facilitate higher level reasoning than other representations might. And they also provide really powerful facilities for abstraction and composition. So let's dig into each of these in sequence. Let's first talk about structural regularization. So one of the cool things that you can do with these program representations is correct mistakes that simpler computer vision systems might make. So here I'll give an example from a paper that Kevin Ellis and others and I published at NeurIPS a few years ago, where we would take 2D sketches, hand-drawn 2D sketches of these diagram-like figures and extract from them a C-like imperative language representation that reproduces that sketch. This system works in a couple of stages. It first uses a neural network-based object primitive detection system to extract things like circles and squares and lines, and then uses a constraint-based program synthesizer, something based on fancy SAT solving, to find a program in this language that will output the same set of primitives. And what's interesting is if you take an input sketch and you pass it through just an object detection system, something that looks for these primitives and identifies them, then we can see that there's an error the system makes. It infers here that there should be this arrow, line with an arrow ending on it, pointing to this circle. And likely it did that because there was a little bit of an imperfection, a little bit of a smudge here where the person drew this sketch. But we know as people that that was not the sketcher's intent. They actually meant for this to be most likely to be just 3 lines that are decreasing in length. And so if you were to then put this through the program inference part of our system, the program synthesis part, it discovers that in fact, that is actually the right way to represent it, because you can actually represent this input sketch much more compactly if you do that. This is a nice way to kind of regularize away some of these low-level object detection mistakes. And we can see a similar phenomenon with inferring programs for 3D objects. So this is from a paper from Young Tian and some others at iClear a couple of years ago that looks at taking 3D objects expressed as volumetric occupancy grids, and once again inferring C-like programs that output those objects. And so here, if we take an input photograph, say our goal is to ultimately infer a 3D shape for an image that we have, and we pass that through some, say, deep volumetric CNN that is going to produce as output a volumetric occupancy grid, we might get something like this, which exhibits a lot of the typical errors that these kinds of systems make. It gets the bulk shape more or less correct, but there are a lot of artifacts and issues with the geometry. And then if I were to take this input, this particular 3D shape, and pass it into the program inference system, I would get an output like this, where because I'm requiring this output to be expressed as a valid program in this language, I end up regularizing away a lot of these issues that the language simply can't express. And in fact, if this particular input photo, this comes from a data set where we actually have access to the ground truth 3D model, the ground truth CAD model that corresponds to the chair in that photo. And we can see that the program induction system's output is much closer to the ground truth than what the raw CNN produced. Another thing that these kinds of systems can do is to see what can't be seen. They can infer the presence of hidden content. So here is an example from another paper that some other folks and I worked on at iClear a couple of years ago, where we took an image of a 3D scene, a synthetic 3D scene. This is similar to scenes you might find in the Clever dataset, for those of you who are familiar with that. And again, we're trying to infer an imperative C-like language that generates the scene by placing primitives and specifying their colors and attributes and so on. And so if we were to apply this system to images like this, where we have these kind of stacks of these nested stacks of cylindrical blocks, this system works similarly to that sketch inference system I described before, where it first starts by applying object detection. Here, I believe it's using a mask RCNN. And there are actually occluded primitives, cylinders, you can see them, back here, that can't be seen or are sufficiently occluded that the object detector doesn't actually recognize them. But this system was trained on training data that already had these kinds of patterns in it, these kinds of stacks of primitives. And so when you ask it to take this sequence, this set of primitives and predict a sequence of program tokens, even though this set of primitives doesn't actually include the ones that are hidden, the system has learned that there's a correlation between visible object patterns that look like this and programs that look like this, which actually has the correct triply nested loop structure. So there's, the three loop orders are this way, and this way, right? So sort of width, depth, and height. And it's able to actually correctly figure that out. Finally, I want to give an example not from sort of a inference task, but more of a generative task, where we have, this is work from this paper on shape assembly that some students and I published at SIGGRAPH Asia last year, where we defined a language for expressing part-based 3D shapes by saying, we're going to declare parts, in this case, they're simple cuboid geometries, and then have a primitive operator in the language for attaching them to each other, specifying where these parts connect. And what's actually quite nice about this is that if we use this as a representation for a generative model or even for a computer vision system, that because the system has to express objects in terms of connected parts, there are certain kinds of failure modes that it simply can't express. So if I say train a system for taking input point clouds and trying to infer programs that describe them, if I were to instead use a model such as StructureNet, this is something that outputs a collection of boxes, a hierarchical collection of boxes to represent a 3D shape, then because these boxes are just positioned and rotated arbitrarily in space, they can end up having some of these failure modes where objects overlap or they're sort of floating or disconnected. Whereas our particular representation, because the language has to represent a connected assembly of parts, it can't actually output geometry with these kinds of errors. Okay, so that's all that I'll say about structural regularization. I want to move on to my second point about interpretability and editability. So one of the cool things that we can do with programs is we can use them to extrapolate visual content. Here's what I mean by that. I'm going to give another example from this sketch program inference system. So if we take this input sketch and we use our system to infer this program for it, then this program is just text. It's freely readable and editable text. Anybody who has a passing familiarity with programming can look at this and say, oh, if I were to take this loop limit here, which currently says for I less than 3 and change it to for I less than 5, and then rerun this program, I can in effect extrapolate this pattern that was drawn in my input sketch and create something that's a generalization of what I saw. So maybe I would use this if I were trying to prototype some diagram by sketching on paper, and then I want to scale that diagram up to something really big that would be cumbersome for me to draw by hand. I could use something like this. And we can apply this to lots of different kinds of visual patterns in the system. So here's a bunch of hand-drawn sketches. Here I'm skipping over the details of exactly what the programs that were inferred looked like, but we can see that we're able to successfully infer looping programs where we can change the loop bounds and create these extrapolations. Extrapolation is not the only kind of text editing we can do to these programs. We can actually work on other kinds of fine-tuning interactive edits. So this is an interactive editing tool we built for shape assembly programs that allows users to tweak these parameters. Interestingly, we also have a mode of this interface that's not shown here, where you can edit the geometry via direct manipulation and have those edits propagate back to the text. So depending upon which mode of interaction is most natural for a user, they can go with that. These have all been sort of toy examples, but we're also starting to see examples of this principle of the editability of programs being applied in more real world scenarios as well. So for example, there's a paper actually being, that was presented at this conference this year, the system called DeepCAD, which is a generative model for these kinds of parametric CAD programs. They're basically sequences of operations that describe how to create these 2D engineering sketches, these 2D cross sections, and then do things like extrude them and combine them via Boolean operations. And if you learn to, just like with the shape assembly example I showed earlier, if you learn to take a point cloud and project it into the latent space of this generative model, then you can reconstruct these point clouds as CAD programs and then edit them. Effectively, what we've done is we've taken some object out in the world that we've scanned, and we've reverse engineered a plausible CAD program that might have given rise to it. Then we can make modifications to suit our needs. Maybe we want to move some things around or change the size of things, or say fillet the edges. So this last point that I brought up about interpretability and editability was more about user interaction. It's more of a graphics motivation. This third point about high-level reasoning is again more of a vision or AI motivation. And that's that this gives us the ability to reason about relationships or similarities between structures in a higher level manner. So again, I'll give another example from this sketch program inference system. If I were to take a look at, I can take a look at some sketches in my data set, and these are sketches that really have nothing to do with each other. They're quite far apart, both in pixel space. And in fact, if you were to look at the programs that generated these, they're also quite dissimilar from one another. Then we can look at some pairs of images of sketches like this one, where these are, sort of related in image space. They if you kind of take a step back and squint, they look a little bit similar in pixel space. But I'd argue that this particular one on the top, these are actually not all that related programmatically. This depicts more of a linear chain structure, whereas this depicts more of a circular undirected graph structure. And so we might actually be more interested in comparing these sketches in program space and actually looking at structurally how related they are. And so these two examples right here would not be close together in image space because one is essentially the vertical mirror image of the other, but in program space, they're actually quite similar. And then of course, we can look at some examples that are close in both program space and image space. We can apply this same idea to 3D objects as well. So here are some 3D objects expressed in the shape assembly language. And we can look at their geometric nearest neighbors, and we can see that, again, if I take a step back and I squint at these images, these look fairly geometrically similar. But I can also look at their nearest neighbors in program space, or the ones that are most lexically or textually similar. And these are quite interesting because, for example, if you look at these two shapes here, they don't really look all that geometrically similar. This one is much more sort of slight and has thinner parts, and this one is much more chunky. But they're actually very structurally similar. They both involve chair backs that have horizontal slats, and they both involve these crossbars on the legs. And so in some sense, if we're thinking about how are these shapes represented via, say, edit distance, there is a smaller edit distance between these two shapes than there is between these two shapes. And that might be a meaningful thing that I might care about in some higher level reasoning application. And the final example I'll give of high level reasoning is analogical reasoning, is saying, if I have two shapes, two images, A and B, and I want to sort of come up with what is to C as B is to A, those of us looking at this as people, we know that the right thing to do is to add another red block here at the end of this diagonal column. If I were to ask an autoencoder to do this, which is to say, if I were to autoencode these images and then do latent space arithmetic, where I say, let's take the vector between A and B and add it to C, and then decode the results, I'll get something like this, which is, clearly not what I want. It hasn't really done the right thing, and I'm getting all these visual artifacts because of the compression that the autoencoder latent space does. But I can actually do this in program space as well. I can essentially take the program space diff between A and B and add that to C, and I can get this result. And here's another example where I've got these two columns and then these three columns, and obviously the right thing to do to extend C is to place another column of blocks here. The program-based diff reasoning does it just fine. The autoencoder does better. At least it sort of places the right thing in the right space. But again, you have this compression that happens, and so we get visual artifacts. And finally, the last point I want to make is about the powerful abstraction and composition that programs offer. So programs really are the most general possible mechanism for capturing abstractions. Subroutines, right? We define programs by building up hierarchies of function calls, and these subroutines are an incredible mechanism for capturing reusable patterns in our structures. So here's an example from this paper called ShapeMod that we published at SIGGRAPH earlier this year, where we take a data set of 3D shapes expressed in the shape assembly language. And we find across the data set of these shape assembly programs, these recurring patterns that occur repeatedly across different programs. So here in this animation, everything in, say, the yellow box is the same repeated pattern of program structure. And what we can do is we can factor these patterns out, literally refactoring our code into these reusable macros. And these macros then allow us to capture these patterns with much fewer parameters. We sort of factor out irrelevant degrees of freedom. We make our shape representation much more compact and much more accurate. So I'll show some examples of that later on. So here is exactly what the payoff is for doing this. So here, one of the macros that the system actually discovers is this subroutine called foreleg base that has just 2 free parameters. And these parameters control the thickness of the legs and their front to back position. And this is actually a higher order function. It takes as input this thing called bbox, which is basically the bounding box of what the leg geometry is. And the leg geometry could be all sorts of different things. It could be just a single cuboid, or it could be something that has like a foot structure here, for example. And this is great. Now I've expressed this degrees of freedom that the bases of four-leg chairs can have with just 2 parameters. I don't have to deal with fiddling all sorts of individual parameters for the individual legs. Another instance of this principle is from the Dream Coder system, which is a great paper by Kevin Ellis and his collaborators at MIT, where they actually did this for a lot of different kinds of data, but here's one example of these 2D logo graphics programs. And they were able to automatically discover subroutines for things like semicircles and circles, spirals, polygons. I should say that the names here were provided by the authors. The system does not name these subroutines, but it comes up with their code. And even just like that four-leg base example I showed earlier, it can even discover higher order functions. So here's a function that expresses radial symmetry, which n gives the number of repetitions in the symmetry group, and then body is some other sub-program that draws something, maybe a dashed line or a circle or an S-curve. And so one of the big payoffs to having higher level subroutines is that this ties back into the interpretability and editability, is that it now makes the shapes or the images you're working with more consistently editable. So here's an example from the shape mod paper I mentioned earlier, where we have 2 tables. And if we apply edits to some of their free parameters, here I'm just highlighting in red the parameters that were edited, and then we generate the outputs, we can see that these are still valid programs, but they don't quite do what we'd like them to do. Some things are going to become decoupled in ways that are not quite intuitive, and that's because there are sort of hidden correlations between these free parameters. That if I were to move this one, probably this one should be changed in some way, and the program doesn't actually capture those for us. It's too low level to capture those correlations. But if we use our system of automatically discovering these macros and refactoring the code to use them, then if we edit the same number of free parameters, we find that these different macros, these higher level subroutines, are actually capturing some of these correlations, so that no matter how I edit the parameters, the resulting shapes stay looking reasonable. Okay, so that's all I'll say right now in terms of my motivating evidence for why I think programs are a good representation. And I want to talk about what comes next. In particular, how do we realize the potential of programs as a representation for more complex real-world problems? I think that's the interesting question to ask. And so the first thing I think is important to figure out is how to do this kind of learning these program-based representations without programs as supervision. And that's because a lot of these systems that I've been showing you have assumed they had access to ground truth pairs of some visual structure and the program that generated it. And in practice, in the real world, oftentimes we just don't have access to those kinds of programs. So how do we learn without supervision? Well, one approach is to use reinforcement learning. This is a fairly classic thing to default to when you don't have step-by-step supervision. And there have been some success cases of applying this. So here's this paper from DeepMind on the system called Spiral from a few years back at ICML, where they trained, using RL, they trained an agent to write these kind of brushstroke programs to, for example, reproduce images of human faces. And they're able to have success with this. But the thing is, reinforcement learning does, I think deservedly so, have a reputation for being notoriously fickle and unstable. It's quite difficult to tune it to work well on these problems. And so as a consequence, thus far, this has really only been deployed on relatively simple domains. Languages that have really only a few types of primitives and a few types of operators. We can also ask, well, what about program synthesis? We've seen some amazing results from, for example, this dreamcoder system, which I presented this as something that discovers program abstractions for these logo graphics programs. It actually does that on the way to building up a system that can take just raw images, just raw pixels of these logo graphics and outputting their programs. And it does all this without any supervision. There are no ground truth image program pairs. But one of the things that allows the system to work is it depends fairly critically on a carefully designed training curriculum, where we give it simple shapes that are explainable by simple programs, so we can discover these lower level subroutines and then gradually present it with more and more complicated data. And in the real world, often those kinds of curricula just aren't available. We don't know how to decompose our data into simpler subparts. We're just given a big dump of very complicated data and we have to handle it. And the last thing that I think we've seen used to try to overcome the need for supervision are just domain-specific tricks. So for example, suppose I'm trying to infer programs that represent 3D shapes. Maybe I assume that my models can only use some fixed number of primitives and can only learn to select from some fixed set of combinations of those primitives. This is exactly the approach that was taken by the UCSGNet paper, which is an unsupervised system for inferring constructive solid geometry trees for 3D shapes. And more recently, a recent archive preprint, the system called CSG Stump, which is an alternate representation of CSG trees, which is, again, allows us to use a fixed number of, it basically fixes the topology of the tree in a way that's amenable to putting this into a deep network, which is cool. But of course, these tricks are very specific to a particular language or a domain. These tricks only apply to constructive solid geometry. They can't be used for other kinds of languages. And by construction, they limit the complexity of the shapes that we can handle. We have to fix in advance a number of primitives, a number of layers of operations that we're allowed to use. This is still really an open problem, how to do this well without supervision. I'd also argue that another important direction to consider is handling more complex languages. That most of the prior work we've seen in this kind of visual program induction and generation space has been on fairly simple domains. Things like parametric constructive solid geometry, where we have just a few types of primitives and a few types of Boolean operators. And some other toy domains like we saw in the dreamcoder paper, logo graphics, or these 2D block towers. But real world designs, real world structures demand more complex languages. For example, parametric CAD uses this paradigm called feature-based modeling, where the designers actually draw these complex engineering sketches that have constraints, and then those sketches are then extruded and combined in interesting ways. And there actually is some existing work that does program synthesis, program induction, or program generation for this kind of data, but it is fully supervised. So that deep CAD system I mentioned before, generative model for these kinds of feature-based CAD programs, assumes it has access to a ground truth database of CAD programs. And there's also a paper that some collaborators from Autodesk Research and I published at CVPR last year, or actually earlier this year, which solves a similar problem, but again, it assumes access to a ground truth data set of these programs. So lastly, I think something that we should think about pursuing is how to actually discover new languages. So why is this important? Well, we have access to some languages that are already great for modeling 3D structures, like parametric CAD, feature-based modeling programs. And this actually seems quite appealing because many manufactured objects begin their lives as parametric CAD programs. So, why not try to recover the CAD program that created that shape? And that's a very reasonable intuition. But, are they necessarily the best choice? You can try to ask yourself, what language actually best describes a given data set or distribution of visual data? What language would I use if I had a data set of modern architecture? What would be a good language for describing this kind of structure? Or, maybe I have a data set of seashells or a data set of the geometries of fish bodies, right? All of these exhibit programmatic structure that we can learn to try to reproduce. And what would be a good language for that? And what do I mean by the best choice? The best describes a given language, a given data set or distribution. Maybe I mean that it's most compact. Maybe I care about a language that best facilitates some desired editing or interaction with these programs. So these are all interesting questions to consider. And then kind of the big question is, can these kinds of languages be automatically discovered? That would be quite amazing. So anyone who's seen any of the other talks I've given recently knows that I'm a big proponent of these neuro-symbolic modeling approaches, where we combine the best of both worlds of the flexibility of neural networks with the high-level reasoning capability of symbolic AI. And I think that this kind of approach actually could be quite useful for this automatic language discovery. And I'll sketch out a very high-level vision of what I think this could look like, where we could use flexible neural representations to discover what are the primitive types in our data set, and maybe even what are the elementary combinators that combine those primitives together. And there's been some work on something kind of like this in recent work in terms of automatically discovering libraries of primitive parts in, say, 3D shape collections. And then once we would discover these primitives and elementary combinators, maybe we would want to use something like the abstraction discovery procedures from DreamCoder or ShapeMod to discover higher level operators, higher level subroutines that combine these different primitives. And ultimately, what we'd really love to do is to actually solve problems 1 and 2 as a big joint optimization problem to get sort of the best possible performance. It's quite a challenging problem to consider, but I think this could be a really interesting direction to explore. Okay, and that's all I have to say for today. So I want to thank the organizers again for inviting me. I want to thank all of the students and collaborators who helped to make the work that I talked about today possible, and also to thank the NSF who funded much of the work that I talked about today. So thank you once again.
Thanks, Daniel. If you have any questions for Daniel, please make sure to post it in the chat so we can ask him. And I guess we can start from the first question. There is a question about if you can give some intuition on how you model, how the model reconstructs and CADs from point clouds. I think that's how the question reads, if I understand it correctly.
Yeah, sure. So the way that works, generally, I think both the way we did this with shape assembly and the way the deep CAD system works is they train a generative model. So it's a latent space that you can sample latent codes from and then decode into some sequence of program tokens. And then there's an encoder that's trained, which takes point cloud and maps it into that latent space. In the case of DeepCAD, that whole thing is trained jointly as a variational autoencoder, I believe. Yeah, that's how the system works.
Thanks. I have another question. Is there currently a limitation on the numbers of programs to be executed or modeled? Would you reckon that it would be a problem if we'd like to move from simple shapes like those in DreamCoder to complex shapes, say more realistic ones?
Yeah, I'm looking at this question in the chat. This sort of seems like this is two questions. I'm not quite sure how to answer the first question about limitation on the number of programs, but the second part of the question, moving from simple shapes to more complex shapes, yeah, I do think that is the challenge. So I think DreamCoder actually can handle some fairly complex shapes, but in order to do that, it has to be given the appropriate curriculum. So it has to see the simple shapes first, figure out the subroutines that it can use there, and then be able to apply those to discover more complex subroutines to represent even more complex shapes. And so the big challenge is when you're given a data set of real world shapes or scenes or what have you that are just complex from the get-go, how do you handle that if no one's telling you this curriculum? So that, yeah, I think that is the big challenge.
There's another one. Neural networks work best when the whole pipeline is differentiable. Do you think that it makes sense to think more about differentiable approximations of programs and operations?
Yeah, that's a great question. There's been there's been plenty of work that does this, looking at differentiable relaxations of these programs, whether they're like hard coded, like somebody figures out, oh, I can relax the language this way, or if I learn some differentiable neural approximation of the program. I think there's definitely room for further investigation there. There's sort of, obviously, you pay a price if you approximate it, if you approximate the program, but yeah, I think that this is such a hard problem that it's worth it, like people investigating multiple different avenues. So differentiable relaxations is one, further investigations in reinforcement learning is another, further progress on these kind of wake sleep kind of inference algorithms like the dream coder system. And probably it's going to end up being that there's no one approach to rule them all. There's going to be, depending upon your particular application, one of those approaches may work better for you than others. So yeah, I would be super happy to see more work in that direction.
All right, thank you very much, Daniel. I think we have to move to our next speaker. I have to say that as a roboticist, I want to apply everything that you've presented today into the real world and see how it works. But okay, so our next speaker is Luca Carlone. He's the associate professor in the Department of Aeronautics and Astronautics at MIT. His work includes seminal results on certifiably correct algorithms for localization and mapping, as well as approaches for visual inertial navigation and 3D scene understanding. He's the recipient of many awards, including most recently the Best Student Paper Award at IROS 2021, the Best Paper Award in Robot Vision at ICRA 2020, an honorable mention for IEEE RAL in 2020, and my personal favorite, the 2017 Transaction on Robotics Best Paper Award for his work on visual inertial SLAM, amongst many other awards. He's also a recipient of the NSF Career Award, the RSS Early Career Award, Google Daydream and Amazon Research Award, and also a faculty award from the Aeroastro department at MIT. Today, Professor Carlone will present recent work on 3D dynamic scene graphs. And so I'll give the stage to Luca. Thank you for joining.
All right, thanks, Tony. So I'm sharing my screen now. Don't be scared by my desktop. I think what I really want to show is these slides. And you should be able to hear me now and to see the slides, right?
Yes.
Okay, so everyone, is a true pleasure. First of all, thanks, Tony, for the nice introduction, and thanks everyone for tuning in. It's a true pleasure. I'm enjoying the talk so far in the workshop, and I think it's a very timely initiative. So thanks for having me. I'm Luca Carlone. I'm an associate professor at MIT, and I'm the director of the Spark Lab at MIT. And the plan for today is to tell you about the work we are doing on 3D dynamic scene graphs, and really about high-level scene understanding for embodied intelligence. Before even starting on that, let me say that I'm presenting this work, but this is really like amazing work by a large set of very talented students, including the ones that you're seeing here at the bottom of the slide. Tony's one, Marcus, Arjun, Yoon, Nathan, Jingnan, Andrew. And then I'm going to present something about learning on scene graph, which is work led by Rajat, Sian, and Lisa. So a lot of this talk is about talking about high-level scene understanding. And I will start with motivations about why we care about high-level scene understanding. And then I want to just stress the fact that we care about perception and scene understanding for embodied intelligence. So a lot of what we do and a lot of the algorithms we design are really motivated by robotics applications. And indeed, towards this goal of high-level scene understanding for robotics, I'm going to present this idea of 3D dynamic scene graphs. Okay, so let me start maybe with some motivations. This slide is essentially summarizing the motivation behind a lot of the work we are doing in the group. And the basic motivation is that if you look carefully, there is still a large gap separating what we consider right now as the state of the art in robot perception and what is the capability of human perception. And I can convince you that this is the case with just simple examples. In robotics right now, we're getting excellent algorithms able to do nice 3D reconstruction, being sparse or dense point clouds. For those of you who are familiar with the algorithm for simultaneous localization and mapping, Right now, you can just download a library like CorbSlam, DSO, like, there are many examples. More recently, maybe something like DroidSlam. So we're able to build this kind of sparse representation even in real time. And we're able even to build object-based representation, such as the pioneering work on SLAM++ from the group of Andy Davison. So in general, I would summarize that the state of the art in SLAM is getting pretty mature in building geometric representation, including, for example, points, lines, voxels, meshes. And this is what I call really the SLAM comfort zone. Again, SLAM is simultaneous localization and mapping. However, human perception is doing much more than that. And I just need an image to convince you that this is the case. If you look at this image for a few seconds as a human, you realize that from a single image, you can understand the geometry of the environment. For example, you can understand there is a road, there are buildings. You can understand the semantics. For example, you can detect the cars and you can identify the fact that a yellow car is a taxi, for example. And you can even reason on relations between different objects or agents in the scene. For example, I don't know, you can see that a person maybe is close to the street and is probably trying to cross the street. So this kind of high-level understanding and reasoning over geometry, semantics, and relation is something that is still out of reach for robot perception. So we are shooting in that direction, but why do we care about, humans are able to do that, but why do we care about having high-level understanding and understanding geometry, semantics, and relations for robotics? Well, the first observation is that high-level understanding is key to interaction. Right now, a robot that has just a pure geometric understanding of the environment can only understand very simple instructions. For example, nowadays, I can tell a robot, maybe a robot is building a map with simultaneous localization and mapping, and will be able to understand instructions like the one in this slide. So robot go to position X, Y, and Z. But in the future, I would not like to give such low-level instruction. I would like to give a little bit more sophisticated instructions to my robot. For example, I would like to tell the robot, robot, go grab me the cup of coffee on the table in the kitchen. And for the robot to even parse this kind of instruction, the robot will need a high-level understanding of the environment. We need to understand the objects in the environment, such as the cup, coffee, table. We need to understand even rooms, such as the kitchen. And we need to understand the relations among these objects. For example, the cup is on the table, is within the kitchen, right? So, so motivation is high-level understanding is fundamental for interaction with humans. But also high-level understanding is key to robustness, it's key to robust perception. And I typically use this single example, to convince you that high-level understanding is really important for robust understanding. If I do object detection in isolation, as a human, of course, I will recognize that there is a car in this pictured in this slide. But if I look at the context from which I cropped the image of the car, again, as a human, you can stare at the picture and you can realize that actually this picture does not contain a car. There is a large white van and the car is only painted on the van. So the mental process probably was something like this. You detected the ground floor, you detected the car, you detected the white van, and you reason on the fact that the car and the van cannot be physically at the same location. So you reason about the relation between these two things, these two objects in 3D space, and you concluded that one of them is not actually physically there in 3D space. So what I'm really saying here is that robust perception relies on simultaneously understanding geometry, semantics, physics, and relations in 3D. So we need all these ingredients to really have robots which are understanding the environment with the same robustness, reliability, and expressivity as humans. So a lot of the work I'm going to present today is about really having a perception system which are able to understand geometry, semantics, and relations in 3D. I will not get into the physics part, we are not there yet, but we have good progress on the other elements. So the plan in particular is to cover 3 topics. First of all, I want to introduce the notion of 3D dynamic scene graphs, which is really an effort to move from traditional simultaneous localization and mapping to this kind of high-level understanding I was talking about. Second, in the spirit of this workshop, I'm going to talk about learning on this kind of structure. I'm going to talk about how to use graph neural networks for node labeling in 3D dynamic scene graphs. And then if time allows, I'm going to touch on the challenges and opportunities. This is some initial work. There is plenty to be done in this research line. So let me start on introducing the idea of 3D dynamic scene graph. So what is a 3D dynamic scene graph? 3D dynamic scene graph is nothing less than a hierarchical representation of 3D scenes, of 3D environments. And I will start describing the video because I think it's giving a good picture of what a 3D dynamic scene graph is. Imagine that there is a robot or maybe a camera mapping a building. So a 3D scene graph is a representation, a graph-based representation, which will have different layers. So it's a hierarchical representation. At the lowest level, we have a metric semantic mesh of the environment. So this is a 3D reconstruction of the environment, including also semantic labels for the different areas of the environment. Layer two, we abstract the metric semantic representation into a set of objects and a set of agents. For example, you should see, and I will show you better these in next slides. There are humans moving around, so we are extracting essentially humans and objects in the environment. Layer three, we're extracting a set of places and structures. The structures are essentially wall, ceiling, and so on. And the places are location, the object that the robot can go to. And then, of course, if you go even farther, you can go to the level of rooms, buildings, and so on. So more formally, a dynamic scene graph is a directed graph where nodes are spatial concepts. Anything that lives in 3D space, for example, objects, rooms, humans, and so on. And agents represent spatio-temporal relations between concepts. For example, you can model the fact the edges are not super visible or partially visible in the video here, but the edges, for example, can model the fact that a person is in a given room at time t, or maybe a person is in a given room at time t, or maybe an object in a specific position with respect to the mesh. So this representation is quite different from things which are out there. First of all, it's a 3D representation. Most of the work on scene graph in computer vision is about placing scene graph in 2D images. This is a full 3D representation. And then something that is unique is that we are trying to really capture multiple levels of abstraction. You see that we have objects, room, and so on. And also, for those of you who are closer to robotics, something that is worth mentioning is that the level of places is essentially a topological map. Is a graph of places the robot can go to. So essentially, dynamic scene graph are kind of unifying metric map, which are the mesh here, with the topological maps, which is the graph of places over here. The graph is dynamic in the sense that we can capture agents and humans, robots moving in the scene. And the graph is also actionable in the sense that by construction, this includes most of the information a robot needs to move around in the environment itself. Something that is worth mentioning here, this proposal is something that we did a while ago. Tony was leading this stuff, but it's also excellent work by Hiro Armeni, and who at the time was at Stanford, I think, with Silvio Savarese. And they've been pioneering a lot of this representation. Our representation is very different. It's an evolution, which is more tailored to robotics, but I just want to give credit to the seminal work of Hiro. So we propose this representation, but in the papers, of course, the focus is not only about proposing the representation, it's about designing algorithms which can build a 3D dynamic scene graph from sensor data, in our case, cameras and inertial sensors in heavily populated environments, as the one that you see in this simulation. This type of algorithms, from our perspective, are really trying to go from traditional SLAM to what we call spatial perception engines, which are new generation of algorithms which are able to infer geometry, semantics, and high-level spatial concepts and relations. What I want to do in the next few slides is really telling you at the high level how we build the different layers in a 3D dynamic scene graph, and then later on I will jump into the learning aspects of it. So I want to start with layer one, which is the metric semantic mesh, which you see here at the bottom of the figure. And what we do here is to have a collection of algorithms that we call Chimera. It's an open source library at this point, which is able to build a metric semantic mesh of the environment from camera and inertial data in real time. And I will give you one slide introduction about Chimera. So Chimera is taking information from a standard camera. This is a real sense. We'll have images, we produce images, and we'll produce inertial data. And the result of Chimera is a 3D metric semantic mesh. So what you see here is a 3D mesh model, but the colors correspond to semantic labels. So for example, gray is the ground, light green are the chairs, and so on. I will not go into the details, but first of all, I want to mention that Chimera allows doing this 3D metric semantic mapping in a completely unknown environment. So the robot is starting in a completely unknown environment, and it's using some factor graph optimization to reconstruct its own trajectory. After reconstructing its own trajectory, we essentially do some volumetric mapping to reconstruct both the geometry and the semantics of the 3D environment. And then we convert this volumetric map into a 3D mesh. Something that is very cool, I will not have time to cover the details, but it's very interesting, is that once you have this 3D mesh, essentially we can enforce things like loop closures or deformation of the map after loop closure in a very natural way using a framework that we call post-graph and mesh optimization. And probably the most important part of this slide is that the code for Chimera is online. It's a very good, fast multi-threaded implementation. So, feel free to give it a try if you want. For layer one, we also have to be, something that I want to remark is that we have to be careful. We care about reconstruction in dynamic environments. We have to be careful about things moving in front of the camera. A basic approach, to mapping, which is not accounting for dynamic objects, will create artifacts. So imagine that there is a human walking in front of the camera. If you do a trivial, voxel-based reconstruction, we'll create artifacts due to the human moving in front of the camera. And what we do is essentially here, very simple idea, is use the semantic to filter out moving objects, such that essentially our 3D mesh in Chimera is only capturing static aspects, fixed, static aspects of the scene. So let me move to layer two. Layer two is one of my favorites. It's capturing objects and agents. And here I will start describing how we essentially extract agents, in particular humans, from the scene. So the extraction of the humans works in two stages. We have a neural network, a graph neural network, which is extracting dense SMPL models of humans from the image. And for this, we are using a very cool paper from the group of Kostas Daniilidis, which is called Graph CMR. And after we get this single frame detection, we essentially enforce consistency of the poses of the humans over time by doing some model-based tracking with a robust post-graph optimization. And as a result, it's pretty much what you see in the video. The robot can follow, can observe people in the environment, and at the same time build a 3D map of the environment and visualize these dense mesh models of the humans walking, nearby. And I think this is a very nice example. I think it's one of the first example doing this kind of large-scale 3D mapping and at the same time reconstructing dense 3D mesh models of humans. For the objects, we are distinguishing right now, two different types of objects. The first one is objects for which we do not have a CAD model. For example, here is a couch. We assume that we do not have a CAD model for these. And in this case, we just fit a bounding box. Instead, for models having, for objects that we segment and for which we have a CAD model, essentially we convert the mesh to a point cloud and we do some point cloud registration using a state-of-the-art algorithm, which is called teaser++. Okay. As a result of the object detection here, essentially we are splitting the mesh into a constellation of different objects that you see here at the bottom right. So layer two is including the places. The places, the way you can think about this is that places are essentially obstacle-free location. So these are points that the robot can go to without colliding into obstacles. And the edges in this graph represent paths that the robot can take without crashing into obstacles. So these are collision-free segments, essentially. So for this, we're using an existing library. We're an existing library from ETH, which is essentially building a generalized Voronoi diagram of the dense voxel-based representation. And from that Voronoi diagram is extracting a skeleton, which is what you see here in red in the slide. And this is very, it's a useful topological map because essentially you can use this graph for path planning, for example, for a robot. On top of that, we also segment the different rooms. And the way we interpret the room segmentation is really about taking the graph of places and clustering the graph of places into different rooms. And the idea here is to really take the advantage of both the graph-based representation, which is provided by the graph of places, and also the voxel-based representation that we build in Chimera. So the basic idea is that if you are clever about taking a 2D slice of the voxel-based representation, the 2D slice essentially will separate the different rooms. In particular, if you take the slice above the level of the doors, essentially that slice will clearly separate the different rooms. And you can use this kind of volumetric representation you can include this in a graph clustering algorithm. And as a result, essentially the graph clustering algorithm can learn, can do in a model-based fashion, can separate the different rooms. So this is about reconstructing the rooms or segmenting out the rooms. The last layer is buildings. For most of the experiments we have done so far, we're considering a single building, so there is nothing to be done. We just have to attach a single node, building node at the top of the graph. But I will take advantage of this slide to give you a little bit of a closer view of the scene graph, and in particular layer 2, which is one of the coolest, in which you have constellation of objects, and you can see the humans essentially moving around in the environment. Something that is also important to state is that while the metric semantic reconstruction can be done in real time in Chimera, currently the construction of the rest of the graph is an offline process. So here I'm saying the construction is offline and takes around 30 minutes. So after the data collection, we click a button, and after several minutes, we get this kind of 3D dynamic scene graph reconstruction. So I want to stress that we tried really to build this dynamic scene graph for many data sets, for a number of data sets. And here you see an example from a real data set on the left and a simulated data set on the right. These are 2 apartments, and qualitative results. You can see that here on the left, you can get a real apartment, you can get a segmentation of the 3 rooms, and you can get the detection of a number of objects. And I guess qualitatively, you can see that in both simulation and on the real scene, we can have pretty comparable qualities for the 3D reconstruction. We've been doing this for many other scenes, including subway scene, very large scale, and also scenes in which it's not really an indoor environment, it's kind of a neighborhood environment in which, of course, we do not have rooms. Of course, we do not have necessarily building structures, but we can have still the metric semantic mesh. We can still identify objects, and we can still identify the places, which is this cloud that you see here in red. So what I'm saying here is that the dynamic scene graph, you do not have to take the idea of the 3D dynamic scene graph as just an idea that applies to indoor environments, but this idea of hierarchical representation is something that you can apply and tailor to any type of environment. There are also very nice technical ideas, as the one that I mentioned before about enforcing loop closure through post-graph and mesh optimization. I will not get into the details. I want to move to the learning part of the talk, but I invite you to check out the paper, which is now accepted on the International Journal of Robotics Research, to look at the description of how we do loop closure by deforming essentially the 3D mesh, and also for more quantitative results there. We have a lot of quantitative results about visual inertial navigation, 3D reconstruction, the semantics, the objects, and so on. What I want to do next is to transition into how we are thinking about using learning to populate essentially 3D dynamic scene graphs. And I will talk in particular about node labeling in 3D dynamic scene graphs. So what is the problem here? In the first part of the presentation, I told you how to reconstruct, or how we can have algorithms to reconstruct this kind of 3D scene graph structure. But the algorithms so far that I described are able to segment out the different rooms. You can see that you have room 1 to, I don't know, room 15 and so on, and segment out the building. But somehow the robot is not really able to understand if a room is a kitchen or not, right? We have just generic labels for the rooms, but we don't know which one is the kitchen, which one is the bedroom, and so on. And similarly for the building, we are segmenting out the building, but we don't know if the building is an apartment building or is an office building. So what I'm saying is that in practice, in the scene graph, in particular in this hierarchical scene graph, there will be many missing semantic labels. And in particular, that is true for the top layers. The bottom layers, we have some metric semantic reconstruction, which can inform the semantic labels of the objects. But for the top layers, really, we are missing labels. Well, why are the labels important? That should be pretty clear. If I want to tell my robot, like, go and grab me a cup of coffee in the kitchen, the robot has to understand where is the kitchen and what is a kitchen. So it's important for this type of semantic path planning instruction that I can provide to my robot. They're important for visual Q&A. For example, I can ask the robot, like, where is the cake in the kitchen? And the robot must have knowledge about, objects and rooms. And in general, for high-level autonomy, it's desirable to get that kind of high-level understanding. So what we want to do here is really to use a learning-based algorithms, essentially to populate the missing labels in the scene graph. And the intuition is the one that I'm mentioning here at the bottom right of this slide. The intuition is that nodes in the 3D scene graph are highly correlated, and we can somehow learn co-occurrence. What do I mean here? So here, if I give you a partially labeled scene graph that you see here on the left, so the scene graph is partially labeled. I have the labels for the objects, but I do not have the label for the room. Well, as a human, you know that if in a room there is a bed, there is a book, there is a clock, well, most likely that room is a bedroom, right? Because you are learning somehow correlations between the objects in a room and the type of room. And that's the same thing that we want to do for our robot. We want the robot to use some learning-based algorithm to learn this kind of correlation between different nodes in the scene graph. Towards this goal, and this connects back somehow, like, to the first presentation today. We are proposing the use of graph neural networks, not only graph neural networks, but also we are proposing a new type of architecture, which is something that we call the neural tree. So the neural tree is something that we put on archive a while ago, is now like in a new RIPS paper. And the paper essentially includes both theoretical results, approximation guarantees, but we essentially show that through this new architecture, we can get much stronger results on labeling for 3D scene graphs. And in the next few minutes, essentially, I want to walk you through this idea of the neural tree. So the problem is, again, about inferring missing labels in a scene graph. We have some graph structure, some subset of the nodes might be labeled, and we want to infer the label for the other nodes. To solve this kind of inference problem, there are two main ways. There is something that I'm calling the old-fashioned way that is essentially doing probabilistic graphical models. You can interpret the graph as a Markov random field, maybe conditional random field, or maybe like some other factor graph. And what you can do is that you can impose potentials on the edges of the graph, and then solve some optimization problem to infer what is the most likely assignment for the missing labels. So it's just purely model-based. You solve an optimization problem, and you get the most likely assignment. And this somehow, like in the literature in probabilistic graphical models, is often handled through message passing. You can do something like belief propagation, or more generally, you can do loopy belief propagation, and you can try to infer these missing labels through the message passing. This is somehow the traditional way to do things. Of course, there is a new way, and we are well aware of that in this workshop. The new way is by using deep learning, and in particular, in this case, graph neural networks. In graph neural networks, we still have a graph, but essentially, we are trying to learn directly a message passing protocol without even going through the potentials and so on. And indeed, we do not even have to design manually the potentials on the graph. So just as a short recap, the way graph neural network will work is, again, you have a graph, you are attaching feature vectors to each node in the graph, and then you are having nodes implement some message passing protocol in which the nodes are essentially like, exchanging these feature vectors, and they're combining them using some function, an aggregation function. So the aggregation function is something that typically will involve a graph, a neural network. And there are many options for that. There are graph convolutional network, graph attention network. You can just have plenty of different schemes for doing the aggregation and so on. And in graph neural networks, you repeat this idea of exchanging messages between neighbors for a number of iterations. And what happens is that after a number of iterations, essentially each node will have a new feature vector, which is some combination of the feature vectors in the graph. And from this feature vector, we can apply another neural network and essentially predict what is the label of that node. Okay, and this is something that is typically called the read function. Again, implemented through another neural network that you will have to train. So what is the trade-off between these two different approaches, right? So the old-fashioned way requires knowing the potential to even set the optimization problem. And the issue is that the potential, if you start handcrafting the potentials in this graph, these are unknown in practice. And if you do manually set the potential, you may get an optimization problem, which is giving you a bad answer, essentially not a useful answer. So the first issue is that the potential are often unknown in practice. The second issue is that for many algorithms, graph inference on probabilistic graphical models is a tough problem. And essentially for algorithms like belief propagation, you only get guarantees for specific type of graphs. In particular, you get guarantees for graphs like such as trees, for example. On the other side, also the situation on the GNN, on the graph neural network side, is not perfect. It's well known that state-of-the-art algorithms are limited in terms of what they can express. And in particular, they cannot distinguish isomorphic graphs. And there is a growing amount of research on invariance and equivariance. There will be plenty of research because the basic architectures essentially are lacking that kind of invariance or equivariance that you would like to have in these classification problems. So the question that we really ask here is, can we use insights from graphical models to develop more powerful graph neural networks? So we'll try to essentially combine these two ideas to get a graph neural network which is slightly more powerful. And the beautiful thing here is that the idea is very, very simple. So our proposal is what we call neural trees. And I will start with the intuition. The intuition is that starts from an insight from probabilistic graphical models, which is about saying that inference in tree structure graphs is much easier than inference on generic graphs. This is something I mentioned in the previous slide. If you do belief propagation in trees, essentially belief propagation will give you the optimal solution. So trees are nice for probabilistic graphical models. This is so true that in probabilistic graphical model, there is a very popular algorithm, which is called the junction tree algorithm, that says, look, if I'm given a graph and I have to do some belief propagation in the graph, instead of doing that, what I should do is to transform the graph into a tree. This is called the junction tree. And I should rather do belief propagation on this tree to get an optimal inference solution. And you can see that the way you build the junction tree from the original graph is just by essentially creating larger nodes, which are including portions of the original graph, right? So each node here is including a subset of nodes in the original graph. So probabilistic graphical models are telling if you convert the original graph into a tree, then inference becomes straightforward, becomes optimal. And the question is, can we apply the same insight to graph neural networks? Well, that's exactly what we do. Essentially, the idea of neural tree is a simple one. It's about saying, look, instead of doing message passing on the original graph, you should transform the graph into a tree. And we don't use a junction tree. We use something that is called, is a bit more complicated. It's called the junction tree hierarchy. And I will tell you in a while what it is. But again, you just have to transform the graph into a tree. And then you have to do the standard graph neural network, standard message passing on the tree instead of the original graph. So this is the original graph. This is a junction tree. A junction tree hierarchy is just slightly more complicated. Essentially, it's a junction tree in which you have to expand each node till you expose the original nodes in the graph. Okay, so you just have to unpack a little bit the junction tree hierarchy. At the intuitive level, beside the motivation in terms of inference in trees is easier. I would say that the nice thing about this idea, like this kind of architecture, is that if you do message passing at the level of the junction tree hierarchy, essentially you're doing message passing over both the initial nodes in the graph, but you're also doing message passing over subgraphs. So it's kind of a more hierarchical take on graph neural networks, which I think is cool. And this idea of the hierarchy is just a way to expose the nodes, right? So we don't want to expose just the subgraphs, but we also want to expose the nodes, because the nodes are the ones for which we care about labeling, essentially. So this idea of the junction tree hierarchy, in the paper, you will see that we talk about a more general concept, which is called the H tree. The difference is that junction tree is just a way to get a tree decomposition, but in graph theory, there are many ways to get different decomposition in terms of trees. So H tree is a generic decomposition. It's something that is a little bit more general. And junction tree hierarchy is the instantiation of H tree in which you do this junction tree decomposition. And again, like, just to summarize, the neural tree is just applying standard message passing on this tree structured junction tree hierarchy. So what you would do is that you create, you take the graph, you convert to a junction tree hierarchy, you initialize the feature vectors. The feature vectors are well defined for the nodes, but they're going to be empty for the clicks, essentially, like in the junction tree hierarchy. And then you do message passing, and you get your inference results. I will skip these at this point. I think should be like, the idea should be pretty clear. And I will jump a little bit to the practical results. So here, again, we're interested in applying this technique. We're applying this technique in the paper also to labeling citation networks, like, more standard data sets. But really, the motivation for this work is about labeling 3D scene graphs. So we took the Stanford 3D scene graph data set, and essentially what we do is to remove a fraction of the nodes and try to predict them. And we're using, in this case, very early attempt, we're using really simple features. Like, for each node, we're using purely geometric features, while of course, like, you can do some word to back, and you can have, like, more complex features. And what you see at the bottom right are, some of the results. So the numbers that you see in the table are the percentage of the correctly labeled nodes. So the higher, the better. On the row, you can see different message passing models. So graph convolutional network, graph sage, and so on are different ways to do message passing. And what you see in this column is the result of doing message passing on the original graph. And in the last column is the result of doing the same type of message passing on the junction tree hierarchy, which is what we propose. And you can see that the boost in performance is quite substantial. Like, in some cases, we have more than 10% boost in performance just by transforming the graph into a tree before doing the message passing, which we thought was pretty cool. In terms of runtime, you don't lose too much here. If you do a test time, the training time will be which will be a bit longer, but at test time, you don't lose too much. Like, doing the forward pass in a standard network on the standard graph will take, like, 46 milliseconds. If you do this in the junction tree, will take around 65 milliseconds, so you don't lose too much. Ablation studies and so on, like, we'll skip all these because I'm running a little bit late. What I want to stress, and I will not go through the details of the theorem, but what I want to stress is that we have a nice theoretical characterization of the neural tree. And I will give you just the bottom line here. So we have an approximation result, which is saying essentially that with the neural tree, you can approximate any type of function which is compatible with a graph. So what is a function compatible with a graph are the typical functions that arise in probabilistic graphical models. So one way to see this is that a neural tree can approximate any function that would arise in standard probabilistic graphical models. Not only that, we can say that we can approximate any type of function over graphs with an accuracy epsilon, with this arbitrary accuracy epsilon, and we can also characterize the number of parameters that we need to get that level of accuracy. And also the number of parameters grows linearly in the number of nodes in the graph, which is very nice. Does not grow badly in the size of the graph, it grows linearly. And it only grows exponentially in the tree width of the graph. So a way to say this result is that really what we are saying is that a measure of complexity of a graph is the tree width instead of being the number of nodes. And if you have a small tree width in the graph, essentially you can do very accurate inference with a small number of parameters. So the bottom line is that the significance is that this result is saying that we don't need many parameters in the neural tree to approximate any function of our graph. And we can have a formal characterization of the expressive power, which is improving, like, over the state of the art. There is always a catch. The catch is that, of course, we still have an exponential dependence on the tree width of the graph. So the catch is that while this will work out nicely for scene graph in which the tree width is pretty small, if you are considering different problems in which the tree width is large, this might become a little bit intractable. Okay, and there are solutions around that. You can sample and so on. But I want to be very upfront about that limitation. So let me conclude and let me go over, like, a few slides about things which are clearly missing here. We very excited about this progress, but there is much more to be done. So I will talk about a number of slides in which I essentially tell you about what are the clear opportunities, what are things that we must do as a community, like in this direction. The first one is getting real-time performance. I'm summarizing here past, present, and future, like in few bullet points. But in the past, we're now very good at building metric maps of the environment with point clouds, voxels, landmarks, and so on. Currently, we're able to get real-time metric semantic maps. Chimera is an example, but there are other libraries, other implementations as well. But our current dynamic scene graph model is something that is built offline, and it takes several minutes. The future is really building this kind of high-level hierarchical representations in real time. And actually, I want to also advertise recent work going in that direction, which is the work from the group of Federico Tombari, which is indeed going towards real-time scene graph prediction. I would say that that work is mostly focusing on objects and relation among objects. It would be nice to extend this kind of work to predict essentially rooms, buildings, and all the other layers that we have in this scene graph hierarchy. And I think this is something that is going to be feasible in the next in the next few years. The second issue is about robustness. The way we build the scene graph is pretty much bottom up. We start from a semantic segmentation of the mesh, and then we reconstruct the other layers in the scene graph. And things are working out nicely in simulation, in which the labels are very nice. But of course, if you use some sort of graph neural network, which is not fine-tuned to an environment, you can get plenty of incorrect labeling. For example, in this picture here, if you look closely, this is the face of a human who is picking at something on the ground, and instead is classified as a cat. So essentially, the issue is that if there are segmentation and reconstruction failures, these will easily cascade into failures of the reconstruction of the scene graph. And instead, what we need is really a framework which is performing more of a tight inference over the different levels of the scene graph and over geometry, shapes, and semantics. In the next slide, I was going to advertise some work in that direction. I think Andrew Davison is doing excellent work in that direction. We have some paper at RSS, but really there is much more on category level shape priors, which are kind of bridging semantic categories with geometric information. Other things that needs to be done is essentially extending this idea of 3D scene graph to other sensors. LiDAR, for example, is a very important sensor in robotics. There are starting to be work doing metric semantic reconstruction with LiDAR. It would be nice for this to be extended to build scene graphs instead. And generality, of course, as I said, scene graphs, as I presented them, are mostly for indoor environments, but you can really apply the same idea to abstract, streets, buildings, neighborhoods, cities, and so on. So you can really extend, depending on your application, you can extend this model to other problems. And of course, a big open problem is about applications. Can you apply this to manipulation, human-robot interaction, navigation, long-term autonomy, and so on? And we see plenty of opportunities there. So I'm running out of time. I will conclude here. In this presentation, I mentioned that there is still a large gap separating robot and human perception. And we really need to go beyond SLAM and think about real-time 3D high-level understanding. Towards this goal, I presented the 3D dynamic scene graphs. I presented algorithms to build the 3D dynamic scene graph from sensor data. And I talked about the neural tree as an architecture to perform labeling on a scene graph. And of course, there are many, many challenges. So plenty of work to be done in this direction. So we'll stop here. I will thank you for your attention. I will thank the students performing this excellent research and also the sponsors supporting it. And if there is time, we'll be happy to take questions.
Thank you very much, Luca. That was an excellent presentation. I really love both the theoretical and practical results. So I think we are a little bit out of time, but let me perhaps, if there's no question from the audience, mention that, well, this workshop was also about uniting the communities of computer vision, computer graphics, and robotics. And I think that thanks to Daniel's presentation, Luca's presentation, also Sivan and Elisa, I think there's some clear intersections between the communities here that we could leverage. I can foresee 3D dynamic scene graphs leveraging the representations that Daniel presented. And I hope that was useful for all the participants here, and I'm looking forward to see what we come up together as a big community that we are. And with that, we'll close the session 1 on structural representations for 3D scenes. And I guess I'll pass the spotlight to Kai-Chun, and we will open in a few minutes the second session. Thank you very much, Luca, for joining, and thank you all the rest to
Thanks, everyone. It's a pleasure. Yep. Take care.
Yeah, thanks, Kai and Tony. Yeah, maybe Faye, you can try to start sharing your screen and set up.
Can everyone see it okay?
Yeah, we can see the mountain.
Okay, okay. So maybe let's have a couple minutes break, or should I start now?
Yeah, I think probably you should start in 1 minute.
Okay, okay, that sounds great. Let's just stick to the schedule.
Thanks.
All right, so maybe let's get started. Hope everyone can see the screen okay. So welcome everyone. So this is the first workshop on structure and compositional learning on 3D data. And so far we have seen great success in terms of building the structure, compositional structure scene representation for the scene. And now it's an interesting question how we can use that for robotics. This is the topic for session 2, compositional structure in robotics. And me and Danfei would be co-hosting this session. My name is Fei. I'm currently a research scientist at Google, and Danfei currently is a research scientist at NVIDIA, and soon will be joining Georgia Tech. And yeah, so what this session is all about, classical robotics, which involves accurate modeling of the environment, and the method that leverage planning and control works very well in factories with clean and repeatable setups, but they struggle to scale to a novel, complex, and unstructured human environments, like the one we see on the right. Additionally, can an agent be trained in one environment and then be deployed in another environment? This type of generalization poses higher requirement for the agent. It requires the agent to understand the compositional structure, compositional nature of complex environments. In recent years, we see a surge of methods that can leverage compositionality to solve robotics problems. One popular way is to represent a scene as a graph. For example, using topological map as a new map representation of the scene to guide an agent through an environment is popular instead of using metric maps. Or using metrics, or using symbolic scene graph and geometric scene graph to do task planning and motion planning, such as the work we see in the middle and we'll be hearing from Yifeng during the session. These works show that by leveraging compositional properties, learning can be more efficient and generalization can be improved. We will hear more from our speakers. The compositionality can also appear in the task level. For example, the individual steps in a long horizon task can be the edges in a graph, and completing the long horizon task now becomes traversing a path in the graph. This type of graph representation have been used in some recent works. Sometimes the single representation of a graph and task level representation of the graph are intertwined through affordance. The agent can learn these affordance by interacting with the environment. So we'll also have some work that learns the affordance through interaction with the environment during this session. Without further ado, I would like to open the stage for our speakers. We'll be hearing 4 talks today, 2 longer keynote talks and 2 shorter spotlight talk. So let's welcome the speakers, and I will stop sharing at this point, and I will introduce the first speaker. All right, let me bring back the Zoom screen, just 1 second. Our first speaker is Shuan Song. Professor Shuan Song is an assistant professor in the computer science department at Columbia University, where she directs the Columbia Artificial Intelligence and Robotics Lab. Her research focuses on computer vision and robotics. She is interested in developing algorithms that enable intelligent systems to learn from their interactions with the physical world and autonomously require the perception and manipulation skills necessary to execute complex tasks and assist the people. So let's give the stage to Shuan.
Thank you very much. Okay, I will try to share my screen. Okay, are you able to see my screen?
Yes, yes.
And it's the right screen, right?
Right, yeah.
Okay, cool. So, okay, hello everyone, I'm Shuan, I'm from Columbia. And yeah, so today the title of my talk is Structure from Action. And yeah, in particularly, I will focus on like the structure, not on the scene level, like the talks, the previous talks, but more on the like a lower object level. And we'll have a special focus on articulate objects. And in particular, I will talk about how we can discover and understand the structure of articulate objects by actively interacting with them. Okay, so to start, let's talk about first, what is articulate object and how we typically represent their structure. So articulate object is very common in our environment. And here are just a few simple examples, such as eyeglasses, folding chairs, or scissors. And for all these articulate objects, their structure is often described by their kinematic chain, which consists of a collection of rigid parts and then connected by a set of movable joints. And here, the joint type typically describes the possible movements between the 2 rigid parts. So for example, a revolute joint will allow rotational movements between 2 rigid parts. And in contrast, prismatic joints will only allow translational movement. And for all articulate objects, oftentimes their kinematic structure often directly defined or described how a robot or an agent should be able to interact with them. So for example, by understanding the object's part segmentation, the agents will be able to understand which part is movable and therefore where they should apply actions. And similarly, the joint parameters, if the agent is able to understand the joint parameters, then it will be able to help them in determining their action directions. So for example, the action should be perpendicular to the revolute joint, or typically in parallel with a prismatic joint. However, the task of trying to infer this kind of structural information for articulate objects from a single static image is actually extremely challenging. And to a certain degree, it's even kind of ill-defined problem due to the ambiguities introduced by objects' self-occlusion or their unknown kinematic structures. And typically, if you, in the literature, you can see that an algorithm that is designed or trained for one type of object or one object category often cannot work for other objects that has different number of parts or different joint types without retraining. So for example, in the slides here, if you have like a model trained for a 3-drawer cabinet, typically it will not work for a cabinet with a revolute joint or has fewer or more number of drawers. So as a result, in robotics or computer vision, we often need to train separate networks in order, just to handle different type of objects or different object categories. And as you can imagine, this kind of training is very hard to scale up in reality. However, in reality, like in real world, in most of applications, we almost never really need to infer object structure from a single static image. So instead, for us, for humans, we can easily interact with objects and then use our action to help us to better understand objects, the object structure, and also build a mental model about the object's underlying 3D structure. So for example, by interacting with objects, we could segment the object's rigid part by observing the movement under interaction. Right. So for the part that is moving together, we kind of know that they belongs to the same part. And similarly, based on the part's motion trajectory, we are also able to kind of infer the drawing parameters and their limits. So for example, from the action trajectory, here we can indicate where the rotation axis is, like both in terms of their position and orientation. So this kind of skill of using our own action to discover object structure is particularly useful when we need to deal with novel objects that we are not familiar before. Right. So in this video, you can see this kid is actually playing with the sunglasses in order to understand its articulation. And as demonstrated by many cognitive science studies, active interaction has been playing a very critical role in helping us making sense of our physical world around us. So the question we want to answer in this talk or in our research is, can we allow our robots or intelligent agents to also kind of acquire this kind of skills? Okay, so in today's talk, I will talk about two of our recent projects to show how we can leverage active interaction as a way to discover objects' articulation structures. So in the first project, the title is Act the Part, Learning to Interact to Discover Articulated Object Structure. And it is a work in collaboration with Samir and Kiana, and this is just presented in this SCCV conference. So again, the goal for this project is to discover the kinematic structure of an articulate object through interaction. So here is a very simple example of an articulate object, scissor. And its kinematic structure is also very simple. That consists of two rigid parts linked by one revolute joint in the middle. So the question is how we can allow the algorithm to segment each individual part without knowing anything about this object or even just in general the concept of scissor. So as you're probably aware, that the task of unsupervised or supervised object part discovery is a very well-studied problem in computer vision with a large number of prior works in literature. And the key idea behind all this work is to leverage the motion consistencies observed in the video frames in order to segment each individual object parts. So here the hypothesis is that all the pixels share a similar motion pattern should be segmented as one part. So it is a very reasonable assumption and it works very well for many applications as shown here. However, one of a very critical question that often gets shoveled under the rug is, where does all this motion come from? Right. So if you think about it, it's actually a very important question because in reality, most of the articulate objects will not move by itself, which means that all this motion needs to be triggered by someone with some kind of interaction or action. And once we start to think about using active actions to create motion, we'll quickly realize that it's actually a very tricky problem. Like it's very tricky to get it right because there are just so many actions a robot can apply on objects. However, most of them is, well, like not all of them is equivalently informative. So for example, if the robot just kind of randomly poking and pushing the object, the whole object, like for example, the whole scissor will just move together and the system will not be able to discover each individual part. At most, it can segment these objects. Right? And however, if the agent is able to choose a smarter action, for example, holding on one part and pulling the other part, then it will be able to discover one of the moving part. However, in order to kind of fully discover all the movable movable part, in this case, is like 2 parts, the algorithm will need to apply a sequence of action and also aggregate all the information into like one model in order to reconstruct the full structure of the object. So we can see that whether an action or interaction is informative or not, it really depends on what the system already know about objects. And the action should be selected based on this information. So to address all these challenges, we propose the algorithm ActPart, where the algorithm goal is to generate a sequence of hold and push action that would result in informative motion for object part discovery. So our key idea for this project is to couple the action selection together with the motion segmentation algorithm. So on a very high level, the algorithm will use an interaction network to select informative action to apply on the object. And then the perception network will try to segment the moving part based on the observed motion, and then update the algorithm's belief about objects which will be used to infer the next best action to apply. And then in the following slides, we will dive into each of individual modules and provide a little bit more details about how it works. So the first is the interaction network, where the network will take in the current part segmentation belief, which is like aggregated history of segmentations, and the image observation of the objects as input. And then it will try to output a heat map for hold and push actions, where the push action is actually conditioned on the hold action. And the action with a higher score, which indicate as the redder pixels here, will be executed. And to train this network, we use 2 categories of rewards. So we assign a smaller reward for all the actions that will trigger any kind of motion. And the second reward is provided only if the action triggers informative motion. So in our case, it means that this resulting motion helps the algorithm to discover a new object part. So this reward is actually determined by the history aggregation module that we're going to talk about later. And after the system executes this action, the perception network will take in the original and the new observation as inputs, and then try to segment the moving part between these 2 observations. So basically, it will predict 2 masks of the same moving part that is aligned to the current and the new observation respectively. So note that here, the algorithm actually do not estimate pixel-wise flow, since the accurate flow on the objects is actually much harder to estimate, especially for textureless objects, which is a lot of the objects that we are considering in this project. And we found that the binary mask oftentimes is sufficient for the algorithm to establish a cross-correspondence between frames. And then the algorithm will compare the predicted object mask with its existing part segmentation in its memory in order to update its belief. So essentially, the history aggregation algorithm need to decide or answer the question whether the new mask corresponding to any existing segmentation in its current memory. So if no, then the algorithm will try to add this new part segmentation into its memory. Otherwise, it will just updating existing segmentation. And in the end, this decision is used to provide the reward signals for the interaction network. So now we have the network. Here is the training and testing objects that we used in our experiment. So note that we only trained, the model is only trained on we only trained one model to handle all these different objects. And also in particular, our algorithm is only trained on objects with 2 parts. And we can later see that it is able to handle objects with more links and significant different kinematic structures. So first, we will look at some qualitative results. So our algorithm is purely trained in simulation, but later we can see that it is able to, we are able to test it on real world objects and images with a very simple setup at home. So here is on the right, you can see the work from home setup with basically with the iPhone taking a top-down image on the object. So here is a step-by-step result. So to start, the memory bank or the memory of segmentation, part segmentation is empty. And then the algorithm will infer affordance map for hold and push action. So here, the score for holding action is pretty much uniformly distributed over the whole eyeglasses, while the push action is conditioned on the selected hold action. And then a human operator executes these actions based on the policy inference result. And then after execution, the perception algorithm will segment the object part based on the observed movement. So in this case, both the front and the left tempo is moved together. Therefore, it's assigned with the same mask. And then with this segmentation, this time the algorithm will focus on selecting action that would help it to discover another tempo. So finally, in the last step, we can see that the algorithm is able to kind of select action, fix its mistake in the first step, and able to segment each individual parts in the end. So here is the final part segmentation results inferred from the whole interaction sequence. And we also quantitatively evaluate our algorithm in a simulated environment where we have the ground truth object mask, and we can just simulate the actions. So on the right, you can it's the segmentation performance evaluated by mean IOU. So from the plot, we can see that our algorithm is first able to improve its own performance with more interaction steps, and also is able to achieve better performance compared to alternative methods. And here are more results on the real world objects. Notice that some of the object actually has not a deformable structure, which is also never seen during the training process. And of course, you can find more experiment results and also quantitative, both quantitative and qualitative results on our website. And we also have an online demo that you can try out to play with the training model to see the inference. So to quickly recap for this project, in this project, we introduced ATP, which is able to kind of learn an efficient strategy for isolating and discovering object parts, and is able to generalize to novel object categories with unknown kinematic structures. However, the interaction strategy learned in this project is limited to very simple 2D actions inferred from a 2D top-down image. Therefore, this method cannot really handle a large number of real-world articulate objects that actually requires more complex action trajectories. So more importantly, the interaction policy learned by this framework cannot really be directly used for any downstream applications, such as goal condition manipulations. So in the next project, our goal is to kind of to see whether we can extend this interaction policy by using a general action representation that is able to support continuous 3D actions with closed loop control, and then evaluate the learned interaction policy in a goal condition manipulation task. And in the end, we will see that whether such a policy would help agents in better understanding the object structure. So the title for this project is called UMP-NET, which stands for Universal Manipulation Policy Network for Articulated Objects. So this work is done by Zhenjia and Zhanpeng. So the goal for this project is to learn a single manipulation policy that is able to handle any articulate objects based on their visual observation of the objects. So here is a small subset of the objects that we considered in this project. So as you can imagine, like training a single policy for all these different type of objects is very challenging, because the action trajectories that required for manipulating all these objects may vary drastically due to their different kinematic structures and their 3D geometries. Therefore, I think even before start this project, an important question to ask is whether it is even possible to train a single network that's able to summarize such a diverse collection of action trajectories. So our hypothesis when we start this project is that it is possible, since that although all these sequences are very drastically different, many of them can be summarized with a similar high-level function that is conditioned on the object's underlying kinematic structure. Right? So for example, the motion trajectories of opening a door can be represented by a function conditioned on the door width and also its rotation axis. And a similar function can also be used for opening a fridge, a laptop, or even a folding chair. Right, so therefore, by learning to interact with a diverse set of articulate objects, the system should be able to acquire a generalizable knowledge about the object's articulation structure, and also how those kind of structure would react to different robot actions. And we think that such knowledge should be able to generalize beyond just a specific object instance or an object category. Therefore, it should allow universal interaction policy for any articulate object. So concretely, what do we mean by effective interaction policy? So first, we think that the policy should at least understand where to interact with objects. So here is a toilet example. We know that the cover is movable, so effective policy should choose to interact with the cover instead of the base. So that's the first step. And the second is the policy should also be able to identify the effective action direction that will change the object state. So in this example, it will mean that the policy should choose to push up the cover instead of pushing down. And then the last requirement is to produce an action sequence that's with a consistent direction. So what do I mean by that? So for example, given a state given the object state that's where the cover is kind of partially open in the middle, we know that the action both pushing up or down can effectively change the object state. But because we know the initial state of this object, the cover is closed, therefore the policy should really choose the up direction instead of the down direction in order to visit normal state instead of going back to the initial state. So we call this attributes, like this kind of consistent action direction, as arrow of time awareness, which means that the policy should be able to tell whether an action will change the object state back into the past or forward into future. And apart from just encouraging the policy to exploring new states, this arrow of time inference should also allow us to actually directly apply this policy to a goal condition manipulation without any goal condition training, which we'll talk about how we can do that later. Okay, so now we can see that we defined how we describe an effective policy. Now the next step is how we can train a policy that's able to satisfy all the requirements. Right, so the first step, again, the policy needs to infer the position of interaction, and similar to ATP, the network basically directly inferred a heat map that's indicating the likelihood of the object movement when applying an action in this position. And in this experiment, in the simulation, we use a session gripper to execute the action. And the network, after they inferred the position, the next step is to infer the action direction, which is done by sampling and evaluating different action directions in the continuous SE3 space. Here, the network will estimate the distance, which is the potential movements of the joint state given action direction. And also, in order to avoid the back and forth action, the network will take the initial state as the input and invert additional arrow of time label for each action candidate, where the positive label indicates moving away from the past, which is labeled as red, and the negative value indicates moving back to the past, which is labeled as blue. So the actions with positive AOT label and the highest distance prediction will be selected by the network and executed. So here is, again, the training and testing object categories used in this project. As you can see, it is significantly more diverse compared to what we use in the previous ATP project. And also in this project, we introduced objects with prismatic joints, like tables, like drawers, windows, those kind of objects. And the whole policy is trained with self-guided exploration, as described before, without any human demonstration, scripted policy, or any predefined goals. So here is an example results for open-ended exploration. So on the right, we will plot out the number of novel states visited by each of the policy. So in this task, we want the system to visit as many novel states as possible. And here we compared with where to act, which is an algorithm that's trying to infer a single-step interaction from the current image observation. And because where to act is not aware of history, from the third step, you can see that it starts to infer back and forth actions, where our policy is able to continue move the object towards the novel state. So although there might be some like single heuristics that can be applied on top of a single step message in order to avoid this kind of back and forth motion, However, those heuristics will not be applicable for a goal condition task, which is the main motivation for this work. So in a goal condition task, the algorithm will need to generate action that will actually move the objects towards a given goal state instead of just a random novel state. And in the following slides, I will kind of demonstrate how we can apply the learned model or the learned policy directly in a goal condition task. So first, to select the position to interact, the algorithm will still need to infer the movable part of the object. However, additionally, it also needs to select the correct part to interact, especially when there are multiple movable links. So to do that, we use a very simple method, basically compute a difference mask between the initial and the target observation, and then use the mask to filter out actions. Basically, for the positions that does not change, we will not select to interact with it. And the next is to select the action direction. And what we do here is basically swap out the initial image with the target image and use that as an input to the policy. And then by executing the action with the negative arrow time, the policy will try to move the object back into the past. However, because we already swap out the past with the target state, the policy is actually moving the object towards its goal. So that's how we change the policy to kind of do goal conditions manipulation. So the key idea is basically swapping the history with the target and also execute the action with negative arrow time. So here's the result for goal condition manipulation, where we compared with a single step inverse model. And on the right, we plot out the normalized distance to the target state for each step, where lower is better. We can see that the inverse model actually gets stuck somewhere in the middle, where our policy is able to choose the suitable actions in order to reach to the goal state. And here is another example. And so in this example, we can see that the inverse model chooses suboptimal action in the beginning of the interaction sequence. It is quite a typical failure case for inverse model, especially when the observation is far away from the goal state, where our policy do not have this problem. So now we show that it is possible to train a single policy to manipulate different type of articulate objects. So now we want to go back to our original hypothesis or original question, which is that in order to learn such a policy, the algorithm, we kind of hypothesize that the policy need to understand the object's underlying articulate structure, which means that the action selected by the policy should in some way reflect its belief on the object structure. So in order to validate this hypothesis, we're going to visualize the policy's belief by computing the join parameters that's able to, the join parameters that we can infer from the selected actions from the policy. So here is how we're going to do it. So given an object and also a sequence of action inferred by the policy, we'll first compute a common 3D plan shared by all these actions. So which means that this plan should be roughly perpendicular to the rotation axis. Therefore, provide an estimate of the joint axis orientation. And then for each of the action, we will independently vote for the joint locations. And then we'll use the locations with the highest agreement between all different actions as the inferred joint location. So combining the joint location and orientation, now we can infer the full all the parameters of the joint axis. So here we visualize it as a right line. And then similarly for objects with prismatic joints, we can also we can basically directly average all the selected action direction in order to compute the joint axis. So we can apply this very simple algorithms on all the objects and also together with the actions that inferred by the policy. And here are some examples of the example results for different objects with their inferred joint axis and their orientations. So you can see that it's including both objects with regular joint and also prismatic joints. So from this visualization, we can see that without any kind of supervision, direct supervision on the joint parameter, our model is able to infer a reasonable joint parameters for both their orientation and position, which indicates that the system is able to acquire some kind of implicit understanding about objects articulation structure through the active interactions. And again, you can find more experiment results and the visualizations on our project website. So to sum up, today I talked about two of our recent projects to show how we can leverage active interaction as a way to discover articulate object structure. Start with a simple 2D, a single step 2D interaction to a 3D closed loop manipulation policy. And I think a common idea applied for both methods is that instead of trying to learn how to segment or manipulating one type of objects from human demonstration or annotation, what the system actually trying to learn is the ability to understand objects' underlying kinematic structure through their active interaction. And I think this is a pretty fundamental knowledge that is needed when handling novel objects with unknown categories. And I think that's the end of my talk. With that, I would like to kind of thank all the collaborators who, and also students who actually make all this project possible. And if I have time, I would like to answer your questions.
Thank you so much, Ron, for the presentation. Very nice talk. So I have gathered some questions from the audience, and I have also some questions myself. So maybe we can start the discussion. So I guess for the first ATP work, you applied it in real. I guess I just want to ask, like, did you run into any trouble for sim to real, and like, do you apply any special techniques there?
Yeah. So for ATP, we have. I think our test in real is kind of like really just very simple setup. Like we didn't even use the robot to do the interaction. We use human to do the interaction. And I can easily expect that there will be a lot of difficulties when we actually use the robot to do interaction. And actually that's something that we experienced when we trying to apply the second project with a real robot setup. And I think the sim to real gap, the typical things is like the image may be different. And the second is actually the physics may be different. I think in both projects, we experience the second part a little bit more. So I think in simulation, we set up some common parameters for joints like frictions and things like that. And we can apply typical actions for different objects. But in real world, actually the joint, the physics is different from object to object. Therefore, the action actually also need to be aware of that. So I think that is like one of the challenges or like limitation that our model is not able to model and therefore handle in the sim to real process. Yeah.
Great. And also in the ATP work, it seems the agent learns to do this kind of counterfactual analysis, of which part can move, which part cannot. And one thing that I noticed is that the movement, the probing action is always quite small. So I'm just wondering, does the segmentation, for example, rely on the probing action to be small? Like, can it be adapted to like larger? So you have to do some like correspondence mapping or something like that.
Yeah, so I would say that the probing action is actually not like we didn't on purpose make it small, and also because we are predicting the segmentation instead of optical flow or a kind of flow, bigger motion is actually better. But you can imagine if we're trying to predict a pixel-wise flow, then smaller action is preferred because it's easier to establish correspondence. But I think in our framework, actually bigger motion actually can make the difference bigger, and typically it's easier for the network. Yeah.
Thank you. And then we have a question from Kai Chun. He was curious that for the ATP work, is the frame applicable to manipulation cases that both grippers need to move? And does it apply to multiple grippers, like 3 grippers or 4 grippers? I guess the intuition is that in some cases, such probing would be more efficient. Like you can hold both ends and then probe the middle. Yeah, so just very curious about that.
Yeah, I think that will definitely help. Like I think especially, so we start with this project with a simple object like cedar, because that's 2 parts, and it's just like very straightforward. That's with 2 parts, you're holding one part, pushing the other part, right? But if you have much complicated objects, then you really like. I think it's clear that you can benefit from more like end factors. You can like kind of even just moving several parts simultaneously will probably give you the results in fewer steps. Even if it's like an object with only 2 parts, if you can like open them together instead of holding and pushing the other one, then you can actually get the 2-part segmentation in 1 step. So yeah, definitely, I think that will help, but also it probably will introduce more complexities in the network and also the system. Yeah.
Cool. We also have a question from the audience, Ahmed. Do you have any insight on how act-to-part can scale to multi-part objects with no joints or rigid joints? For example, tool manipulation with part affordances. Can we use their learned functionality in some way?
With multi-part objects with no joints. Well, I guess the key idea for act-to-part is actually to create motions in order to do segmentation. I guess if you have an object that's with multiple parts but do not have joint, which means that you cannot create relative motions between parts, then it's probably not suitable to use this framework to segment their part. But instead, maybe you can use like other interactions or other, maybe just perception algorithm that's able to kind of segment the part based on visual observations instead of trying to analyze the motion. Yeah, so I would say that's a different type of task.
Cool. Yeah, and then I guess I also have a question. So it seems in the second work, the universal manipulation policy, you're implicitly modeling the joint, right? Because like each of the motion is kind of perpendicular to the revolute joint, so you can later run like a consensus algorithm to get the joint out. So I just want to pick your brain on, do you have any insight on like explicit modeling of the joints versus like implicit modeling of the joint? Because I think that would be a very interesting like design decision, like which one do you use?
Yeah, so I think when we started this project, back then we have worked on like how to explicitly kind of do the post estimation for articulate objects, and we just found that it's so hard, and it's like sometimes it's ill-defined. But I kind of feel like learning how to interact with object in some sense, it feels easier, like you just infer the action, and we also show that it works, or at least in simulation in the cases that we test. So from that experiment, I think the idea I got is that in order to interact with an object, you probably don't need to have very precise like part segmentation or very precise joint estimation. You just kind of need to get a rough idea, and then your action will self-correct and able to kind of give you a good way of interacting with objects. And in particular, if you look at for prismatic joints, right? So for drawers, we realized that actually the action don't need to be very perfectly aligned with the axis. You can still open the drawer. So maybe kind of have those kind of understanding is already sufficient for interacting it, which means that you can skip the steps of doing like post estimation and directly to do interaction. And then, yeah, so, but also we can show that this kind of action is indeed based on some kind of understanding of the object structure, which is what we show in the visualization.
Cool. Yeah, I think I agree with you, and I think it's also motivated by the example, like you have the zigzag slot, right? So it cannot be easily modeled just by a couple of joints. I think the real world constraint is more diverse, and yeah. And we have a question from the audience, Yang Zheng. Do you think it's meaningful to add a goal of interaction during training, since the interaction usually shows the user's intents and the state of the object also implies a potential goal? So I'm not sure which one like this work referred to, but I guess it's a general question.
Yeah, I think it's for the second project, because we kind of highlight that during training, it doesn't need any specifically human-defined goals. We just use the history as a goal, and then as a result, we can swap the history and then do goal conditions. I think it's probably going to be helpful if we can have additional goals provided by human. It's just like at which cost, right? So in that case, we kind of need to, I think for more complex objects, maybe having some predefined goals or human specific goals, it will help the exploration process and therefore makes the training more efficient. But for relatively simple objects, I think it's not very necessary, as we show. Yeah.
Got it. Thanks. And we have a question from the audience. Named the CVPR Zoom 47, great choice of name. For the UMP net, is gravity considered? how much dynamic physical factors affect the performance. So like the friction and joint damping, like something like that.
Yeah, so this is something that is very hard. So for the first question, gravity. Yes, gravity is considered is like in a simulation we apply gravity, and also all the objects when we load it. As long as the object itself has some like pretty well-defined gravity direction, then we will load it with the gravity along with the gravity direction. And I think for the second question is whether dynamics or physical factors affect the performance. Yes, of course, it will affect. And in particular, I think in particular for objects, there are objects that you really need to apply a lot of force in order to open it. There are objects that's relatively easy to open it. So I think that's a very important factor. But it's very hard to do it right in simulation. So I think that probably requires some like real world training in order for the system to understand that. Yeah, so I think that's a very good next step.
Awesome. Yeah, so I think that's all we have for now. And thank you so much for the talk and the insightful discussion. And yeah, hopefully we'll see you in the panel discussion like later.
Thank you. Bye-bye.
All right. Yeah, with that, now I think it's good to introduce our next speaker. Our next speaker is Krishna Murphy. Krishna Murphy is a PhD candidate at Mila and the Robotics and Embodied AI Lab, advised by Liam Paul. His research vision is to enable embodied agents to perceive, to reason, and act intelligently. To achieve this, his work intertwines understanding of the world, including physics, robotics, vision, graphics, with deep learning machinery. And with that, you can take that away.
Hi, so I just wanted to do a quick check. Can you all see my screen and hear me okay?
Yes.
Great. So yeah, it's good to be here. Thanks for organizing this workshop. You know, it's a very timely theme. And today I'm going to be talking about our recent work, which is going to appear in a month at Corel. Now, so the work is titled Taskography, Evaluating Robot Task Planning over Large 3D Scene Graphs. And just going by what our previous speakers have been talking about, I'm sure a lot of you might already have heard about 3D scene graphs and their promise. So this talk is going to be about how can we, now that we have these representations that are emerging, how can we effectively use them for robot task planning? This is joint work with Chris, who was at the time an undergrad at the University of Toronto. He's now just started his PhD at Stanford. And there were a number of supporting authors who I'd like to acknowledge: Mohammed, Andra, Vibhav, Mustafa, Liam, and Florian. So with that out of the way, let's dive right in. So you might have heard about 3D scene graphs, and you know they're really promising abstractions of a scene, and they encapsulate various properties of a scene, like metric properties, semantic and spatial, or topological representations. And the kind of 3D scene graphs we're talking about are pretty much aligned with what Luca was talking about a while earlier. So you have a scene represented as a factored graph where you have objects, places, and then at a level above you have rooms and then floors and buildings. And at each level you have like unary and binary attributes that basically indicate what kinds of actions you can take on a pair of objects or a single object. And so far, 3D scene graphs have been used in a number of planning problems, but what we try and argue in this effort is these planning problems are still, they don't capture all of the complexities you'd have in like real world tasks. There have been significant advances in, semantic path planning or object retrieval, find an object in a scene, leveraging your prior knowledge of the structure of a scene. And more recently, we've been seeing like more complex task and planning, task and motion planning efforts, but still, with a limited set of objects, which is still like a big advance in the task and motion planning context if you're dealing with dozens of objects and leveraging 3D scene graphs there. But what we were interested in is, can we somehow test the limits of 3D scene graphs for some of these symbolic like task planning queries? So what we did in this work was to build a taskography, which is what we call our large-scale benchmark for task planning. So our benchmark is based on the Gibson dataset, where we take each building, and there are scene graphs provided for each building. And for each scene graph, we annotate plannable attributes. So what can we basically annotate affordances and define planning problems. So we have about 20 planning domains. And just a quick note of distinction between grounded and lifted planning problems. Like we have grounded planning problems, which are concrete planning problems you define over instances. So, go to the kitchen and get me this particular cup. That would be a grounded planning problem because all of the entities in the specification are grounded. And you'd also have lifted planning problems where you don't actually care about the instance. It's more of a category level plan. So it could be like, get me any cup from the kitchen. And what we do is we also provide like a whole bunch of classical and learning-based planners that run on this benchmark. So we have, in terms of classical planners, we have optimal planners as well as satisficing planners, and in learning-based planners, we kind of have like 2 or 3 modern variants, some of the most promising variants on the benchmark. And the categories of tasks we're dealing with are largely, one category, really popular category of late is the rearrangement planning problem. As many of you might know, like rearrangement planning is, it's a generic planning problem where you need to rearrange given set of K objects into their target locations. And this really encapsulates a broad range of other planning problems which can be reduced to rearrangement. And we have like a courier, which is a version of rearrangement, but with like an optimal knapsack sort of flavor. Like you need to still do rearrangement, but the robot has a knapsack which can store a finite capacity, and each object has a different weight. And this effectively embeds like combinatorial planning problem, combinatorial optimization problem within a simpler rearrangement loop. And we have like lifted variants of these problems where the goals are not concrete instances, but more category level. So once we built this benchmark and we ran all of the planners over these 3D scene graphs, we had a few interesting observations. So the first thing, so in this benchmark, you kind of see, we show like 6 domains from the benchmark. And for each planner, we compute the length of the plan it produces and the time it takes to produce this plan and a failure rate. So lower failure rates are better. And as we go from left to right, we start getting into more and more complex planning domains. And we make a distinction between optimal versus satisficing planners and like classical versus learning-based planners. So optimal planners, really, they tend to produce an optimal plan without like worrying about real-time execution capabilities. You just need a plan that is optimal in terms of plan time. You have the least number of steps, the plan length, sorry. And there are satisficing planners. As you can see, there's a lot of domains in which optimal planners do not perform well. So this is pretty much like we gave these planners about a day, or in some cases even more, to run, and they haven't been able to produce a plan. And this is because the states, when you talk about a building 3D scene graph, you have thousands of nodes, and each node has multiple actions you can take on it. So the branching factor gets really, really large. And what this means is the planners, optimal planners, do not have enough computation time to like reason about all of these possibilities. So what ends up happening is you often need to make a compromise. Like you don't need an optimal plan. You need a plan that would work. So a plan that satisfies your constraints of the task planning problem. So we have like satisficing planners, but we see that for satisficing planners, their failure rates tend to shoot up as we go to more complicated domains. So you can see that in some of the most complicated domains, they have failure rates anywhere ranging between 40% and 100% of the time, which is clearly not ideal. And we see that state-of-the-art relational policy-based planning techniques, they do not scale to the size of a scene graph that's a building level with thousands of nodes. But the techniques that do scale are techniques that somehow intelligently prune a scene graph to only focus on task relevant attributes. And based on all of these observations, we make two central claims, which I'll like quickly try and give you a flavor of. So the idea is, if tractable and real-time task planning, particularly in large 3D scene graphs, needs progress on both ends. Like you need to somehow figure a way to sparsify or prune a lot of these 3D scene graphs. And we propose a technique that's called scrub that does this. And the idea, the intuition here is, if you have a planning problem, like you need to fetch an object from the kitchen and put it in the living room, you really only care about the critical path between the kitchen and the living room and everything that the robots need to reason about in between. Like you don't care about what's happening on the other floor or other buildings. So the idea is, somehow when you're given your task, you need to use the task specification to contextualize your scene graph. And we propose a technique and we call that scrub that exactly does this. And the other end is, since learning based in scene graph planners, they perform really well. But one drawback we've seen in learning-based planners is they need lots and lots of replanning iterations. So learning-based planners, basically, when you're given a scene graph, they just prune the scene graph and take the most promising, let's say 25 nodes, and then use those to come up with the plan. And if they fail, they'll expand the blanket to about the most promising 50 nodes and replan, and then the most promising 1,000 nodes or 100 nodes and replan. And in this way, they need a lot of replanning iterations, especially as tasks grow more complex. So we need to somehow make these planners exploit the scene graph hierarchy to reduce the number of replanning iterations. And we do that by a procedure we call seek. So scrub is kind of provably minimal in the sense that it'll yield a scene graph with the least number of nodes. And it only takes a few milliseconds. Again, I'm skipping over all of these details because we're almost out of time. So the idea is, scrub is a technique that you can run, given a task planning query, you can scrub the scene graph to yield like a minimal scene graph for grounded planning problems. And you can see that it greatly reduces the number of operators and state variables. And after scrubbing, we noticed that the total planning time reduces by a lot, and without compromising with plan length too much. And we also see that optimal planners, which could not otherwise run without scrubbing, they were able to solve the domain after scrubbing. And then we proposed this other algorithm called seek. Again, not going into too many details, but the high level idea is it'll ensure that all of the important objects in the scene are reachable from the root node of the scene graph. And by doing this, it greatly reduces the number of replanning iterations, especially in lifted planning problems, as you can see here. Like without seeking, you would incur a lot of replanning steps, but after seek, you get a replanning step that's almost a third. And just to give you a quick overview of what we do and what we do not do, we don't claim to have solved everything yet. So we provide an API, which we call taskography API, which should be out soon with the data set. It's going to support the creation of a lot of other domains. So in the paper, we show two different classes of domains, rearrangement and courier and the lifted variants. If you wanted to define other domains and test the whole suite of classical and learning and optimal and satisfying planners on your new task, it should be really easy to do with the taskography API, which should provide you access to all of these low-level attributes in the scene graph. So far, we've only been dealing with fully observable environments and deterministic state transition and only on symbolic planning queries. So there's a lot of work to be done to relax these and to go towards task and motion planning, which is basically the gold standard for robotics tasks. So I'll leave you with these thoughts here. So in summary, taskography is a large task planning benchmark over 3D scene graphs, and then scrub and seek are two really strong techniques which can serve as baselines for future work in this area. So with this, I'll take questions. I'm happy to take questions as long as time permits. Thanks so much.
Yeah, thanks, Krishna. It's a great work. I'm very excited about this, yeah, especially the capability of like expanding it, because recently we have this work at Gibson 2 and behaviors, which allows you to do much more actions than pick and place. So I would very much like to see like yeah, some later follow up that leverage the taskography API and all these potential actions. I guess I have a question about your work, which is I saw in some of the planning example, the number of steps is like 60 or 70. So that might indicate the scene graph is not very well built, right? So I'm just wondering, do you think it will be helpful when you have a hierarchical scene graph, or like the scene graph like itself is better built, so it doesn't require so many planning steps? So what's your insight there?
Yeah, that's a good point. So the number of steps, I'd say, as is the metric to evaluate a lot of task planners. Firstly, that I feel it's a bit misleading, because at least in the symbolic task planning level, you consider each step to have the same cost or complexity, which does not make sense when you have to deal with the complexities of motion planning. Like, clearly taking one path, which involves maybe opening a lot of doors to get to a place, is much more complicated than taking a path that does not require you to interact with as many objects. So in a way, a lot of these hidden costs get abstracted away, and I suppose like actually somehow trying to reason about how expensive each transition is. That's a very important step in trying to see, you know, what does 60 steps actually mean in terms of whether it's more complicated or not. So in that sense, I'd say at least the symbolic planning community, they don't really reason about all of these, except for maybe like having these as transition costs if you have a way of estimating them. So yeah, I'd say there needs to be a more nuanced discussion around this. But in general, I echo your sentiment. One of the hopes, you know, as I listed as a third point on the slide, is with this benchmark, we kind of know how planners perform on this particular representation. So this might inform how you want to design a newer representation, like how you want to tweak a scene graph.
Cool. There's another question. It seems that scrubs reduction is application dependent, and what are the factors impacting the amount of reduction? And also, does it make sense to use learning for scrub? We are also a little bit like out of time, so maybe you can yeah, answer it like in a few sentences.
Yeah, sure. So I'll say that scrub is actually application dependent. It works well for grounded planning problems, but not so much for lifted planning problems. And since we're like out of time, I'm happy to go into a more nuanced discussion over Zoom chat, if that helps.
Awesome. Thank you so much for the presentation, Krishna.
Thanks so much.
Yeah, with that, I would like to introduce our next speaker. Our next speaker is Yifeng Zhu. Yifeng Zhu is a PhD student in the computer science department at University of Texas at Austin. His research lies on the intersection of robot learning, robot control, and robot planning. He is interested in general purpose robot autonomy, especially its social impact on people's daily life in all aspects. With that, please take that away.
Thank you. Thank you, Faye, for the nice introduction. Can you all hear us? Hear me?
Yes.
Yeah, cool. Okay, then I'll get started. So hello everyone. My name is Yifeng Zhu, and I'm a third-year PhD student at University of Texas at Austin. And today I'm very glad to present at this workshop, presenting our work, hierarchical planning for long horizon manipulation with geometric and symbolic scene graphs. And then so the problem that I'm considering in robot manipulation is the robot manipulation for everyday tasks. And then such a kind of tasks present three challenges in overall. First of all, the robot needs to operate for long horizons, reason about long-term manipulation and interaction with objects. And then it needs to process raw sensory data, especially, for example, high-dimensional images. And then it also needs to complete various goals. And how do people usually perform everyday manipulation tasks in the past? A notebook framework, task and motion planning, has a very good ability to generalize the long horizon tasks. However, it requires prior domain knowledge, specifically domain files, and also usually this framework abstracts away the perception part. On the other hand, the recent resurrect of deep learning has enabled end-to-end learning for robot manipulations. And then this kind of approaches can process raw sensor data directly. However, end-to-end learning approaches typically fail to generalize on-scene goals. So how do we get the best of both worlds? So basically, we want the representations that can take the perceptual data so that it can has an abstract semantic concept. For example, in this picture, a plate is on the table, and also has the spatial information of the object, like for precise spatial reasoning, like a plate is at the location X, Y of the table. So in overall, we want the representations that can capture both semantic concepts and spatial information. And also this representation is grounded in raw sensor data. And this representation has compositional structures to enable to generalize the on-scene goals and also long horizon tasks. So this brings us to look into the scene graphs. And the scene graphs has been explored in computer vision community for a long time. For example, the scene graph has been used for 2D images tasks, and it also being used for action predictions in instruction videos, or in 3D environments where some people use 3D scene graphs for long-term navigations. And then our question is, how can we utilize these nice representations for our robot manipulation for both planning and control? And then this brings us to our theoretical scene graphs in this work, where we take, which is a two-level abstractions. In these representations, we take the image observations, RGB images, to first generate geometric scene graphs, and where it contains the object informations of the spatial information, specifically 6 poses here, which enables precise spatial reasoning. And then based on this geometric scene graph, we have another higher level of abstraction, symbolic scene graph, which contains the abstract semantic informations of the objects. And then more specifically, how we generate this hierarchical scene graph is that we use a pose estimations to estimate the poses of each object so that we can generate geometric scene graph whose nodes are the 6 poses and the edges are the relative poses. And then we have a heuristic defined symbol mapping function in this work to generate symbolic scene graph from the geometric scene graph. And then in this symbolic scene graph, we have the nodes whose attributes are the object categories and edges are the semantic relations. And then on this geometric scene graph, we can do a continuous motion generation so that the robot can actually interact with the objects. And also on this symbolic scene graph, we can do symbolic planning so that we can do a long horizon planning. And then based on this hierarchical scene graphs, we propose a hierarchical planning algorithm which consists of both motion generation and symbolic reasoning. More specifically, first of all, we pass the symbolic scene graph and the given task goals into a neurosymbolic planning model, and then outputs the next reachable symbolic subgoal. And this planning model is based on regression planning networks from previous work. And this planning model does not require any domain files defined, and it can just train from a very small set of demonstration data. And once we get this next reachable subgoal informations, we ground this next subgoal information into the geometric scene graph. And by symbol grounding, we mean that how to incorporate the symbolic informations into the geometric information. And the way that we do in this work is that we transform the attributes of the original geometric scene graph to a grounded geometric scene graph, where the node attributes are the poses that are relative to the of the objects in the subgoal information instead of the original pose information. And then once we get this grounded geometric scene graph, we pass through a geometric graph neural networks and predict the motion primitive parameters. And then the robot executes the motion primitive, finish it, and then take the new observations to check if it needs to continue the plan or the task is achieved. To test our representation and the hierarchical planning, we designed a kitchen rearrangement tasks which contains 6 hoop objects, 3 cans, 3 boxes, and then we also define motion primitives, which is pick, place, and push, which covers both prehensile and non-prehensile motions in manipulation. And for more training details, our pose estimations we use is the pose estimator DOPE, which is training for the realistic simulation and VC from NVIDIA. And the neural symbolic planning model is based on regression planning network, which I just mentioned, that can train just on demonstrations of simple tasks and also does not require symbolic transition model a priori. And finally, our motion generation model is training in a self-supervised learning manner. And also this is all done in simulation. And how does our model perform? And we first quantitatively evaluate in simulations where we test on tasks from 2 object tasks to 6 object tasks. And here we compare with 2 baselines where the random and MLP that here shown does not use the graph-based motion generation model. And then as our model should, and then our model, while our model is trained on short demonstrations only between of 1 to 2 objects, our model can generalize the task with longer lengths and also on singles because it's only trained on 1 to 2 objects and it has never seen a task to like 5 objects and 6 objects. And most of the failure here is from the motion planning part, so that actually our model generalizes well on the task level. And also compared to 2 baselines, our model pertains to good performance, even generalized to 6 object tasks. And also during our evaluations, we vary the initial configuration so that our model is also robust to the various initial configurations of the region. And in terms of the planning efficiency, we compare with a task planning temp method PDDL stream, and then we show that our task planning model is 4 orders of magnitude faster. And then the reason is that our task planning model is based on neural network prediction instead of searching, so it saves a lot of time in terms of the searching algorithm. And also our motion generation is 3 times faster. And this is also due thanks to the constant inference time of graph neural networks, while in PDDL stream, they need to sample parameters in simulation for a lot of time. And then here's an example of a robot, of how our algorithm works. The robot first takes about 12 images of the scene, and it generates a hierarchical scene graphs. And here I only show symbolic scene graph for simplicity. And then this symbolic scene graph is passed the neural symbolic planning model along with the task goal. And then the planning model computes the next sub goals and next reachable sub goals, for example, here in grasp soup can, and this is grounded to the geometric scene graph. And the graph-based motion generation model computes the motion primitives parameters to execute this motion primitive. And here's another example of our model executing on 4 object tasks. And we also quantitatively evaluate our models on real robot, ranging from 2 objects to 6 objects. And we conducted 34 trials in total, and we achieved 70.6% success rate. And in summary, we present a structural representation of hierarchical scene graphs, which is object-centric, perceptually grounded, and compositional. And then we propose a hierarchical planning algorithm based on this representation to enable the robot manipulation for long horizon manipulation tasks. And finally, we use experiments to validate that our method, our approach generalized to longer horizon tasks while maintaining efficient planning. And with that, I would like to thank my collaborators, and I would like to take any questions. Thank you.
Thank you for the talk, Yifeng. I think this is a great talk. I have a question about the geometric scene graph. So it is. I can understand that the symbolic scene graph can help you do planning, and it makes sense to use a graph there. So I'm just wondering what's the insights of using a geometric scene graph to do motion generation, because I would assume you can just like get the depth map of the scene, and if you also get grounded entity in that depth map, you can do like a traditional motion generation. So I want to get your insights on what's the advantage of using a graph structure there for motion planning. Thank you.
So first of all, in our work, we only use RGB observation, so we don't take any depth information here. So we can get the pose information, but not the direct depth images. Yeah,
I see.
And also using this graph-based model, although in this work is a little bit simplified version, but like if we have more information in geometric scene graph, like I think this is a more general framework to just include more information into this graph and then train a GNN models to predict the motion primitive parameters.
Got it. So yeah, then I guess another follow-up question is that is collision detection or collision avoidance explicitly modeled or not?
I think in our work, in our motion generation model, it's implicitly included. So like in simulations, we actually run the full-fledged planning model in simulations to detect if it's collision, and then it fails, and then we just collect positive samples in simulations. Yeah.
Got it. Yeah, very cool. Thank you so much. If there are no more questions in the audience, I think we can move on to the next chat, next talk. Yeah, great talk, Yvonne. Thank you.
Thank you.
All right. So I think we have come to the last talk in this session, and the speaker is Rusbe. Rusbe is a research manager of the prior team at Allen Institute for AI, also called AI2, and the affiliate associate professor of the Paul G. Allen School of Computer Science and Engineering at the University of Washington. He has been a pioneering figure in the area of embodied AI and leads efforts including AI2 Thor, Manipulate Thor, Allen Act, rearrangement problem definition, and etc. I'm very excited to hear your talk, Rusbe. Please take it away. Thank you.
Thanks, Faye, for the introduction. Let me share my screen. Can you see the screen?
Yeah, perfect. Thank you.
Okay, cool. Okay, so I'm going to talk about learning visual representations, language, and scene dynamics via interaction with the world. Okay, so in computer vision, when we want to learn representations, usually we have a large scale data set, we have some model, and we do a number of different tasks. For example, if we want to learn in a supervised way, we classify different categories of objects, or some of the most successful self-supervised representation learning methods distinguish different transformations of the same image from other images. And there's a similar story in NLP. We download large corpus of text from internet, and there is that we feed into a model, and we train for a specific task. For example, we predict the next token in a sentence. But we believe humans learn very different. Nobody provides a larger scale data set to these kids to teach them how to manipulate blocks, how to learn about like physics of the words and so on and so forth. And we believe learning via using larger scale data set is a bit inefficient. And instead, our hypothesis is that we need to learn via interaction. Okay, so in this talk, I will cover 3 different projects. First, I will talk about learning language via interaction. Then I will focus on learning visual representations via interaction. And finally, I will talk about the benchmark that encourages learning scene dynamics and appearance via interacting with the world. Okay, so let's get started with language. So this project was led by Rowan, and here is the idea. So the word MOG is not just these three characters. It's not just MUG. There are a lot of attributes and functionalities associated to the word MOG. For example, a MOG can hold liquid or coffee. A MOG can break. A MOG can have a different temperature. A MOG can be used for pouring. So basically, there are a lot of functionalities associated to this word. Is not just this this particular symbol. Okay, so our hypothesis is that, or proposal is, we want to ground language by a functional word representation learned in simulation. So here you see a sequence of making coffee using a MOG, and at the bottom of the page, you see different states for objects. For example, in this case, so we have this MOG. It has a number of different attributes. For example, temperature is room temperature. Is it? It's breakable. It can be filled with liquid, and so on and so forth. And our goal is to have a grounded sense of the word MOG when we talk or hear about a MOG. Okay, so we learn from AI2 Thor, which is an interactive 3D environment that includes 20 different types of actions and more than 100 different types of objects. And the actions are contextual, meaning that, for example, if I imagine there's a pan on the stove, if I turn on the stove, the content of the pan gets hot. So meaning that the actions, the outcome of the actions depend on the context and or affect the context. And objects have different states. So in this work, we consider 42 different attributes. It can be temperature, mass, and so on and so forth. Okay, so first I will talk about the model, which we call Piglet, and then I will talk about two different tasks that we did using the Piglet model. So here is the key idea. So we learned two model components, one model for how the word works, we call it physical dynamics model, and another model to communicate the state of the word, which is this language model. And these two components talk to each other to produce reasonable information about the state of the word. Okay, so here I'm going to explain the physical dynamics model. So here in this picture, you see a pan. There's an egg inside the pan. And so the object that we are considering here is egg. Temperature is room temperature. Is cooked, attribute is false. Is broken is true. So it's a cracked egg. Then we apply this action, heat up the pan. So the outcome should be the following. So temperature should be hot. Is cooked attribute should be true, and it should be still broken. So we want to learn these transitions condition on the actions. So here is how we do that. So we have these tables of attributes. We use an encoder, which is basically a transformer model to encode these attributes. And then we also have an encoder for the action. So it's a simple MLP. And these both go to an action application module. And the output of that is fed into an object detector, which is, again, a transformer model, which is used to decode the next state of the object. Okay, so we pre-trained this model using about 300K different scenarios in AI2 Thor. And now I'm going to talk about the language model. So the language model has two roles. One is it can be used to encode the action input. For example, here it encodes the sentence robot. The robot heats up the pan. And also it can be used for decoding the state of the word. Like here, it says it outputs the pan becomes hot and the egg gets cooked. So the output of the language model is also fed to our action application module, and the language model also uses the output of action application module to produces that sentence. Also, we use very small amount of data, like 500 pairs of language situation examples to fine-tune our language model. Okay, so the first task I'm going to talk about is predicting what happens next given an English sentence, or basically an English sentence that describes the action. So here is the example. On this picture here, you see a mug which is filled with water. There's also a sink filled with water. So these two attribute tables show the different states. For example, filled with liquid, sink is true. The same for mug, and is picked up is also true. Then we apply this action. We provide the sentence. The robot empties the mug, and expected answer should be the following. So sink should remain unchanged, but the filled with liquid attribute of mug should become false. And the evaluation criteria that we use here is accuracy of getting all attributes right for all objects in the scene. So here is the result that we obtained. So first is no change. Basically, we copy the initial state to the next state. So we get like about 26% accuracy. Then we have this GPT-3 model, which is a language model, and it's trained or it's fine-tuned on our data. So that gets 22% accuracy. Then we have this T5 language model, which is a large language model, and that obtains 64% accuracy. However, our model achieves like 81% accuracy, and this is kind of interesting because Piglet model, which has learned through physical experiences in Thor, and it's about 100x smaller than the T5 model, outperforms T5 model by about like 15% difference. Okay, so here are some examples. Like this Piglet model gets all these attributes right. However, the T5 model makes a mistake and thinks it learns through text. Emptying liquid from an object makes all objects in the room empty. So it makes a wrong prediction for the state of the sink, which thinks it's not filled with liquid anymore. Okay, then I'm going to talk about the next task. We want to produce an English sentence summarizing the state change. So here is the same example as before. So the action is empty mug. So we want to produce the sentence. The mug is no longer filled with water. So the evaluation metric we use here are human comparison, blue score, and bird score. And these are the results in terms of fluency and faithfulness, some common criteria in NLP that, again, these shows our model outperforms the T5 model. These are some examples that, for example, that the Piglet model gets the state right. However, the T5 makes the same mistake as before. Okay, so here we show that learning a lightweight factorized word model for predicting what happens next is much better than a large model that's basically a heavyweight model that just learned through a large corpus of text. So it shows us physical experiences, and this particular inductive bias is important in learning learning such things. Okay, so the next part of the talk is about learning visual representation via interaction. Okay, so in computer vision, we usually have some data set of images or videos, and we train our models for a specific task. On the other hand, human vision is action and intention driven. It's enhanced by memory and so on and so forth. So in this work, we focus on learning via gameplay as a form of interaction. And then we apply the learned representations to different tasks, like reasoning about containment, reasoning about object permanence, and also reasoning about free space in front of the agent. I will explain the details of each task later. Okay, so here is the idea. So this work was led by Luca, and we play a game of cache. Cache is a variant of hide and seek where the agents hide objects instead of themselves. So here is a hiding scenario. We want to hide a tomato, so it goes around the scene to find a good hiding location. For example, opens a drawer and puts a tomato inside the drawer. And on the right, you see a seeking scenario that the agent roams around the scene, interacts with different objects. For example, here it opens the fridge and cabinets and drawers until it finds the target object. This task has several stages: exploration and mapping, where the agent explores the room and builds a map. Perspective simulation, basically it's a simulation of the behavior of the seeker, how the seeker behaves. So it hides the object in a way that the seeker cannot find it. It has the object hiding stage, where the agent finds a good hiding location given an egocentric view, and also manipulation stage, where we move the object to a target location, and finally there's this there's seeking stage. That the idea is that the agent goes around the room to find the target object. Okay, so here is the architecture that we use for this. So the pink part here on top shows the definition of the task. Then we have a sequence of frames. The frames go into a CNN model, and as a result, we get this embedding that we call a static image representation. The model has also a recurrent branch that encodes temporal information, and the embedding that we obtain from that branch, we call them dynamic image representation. So they have some encode some temporal information as well, and they are used to learn a policy and value and output an action. And the static image representations are used to create a map, and that map is fed into a CNN, and that CNN is used for this mental rollout to find basically to simulate the behavior of the seeker to find good hiding locations. Okay, so we consider two different types of tasks: low-level vision tasks and also higher-level cognition tasks. So let's first look at low-level vision tasks. So we consider different types of tasks. For example, depth estimation, surface normal estimation, traversable estimating traversable surfaces, like which pixels in this image are can be walked on. And on the right, you see this plot, which is shows loss relative to an ImageNet model. And we have different baselines: an autoencoder baseline, a classifier, a model that just only do classification, and this red bar corresponds to a cache model. So this plot shows that there's no significant difference between our approach and the ImageNet model, which is which has used a lot of supervision. Okay, so we also tested that on natural images as well. So we have these three different tasks: scene classification, depth estimation, and walkable surface estimation. Again, there are different baselines here. And note that our model, the cache model, has never seen a natural image. And again, it obtains very good accuracy. Like it outperforms all the baseline, and it gets close to ImageNet performance. Okay, now I'm going to talk about higher level cognition tasks. One of the tasks we considered was object permanence. So there's a famous experiment that there's a cart rolling down the track, and there's a cube at the back that they put it on the track, and the kid expects that the cart hits the cube and stays there. but they remove the cube from the track, so the car goes to the moves to the other side, and the kid gets surprised. So basically, they want to test if kids have an understanding of object permanence or not. So we try to replicate the same type of experiment using A2 Thor. So we have an object. Sorry, for some reason it doesn't play. Okay, so we have an object that goes behind these books, and we ask the agent to predict the location of the object. So kind of similar to the experiments that psychologists did before. The other task that we consider is reasoning about occlusion and containing. So infants before certain age, they cannot distinguish occlusion versus containment, meaning that they cannot tell if an object is inside another object or if it's behind that object. So we want to test our agent to see if it has such understanding. For example, in this case here, there's a cup. We put it inside the bowl and also behind the bowl, and ask our agent to tell us what relationship exists in this particular video. So we have other tasks as well. Like, for example, we ask the agent if it has seen a particular object or not, or reasoning about the free space in front of the agent. So there are different baselines that we considered, baselines that are just based on those static image representations, based on baselines that do only classification, and so on and so forth. And this blue line on top is our model, which basically outperforms the baselines for these tasks. So let's look at a qualitative example here. So this is the first stage, exploration. The agent explores the room. The agent only sees egocentric observations. It doesn't have this. It doesn't have access to this top-down view shown on the right. So after the exploration, it will find good hiding locations, assign a probability to each location to see which part is good, and then it does a mental rollout of the seeker behavior to see if the seeker can find the object. And the next step is evaluating hiding locations locally. By that I mean, given just the current view, it tries to find a good location for hiding. For example, in this case, behind this trash can is a good location. So it manipulates the object to that particular location, which is behind the trash can, to hide it from the seeker. And then we have the seeking trajectory, that the seeker that goes around the room, interacts with different objects to find the object of interest. Okay, let's look at some numbers. So we have two scenarios, training for training scenes and testing scenes. The subscript here shows the number of steps used for training. For example, H0 means hider without any training. H1 million means hider after 1 million steps of training. And different colors here show different seekers. Again, S0 means a seeker that's not trained. S1 million means the blue line means a seeker that's trained for 1 million steps. As you see here, and the metric that we use is frequency of finding the object. So the lower the better for hider, the higher the better for the seeker. So here, as the hider gets better, that frequency goes down, it means that it learns something meaningful. And also, as the seeker gets better, that frequency goes up. So that's shown in this plot. But the interesting thing here is that, so we asked humans to play as seeker and also as hider. So in training scenes, the top portion of the table, there was not much difference between a human hider and a machine hider. So the performance was more or less similar. However, in testing scenes, on unseen scenes, basically humans perform much better, and this frequency was lower compared to that 90. Okay, so here I talked about learning visual representations via interaction, and we showed that the performance that we obtain via interaction, by representations trained using interaction, were much more powerful than representations we obtain using static data. Okay, so the last part of the talk is about the benchmark that encourages learning scene dynamics and appearance characteristics while interacting with the scene. Okay, sorry. So this work was led by Prithvi, and it's about visual navigation. So here is the idea. So we have an agent, a localized agent. We spawn that into in a 3D environment, in an indoor environment, A2 Thor. And here is the typical task that go to the house plan. We use RGB data and depth data, and this we don't have access to this top-down view. It's just for visualization, and we show that the sample trajectory of moving towards the house plan view. Okay, so in visual navigation, here's what we generally do. So we have a source environment. We train our agent in the source environment. We learn a policy, and that and the source environment can be many different scenes. So we learn that policy, and then we apply that policy in a test environment, which is different from the training environment. Basically, here are the changes from the source environment to target environment. First, the scene layout is different, so it's completely different floor plan, and sometimes we assume there's observation noise. But one big assumption that we usually make is that we know this observation noise beforehand. And the third thing is stochastic actuation. So we assume their actuation is noisy, but again we assume that there is a model that's known beforehand. So the assumption here is that we often evaluate our visual navigation models under specific and limited target characteristics. However, in this work, we want to evaluate generalization across a rich and diverse set of changes. Okay, so we call this benchmark robust nav. So here is you see an agent operating in one of the scenes, but now we introduce some visual corruptions. For example, here you see a clean frame that the robot usually sees, but what happens if there's a camera crack on the basically there's a crack on the lens? Or the other type of corruption that we consider is dynamics corruption. So ideally, when we issue the move ahead command, the agent should move forward, but due to friction, wheel slippage, and these types of things, the agent might drift from the ideal path or from the expected path. So we introduce these two types of corruptions, and we want to make our agents robust against these corruptions. For example, if you want to design a robot and ship it to like a large number of customers, you don't know the visual characteristics, appearance characteristics, or dynamics characteristics of the place that your customers use that robot. So your robot should be able to adapt to those situations. So we introduced 7 visual corruptions at 5 levels of severity. And also we have 4 different types of dynamics corruptions. They can be due to actuation or the environment characteristics. So these are the visual corruptions we consider. So here you see the clean image. We have low lighting, lower field of view, some motion blur, and so on and so forth. And also for dynamics corruptions. So there's motion bias. So we add a bias to the translation or rotation of the agent, and that bias can be a constant bias or it can be a stochastic bias. We also consider motion drift, drifting from the expected path, and motor failure. For example, one motor doesn't work, so you cannot rotate in certain direction. We consider two tasks. The first one was point nav, going to a specific coordinate in a scene. That's specified by distance and orientation. And object nav, which is going to a specific target category. So in this case, for example, we should go towards the sofa shown on top here. And these are different actions available to the agent. For example, there are translation actions, rotation actions, looking up and down, and the end action, meaning that the agent should say, I'm done with my task. And here is a kind of common or standard architecture that people use. There's a goal encoder on top that encodes the task. There's a visual encoder. They're somehow combined, and that embedding goes through a recurrent model to predict an action. And there are some popular training algorithms such as DDPPO, and for metrics we use success rate and SPL, which is basically success but weighted by the path length. It encourages efficient path towards a target. So we consider 72 different configurations for different sensors, different corruptions, and severity levels. And here is the results. For the result I'm going to show you is for point nav RGB that uses only the RGB sensor, not the depth sensor. So here's the result for the clean setting. It's 83% SPL. So when we introduce the visual corruptions, the performance goes down, and this is expected. So that's nothing surprising. Same thing for dynamics corruptions. We see a drop in performance, and a similar story when we combine visual and dynamics corruptions. Here is the result for object nav using the RGB sensor. The drop that we see here is much larger compared to the point nav task. And here is the adaptation scenario. So we train our models in a source environment, and we want to test them in a target environment. So here we have a calibration stage. So there is a calibration step, and we allow the agent to interact at the target in the target environment to learn the characteristics of the target environment. Basically, the idea is that there is a limited budget, and using that budget, the agent should adapt itself to that target environment using a limited number of unsupervised interactions. So basically, we want to encourage learning these dynamics characteristics, learning appearance characteristics, just by a limited number of interactions, but without any supervision. Okay, so there are typically two approaches to this problem. One we call like zero-shot approaches, that we do some data augmentation or randomization in the source environment, and we hope that it generalizes to the target environment. The other approach is adaptation. Basically, the agent should adapt to the target environment via a series of self-supervised adaptation techniques. So we use this particular approach, which is a state-of-the-art approach, and we want to see how well our navigation model adapts to the test environment. So one type of adaptation is done via this auxiliary head, that given two consecutive images, the idea is to find the intermediate action that basically moves you from observation T to observation T+1. Also, there's another approach that they have tried. It's called rotation prediction. The idea is the following. So the image is rotated, and the task is to predict if it's rotated 0 degrees, 90 degrees, 180 degrees, and so on and so forth. So via rotation prediction, this basically there is no supervision. Everything is self-supervised. Okay, so here the dashed line on top that you see is without any corruption. And when we introduce the corruption, the performance drops to, as you see here. So these are 4 different types of corruptions, visual corruptions. And when we introduce data augmentation, we see a bit of boost in certain scenarios. For example, it doesn't help in the spatter case. And then for when we tried action prediction, self-supervised adaptation with action prediction, it didn't help much, or it reduced the performance. And when we tried rotation prediction, it helped in certain scenarios, but it didn't help in other cases. For example, it didn't help in the case of camera crack. Okay, so we introduced a framework to evaluate navigation models under significant changes in motion and appearance characteristics. And our goal is to encourage agents that can learn characteristics of their environment just by interacting with the environment without any supervision. Okay, so here's basically a summary of the talk. So first, I talked about learning language via interaction, and after that, I talked about learning visual representations via interaction, and showed that those representations are rich. And finally, I talked about this benchmark that encourages learning scene dynamics and appearance characteristics via interacting with the scene. So far in our community, we have had great progress using passive observation of the world, meaning using large scale data sets. So we believe it's time to move towards learning by interaction, so we can learn with a small amount of data, as opposed to relying on a large amount of data and on supervision. So we might be able to learn rich representation just by interaction, just without any external supervision. Okay, thanks very much.
Thank you, Rusbeh, for the talk. Yeah, so in the audience, please feel free to post any questions or unmute yourself to ask questions. To get started, I guess I have a question for the first work, Piglet. So so far, I think it shows great performance in terms of like rolling out one step this future. So I'm just wondering, have you considered doing more longer horizon tasks, like you not only need to heat up the pan, but you probably need to wash the vegetables and like make a salad. So what do you think, like the potential there of these models?
Yeah, that's a great point. So yeah, in that work, we just considered just the next step. What happens the step after? I mean, immediate next step. But it's a very great point, and yeah, we should be able to predict the next, basically perform predictions in long horizon settings as well. So that's all. Yeah, that's a great point.
Also, I want to connect with like previous talks that does planning. So I'm just wondering, is this kind of language model can also act as a forward model or a world model, so that you can do some planning with that? So what do you think?
Yes, so that can be used for planning, but language model might be, because if we consider just symbols, so it might we need to also learn the grounding as well. So basically, the plan should be, for example, if you use language for planning, there should be a step that maps that language to some form of planning language. So that's the missing step. Yeah, we can. So it might be easier to do planning using other types of techniques. But again, yeah, that's a good idea, that language model also can provide some plan. For example, there are some instruction following words that they provide a set of instructions to the agent and try to do planning based on those provided instructions. So yeah, there's some work in this domain, but in that work we did not consider that.
Got it. Thank you so much. And also, I'm very interested in the work Robust Nav. I think it opens up like great opportunity for the embodied AI community to focus on more on the real world kind of problems and the problems that you will see in the real world. I'm just wondering the kind of image augmentation techniques, is that specific to RoboThor, or is that just the image augmentation so that it can be applied to many other robotics benchmarks? So still like coming back to the topic of compositionality, because I feel that the image corruption or dynamic corruption, it can be like compositional and it can be added to other benchmarks as well. So what's your comment on that?
Yeah, sure. It can be added to other benchmarks. It's not something specific to Thor. It's for example, some of the visual corruptions are like a standard noise models that people typically use. So similarly for dynamics corruptions, so that also it can be easily applied to other frameworks that exist. So but we have a set of augmentation techniques, for example, texture augmentation and like color augmentation, lighting augmentation, and so on, which is kind of specific to Thor. But these are something, but all these can be implemented in other frameworks as well. So for example, we can change the texture of the wall, we can change the texture of the table and so on. But that functionality might be, at this point, might be just specific to Thor, but I believe it's not super complicated to implement in other frameworks as well.
Got it. Thank you so much. And thank you for the great talk. So I think we are approaching the end of this session. So just to summarize, I think so far we have seen some great work that leverage the scene structure as a scene graph. And from Krishna's talk and Yifeng's talk, we learned that we can do efficient planning on this type of representations and do inference on this type of representations. And from Rusbe and Shuran's talk, we learned that you can start to learn this type of scene structure or like dynamics from interactions. So currently we can do inference on this, and we start to accumulate techniques that can do mapping and create these type of structures from active interaction. So I think it's very exciting time to apply this compositional 3D structure in robotics, and I look forward to the development of this field. With that, I would like to pass the torch to back to Kai-Chun, and thank you so much for attending the session. I learned a lot.
Thank you so much.
Yeah, thank you.
Thanks, Rusa. Yeah, and also a big thank you to all of the speakers in the morning session. Yeah, let me share the screen on my side. So now we move into the first paper poster session in the morning. So this is a full day workshop. So there are another 2 talk sections, a panel discussion, and another poster section in the afternoon. So please make sure that you will come back at 12:30 EDT. And now we are moving to the paper poster section 1, and we are using Gatherly instead of Zoom. So we have 14 amazing papers. So if you go to the website of this workshop and you click the papers tab, and you can see that we have 3 archival long papers and 11 short paper presentations. So for each paper, you can click, so you can see the authors and also the title, and also you can see the abstract of this paper. And you can click this button to check the PDF, like the full paper, if you want to read the more technical details.
Kai-Chun?
And also,
I think it would be helpful if you can briefly mention how to join the Gatherly. I think that would be helpful.
Yeah, I will do that later. Yeah, yes, thanks. Yeah, so and you can also watch the video presentation prepared by the authors that will be hosted on the YouTube. So move on to the Gatherly. So this is the link that you log into the Gatherly. And so there is also a QR code that you can scan to access to the Gatherly. And yeah, after set up your names, the audio and video settings, so you will be hopped into this lobby UI. And so this is also my first time using Gatherly, to be honest. But yeah, I think it's pretty easy to use. That so right now I'm in the lobby. So on the right top corner, so this is a very small map. And if you navigate yourself to the elevators, then you can see that in the elevator you can pick which floor you want to go. And there are 4 workshops, and you can pick the structural and compositional learning on 3D data, and click it. And you will be popped into here. And I'm already seeing one of the paper author is standing in front of his paper. So there will be 14 papers, so that you just use the ID that is assigned in this web page. So it's from 1 to 14, and try to find the paper authors at front of the paper poster of that ID. And then yeah, I think that you can like enable your video and audio, and you can just freely chat with the paper authors and for more discussion. So please join the poster section, and this will last for 30 minutes, and we have another section in the afternoon. And also, if you look forward to more talks, please come back at 12:30 at EDT. And now let's talk to the paper authors together. Thank you.
Hi, Leo. Okay, hello everyone. I am Min Hyuk-sung, hosting this third session of our workshop on the structure and the compositional learning on this radiator. And we are going to start this third session in a couple of minutes after we have some older people in this Zoom session. Hi, Leo. Would you test the screen sharing and see how the sharing works?
Yeah, let me try. Hold on. Can you see my screen?
Yeah, it works.
And also the cursor?
Yes, it works. Yep. Okay. Do you also have any videos in the slides? So maybe it might be good to.
Pardon?
Do you also have any videos in the slides? It might be also.
There are some videos, yes.
Yeah, because there is the option of like optimizing the screen sharing for the videos. So it might be so good to test the option.
How do I do that?
In the screen sharing, there might be the click button at the bottom, like optimizing.
I guess. Hold on. Okay. Okay, I clicked that.
Yeah, I think it looks okay.
All my, I don't see anybody else. I guess maybe it's trying to minimize bandwidth and so on.
Yeah, I guess everyone just like turned off their cameras. Yeah.
Okay.
Yeah, so I'm going to start this session with some very short introduction while sharing my slides. So okay. I will switch to my screen.
Yeah.
Thanks. Yeah, I think now we are ready to go to this third session. So welcome everyone back to the third session of our workshop on the structural and the compositional learning on this radiator. And I am Min Hyuk-sung, hosting this session with Kai-chun. And in this session, we are going to discuss some of the structural representations for the 3D shapes. So yeah, this is our third time for these sessions. Yeah, so basically, when we talk about the 3D data describing some objects, one of the major differences with the other types of the data would be that the fact that the 3D data basically can describe the objects as they are present in the actual space. So which means that in this 3D representation, we can also easily encode some sort of the structural informations that can be observed from some of the actual objects, especially for the human-made objects. We can easily see some like structures like the symmetries and also some compositional structures that we have also discussed in the first session, and also some parametric forms of each of the part, and also the relationships across the parts. So for the 3D shapes, basically we can consider representing the shape not just with some sort of the set of the points or the triangles in a mesh, but with some sort of the high-level entities that can explicitly represent all this structure. And also such structure is also present not only for the human-made objects, but also in some like deformable shapes, such as the human bodies. And this structure can be also encoded into a skeleton, joints, or some deformation ways there. And as you know, like such structural representation with 3D shapes have been used in the many perception tasks in the computer vision for like long time after the idea of the like some generalized cylinders and the geons were introduced back in the 1970s and 1980s. And also on the other hand, obviously like such the structural representations have been widely used in many CAD and the graphics applications as well in the also in the some manufacturing systems. So basically in this session, we are going to discuss some different kinds of these structural representations for these 3D shapes and how they can be predicted and also inferred from the raw geometry information. Also, what are the pros and the cons of the different representations and how we can also leverage such structural representations in the many downstream the applications. So we are going to have the two keynote talks by Rio Gibas and also Richard Zhang. And also after that, we are going to have the two spotlight talks from the Gopal and the Jason. So Leo will give the first talk. And let me briefly introduce the first speaker. And while I'm introducing Leo, I guess Leo can first share your slide. Yeah. So yeah, Leo is a professor at Stanford in the computer science department and also by courtesy in the electrical engineering department. And so far, Leo had worked at the Jukes Park and the CSLC and also MIT, and also had affiliated at the National University of Singapore, ETH and University of the Athens, Google Research and Hong Kong University of the Science and Technology, and the Tsinghua Berkeley Shenzhen Institute, and also Facebook AI Research. And at Stanford, Leo is also a member of the past and also the past acting director of the Stanford the Artificial Intelligence Laboratory, and also the member of the Institute for the Computational and the Mathematical Engineering, and also the BioX program. And Leo has been elected to the US the National Academy of the Engineering, and also the American Academy of the Arts and the Sciences. And also he's the ASM Fellow and IEEE Fellow, and also the winner of the ASM, the Alan Newell Award, and also the ICCB, the Helmholtz Prize. And Leo is also a recent recipient of the DoD, the Vannevar Bush Faculty Fellowship, and also the Hans Fischer, the Senior Fellowship from the TUM. And Leo will talk about the 3D structure extraction and degeneration.
Okay, can you see my slides and the cursor okay?
Yep.
Okay, so let me start by thanking Minhyuk and Kaichun and all the organizers for the invitation to this very timely workshop on structural and compositional learning for 3D data. And as my title says, I'm going to talk about some research directions on 3D structure, extraction, and generation, mostly covering past work, but also suggesting some new directions for research. So I will, let's see what's going on. Why aren't my slides advancing? Well, it's kind of strange. They're advancing on the other screen, but not the one that I'm seeing, which is a problem. Can I stop for a moment and start again?
Yeah.
Try to fix this, I'm sorry. Let me see what's going on here. Can you see my screen now?
Yes, now it works. Yep.
So I hope it works now. Let's see. Okay, yeah. So I'll cover a number of topics, primarily focused on, as Minhyuk mentioned, symmetries and part compositions of 3D shapes. Specifically, it'll be symmetries and regularities, shape completion, part assembly, data that we can use for this purpose from 3D repositories, structure generation, and variation generation. And really what this is to highlight the work of 4 of my students over 4 generations, starting with Niloy Mitra, and then Hao Su, and then Min-hyuk himself, and also Kai-chun. And of these 4, 3 are organizers of this workshop, and 1 is an invited speaker as well. So let me start with symmetries and regularities. This is a very classical topic, and this work is a little bit old. It's before deep nets, but I think it's still highly relevant. And perhaps all these ideas can be revisited now with the better tools that we have at our disposal. Symmetry and regularity is extremely common in nature, in both man-made and natural objects. It's of course related to our perception of beauty, but more generally, it's interesting to consider what in physics, in biology, in economics leads to symmetry being so common. I will not have this discussion now. Let me just finish the slide by saying what Alan Perlis said, that symmetry is a complexity reducing concept. It sort of eases our understanding of the world. And this complexity reduction you can see in this little animation, which somehow I cannot play now. I don't know why. I don't see the, maybe it has to do with the setting I selected. Sorry, I don't know. This shows this, maybe I can do it from there. No. Folks, I don't know what's going on, and I don't want to interrupt and start again. So let me skip this slide. The next slide has a little bit of a shorter version of this. Here you can see what's going on. This is the Chamfort Castle in France, and it has a lot of symmetries and regularities. So in the end, essentially, we can reproduce the entire geometry of the castle by storing only something like 14% of the original geometry. And note that this is not lossy compression, this is exact reconstruction, and it's a compressed form that is in the original format, namely this is also 3D geometry, so one can operate on the compressed version with the very same tools you would have used in the original. The pipeline that does this compression is, I think by now very, very standard, very classical, based on voting and ransack ideas, where we take an input model, we generate a sampling of the model by points on its surface, then we compute certain signatures, local descriptors of these points, and in those days, those were design descriptors by us, and then we take, say, pairs of points and try to connect them via some symmetry, and symmetries tend to be low-dimensional transformations of space, so they can be parameterized in a low-dimensional space. So each such possible symmetry becomes a vote in this symmetry space, and then we look for prominent peaks in the space of symmetries, trying to extract what are the main symmetries of the object of interest. And all this has to be done with the consideration that even if the object itself is perfectly symmetric, a sampling of it need not be so. So one has to be able to deal with uncertainty in the symmetry. The basic notion is extremely simple. Say this in the plane for this reflectional symmetry, these 2 points suggest an axis. The axis is a line, can be parameterized with 2 parameters like an offset and an angle in a transformation space, which here is 2D. So we have many pairs of points giving many votes in this transform space. And then we look at this distribution, and we are trying to find the prominent peaks in this distribution, where the height of this cluster indicates the amount of the symmetry present, how many pairs of points led to the symmetry, and the width indicates how approximate the symmetry is. So we do some mean shift clustering to essentially sharpen and isolate the peaks so we can extract them. So if you look at this model of the Sydney Opera House, you can see there is several peaks in the distribution, and the prominent peaks are this 4, 5, and 6. These are the large scale symmetries, but there are also a number of smaller symmetries. And in fact, if we had allowed scaling, there would be also scaling symmetries that you see here. And again, the clusters give you not just the symmetry, but the breadth of the cluster gives you a notion of how sharp or approximate the symmetry is how far you are away from a perfect symmetry. This notion of imperfection of symmetries is interesting because it can be used to take shapes that are slightly non-symmetric and symmetrize them, put them in a more canonical pose. This is an interesting optimization problem because, of course, we are manipulating 3D geometry, but the objective that we are minimizing is in a transform space different from 3D. So we have to have this kind of back and forth communication between these two spaces. It's also interesting because not all the symmetries present can be optimized at once. There can be conflict. Some symmetries may oppose other symmetries, so one has to decide if one will satisfy them all in a least square sense, or whether one will abandon some symmetries completely with the aim of completely satisfying others. Then in addition to symmetries, we can have symmetries of symmetries, that is repetitions. For example, there's a translational regular pattern, scaling pattern, a rotational pattern. This can be 1D or 2D. And these are very common also in man-made and natural objects. For example, you can see these kind of window patterns in buildings, often forming on grids. Detecting this kind of second-order symmetries can be quite challenging because we don't know in advance either the pattern of the repetition or the repeating element. We have to estimate both. So it's a joint, discrete, continuous optimization in the presence of clutter and outliers. So again, I will not go into any details, but again, we try to map the geometry into a low-dimensional transform space and look for structure in that space, which in this case turns out to be your grids. So we are somehow trying to fit grids in transform space. We're given some incomplete grid and with noise points, and we're trying to find where is the grid. This is the model estimation part that will give us the regular structures. So in this building that I was showing earlier, we can detect, for example, these two window patterns, even though, of course, there is noise, even though there is missing data because of the shadow cast by this column. If we go back to our chamfer castle, now we can see a lot more low-level symmetries and repetitions that we couldn't see directly before because they were too small. And if we look at this, for example, Colosseum-like structure, we can see it is made of multiple repeating elements through a rotational symmetry. And part of what we want in this method is the ability to capture the structure, even though there is noise and missing data. And here you can see that some of the elements can be captured, even with 60%, I mean, with 40% of the data are missing. But as we sparsify the data, then of course we miss some of the repeating elements. We can also have scale changes as shown in this Nautilus that involves a symmetry, a similarity transform. We can use it to complete the Nautilus. And this brings me to my next topic, which is shape completion, for which symmetry is a very important prior because parts of shapes can be used to predict other parts of shapes. So the goal here is, given a partial point cloud of a shape, we want to be able to predict the full shape. And the idea behind this work was to combine class priors and part structure and the cell structure, the symmetry of the shape. And the challenge compared to what I was doing before is now the symmetry structure has to be predicted from a partial shape. So you don't have all of the points to predict the symmetry. You must predict them from only a part of the shape. And here, of course, we'll bring class priors and training data that will help in this task to predict both the compositional part structure and the presence of symmetries. So this work, a key contribution was the learning of essentially how parts relate to other parts, who is next to whom, and who is symmetric to whom, and the relative variations between them in terms of pose and size and so on. So basically, there is a training part where we're given a collection of 3D models with part annotations that have to be consistent, and we learn this probabilistic shape model. And then at inference time, this gets used to take a partial scan and complete it both at the point sense, but also at the part sense, being able to add parts that are completely missing. So at inference time, there is this pipeline that I will not go through any detail, but basically it involves, assigning labels to the points, feeding part structures to the points, optimizing the points of the parts, predicting possible new parts, and then getting the final result. And this has optimization criteria both at the point level and at the part level. So you can see here that you can take this partial chair and complete it like I show here, where essentially part of the completion is filling in the seat and part of it is coming from filling in the leg. And here the leg filling comes from the symmetry completion and the seat filling comes from the prior. So in more detail, you can see this here. Here is the input, here is the final. If you complete this only using symmetry, you will get the other arm, but you will not fill in the seat completely. If you complete using only priors, you will get some kind of incorrect completion for the arms, but you will fill in the seat. And if you do both, you get something that is better and closer to the original. And another example. Is here where you have this aeroplane, and again, if you use only symmetry because you see missing parts from both wings, in the symmetry only completion, this will not be there, they will be missing. If you complete only with the class prior, you will fill those in, but the completion for the tail will be wrong, and you can do better when you have both together. This was so far a combination of discriminative and generative, because you have to understand the partial point cloud and then generate missing parts. In the next vignette, I want to go into a generative model based on parts, where essentially you create shapes by just combining parts that may come from other shapes. So again, there's a pipeline of assembling parts together, and this table is composed, is generated by combining parts that come from many different shapes you may have in a database. And this can be used to both to interactive design or automatic shape synthesis by just putting parts together that fit each other. So the interesting work here was to try to use only this mid-level information about parts and reuse the geometry of the parts to understand how to fit them together. And while there had been works like this before that do shape generation by adding parts, they required consistent annotations and consistent segmentations to be able to use parts. And part of our challenge here was the fact that maybe, the databases back then that were consistently annotated were very small, while say something like ShapeNet had many more models, but it was inconsistent. And yet most models that we scrape from the wild do have some structure. They do come as kind of scene graphs of parts. So they have natural part segmentations, but the challenge is that these part segmentations aren't consistent, and often they are not labeled. And even if we had labels, the labels might be consistent, might be inconsistent. So here we wanted to predict complementary shape parts using only geometric information. This is this complement me system that allows you to build shapes part by part, putting them together. And the question is, how do we discover parts that fit a given partial shape? And the idea was to create an embedding space where somehow the partial shape and the part that can complement it come together. And so the notion again is that for all the parts, you embed them into the space, and then you query the space with the partial assembly to get the result that you want. But there's a difficulty here, because if you think about, say, the seat, for a chair, this seat can be complemented by both the base shown there and the back shown there. So presumably, because these both complement the seat, they should be mapped near each other in the latent space. On the other hand, if you take this partial shape, then the back still complements it, but the seat, of course, does not. So according to this query, they should not be in the same place. So how to deal with this? The idea was to embed the partial assembly not in a single location, but in a multimodal space. So we can get multiple parts together to generate a multimodal distribution, a Gaussian mixture of modes. And so we trained a neural network that takes a partial assembly and predicts this Gaussian mixture, so that when you have positive examples, then these are highly likely, and when you have negative examples, these are much less likely. And in addition to predicting what parts we can use, we also have to have another network that helps us place these parts in the right place, and this is the placement network. So this shows an animation of constructing different objects by just picking parts and putting them together. It is twice real time, but you can see that this is still a very fast process. Also, this can be used for automated shape synthesis, where you simply keep adding parts that fit together until you complete the shape. And notice that all these parts come from different shapes in the database. It's another example of building a boat by combining parts, building a table by combining parts. Again, from different places and finding sort of new placements for the parts. One can also do automated synthesis where you generate multiple variations starting from a given part. That's something I'll come back to in a bit. And finally, what's interesting here is that the embedding that you learn for parts is kind of not just geometric, but also semantic. You see, if you look, say, at the legs of this table, near it are other leg structures. Even though geometrically they're very different, semantically they're near this because they can be used to complete the same type of partial assembly. So all these leg structures, all the sails can come together in the respective embedding spaces. Yeah. So essentially, we are discovering semantic relationships among the parts. We were doing this because we didn't have properly annotated data. So essentially, at the same time as it was going on, we tried to take ShapeNet and add that means you already covered, so I will not go much more into it, but get fine-grained part annotations, essentially for a subset of ShapeNet, get very detailed annotations where a keyboard, as shown here, every key is a different part. In this trash can, every slot is a different part. And to do so consistently across different shapes by building these curated hierarchies, we can accommodate variability so that, for example, this table lamp and this ceiling lamp, even though they have very different structure, they can be embedded into the same overall hierarchy by using the notion of end-or graphs. So having these consistent hierarchies can make a big difference when it comes to training algorithms that find part structures. And of course, parts are related to functionality, and we were interested in small parts, in part because humans typically interact with objects through buttons, levers, and so on, small parts. And so we've also been studying articulations and how parts can move with the goal of understanding interactions between humans and objects. And I'll come back to this at the end. But having this part structure can be a big help in geometry generation. As you know, my group has done a lot of work on point cloud geometry, but it's a lot more interesting when you have structure. So now you have a chair that corresponds to a hierarchy of parts. And of course, because you have this consistent hierarchies, if you decompose different chairs, you will get consistent decompositions. And what's important here is that beyond these vertical links of kind of super part to part, you also have horizontal links that relate geometry at the same level, either through symmetry or through adjacency. There's many kinds of relationships that are possible. So essentially, the representation here becomes a hierarchy of graphs, where at each level we have a graph that relates the parts or the part structures that are present at that level, as you see here. And again, I will not go into any detail, but the notion in StructureNet is that we build hierarchical graph encoder for this kind of graph structures. So essentially, so in the end, we encode subgraphs into supergraphs and so on until we get a single code for the whole hierarchy. And again, let me skip the detail. And then we can decode this back into the geometry and the hierarchy by graph decoder. So once we have this, now we can have essentially a VAE that reconstructs shapes, trying to preserve both the geometry and the geometry loss, say chamfer distance between the point clouds, but also a structure loss on the hierarchical structures. And from this VAE, we can also do generation by sampling the distribution to generate novel objects with structure. And this shows some of the generations, both at the pure structure level and at the point cloud level. And here is another example of that. And you can see that these are generated shapes, and these are the closest examples that were in the training set. And you can see they are not that similar. So there's definitely innovation in the generation. Besides generation, of course, another interesting thing to do is interpolation between shapes in the latent space. And this shows some examples of interpolations at the part level or the point cloud level. And this definitely helps, because if you just interpolate purely at the point cloud level between these two chairs, in the middle you are getting pretty fuzzy point cloud with all points flying all over the place. But if you have the structure there to guide you, you can do better. Now, clearly, this captures the structure of the shapes, but not the geometry in great detail. And we had also some work that tries to essentially have two hierarchies, a hierarchy based on structure and a hierarchy based on the geometry, where the geometry is represented by mesh deformation, so one can get much more exact representation. And then there are these two parallel hierarchies, one on the structure level, one on the geometry level, that talk to each other. So that essentially the structure conditions the geometry and vice versa. And this lets us generate now essentially meshes that have interesting structure and geometry, that include some nice details like knobs and wheels in the geometry. And one can now vary separately the structure and the geometry. So here we can fix the structure and keep and vary the geometry. Here we fix the geometry, but vary the structure. So one can get at least a partial disentanglement of the two. I want to again point out that the geometry alone is often not enough. There's this interesting website, The Uncomfortable, that gives you shapes that look real, but actually they cannot be, because essentially they don't satisfy their functions. And so getting to function is one of the topics for future research that I would like to come back to. The last topic I want to cover is the generation of shapes, not ab initio, but as variations of given shapes. And I think that's important, because generating detailed geometry is quite complicated. And if we have nice CAD models, we should be able to use them. On the other hand, generating semantically plausible variations is definitely not trivial. I think also we can try to use this variation ability to improve learning pipelines, because we can put the synthesis directly into the training, so that essentially losses propagate back into the synthesizer to generate examples that help the learning algorithm learn. For example, if you have a hard time learning the concept of a rocking shape, perhaps you can generate examples like these that are near the boundary of non-rocking and rocking to help the algorithm understand the difference. This variation generation is essentially sort of modeling the tangent space of a point in the shape space. And it's interesting because, you know, if say you have a car or a bicycle, of course you can imagine stretching it in, say, from front to back. On the other hand, as you do the stretching, the wheels have to remain circular, and these kinds of constraints have to be learned from data. We also want to learn ways to modify shapes that are consistent across different shapes. So for example, this elongation of legs vector should have a consistent action on different shapes. And unfortunately, autoencoders trained with reconstruction laws often don't give consistency when it comes to applying certain motion vectors in the latent space. So here we wanted to transfer deformations across related shapes, but without having correspondences. And so the key notion somehow was to define a set of actions that can be composed and which can be consistent across shapes. And again, I will not go so much into details about this, but the main notion was to embed shapes in a latent space, take the vector between them, but then map back to the real space through another network that is specific to the source. Essentially, this network interprets the shape difference in a way that is specific to the source. And this is necessary because, you know, the sort of Euclidean space is very homogeneous. You can transfer a vector anywhere. But in these latent spaces of shapes, that's not true. I mean, for example, if you say take a chair and add arms to it, if you transfer this vector to a chair that already has arms, this is meaningless. So you have to be able to decode the shape difference in light of the specific shape that you are modifying. So in this deformed sig network, there were essentially two networks. There's the encoding network that maps shapes into latent space, so we can compute the vector between them, the difference. But then there's this other network, F, that translates this difference back into real space, but it's specific to the source shape. And what happens here is that consistency just emerges. Essentially, you're learning a dictionary of deformations that can be applied to each shape. And it so turns out that the same columns of this dictionary across different shapes give you semantically consistent deformations. You can see here a number of examples of that. It can also be used to edit shapes and then transfer those edits consistently to other shapes. So here, for example, you take this chair, you raise this armrest, you project the chair back into the shape space, and you get this kind of chair with raised arms. But then this vector can be transferred to different chairs with a consistent meaning. Okay, I'm running out of time. So as you can see, this is an area with many, many open questions. Let me finish by just mentioning 4 that are of interest to me and my group. One is how to learn shape variations from images. That's important because we have many more images than we have 3D models. So how can we understand how a shape can vary based on images of shapes from the same class? How can we model not just shapes that are rigid, but more complex motions like articulations, as I mentioned earlier. And ultimately, this is related to understanding shape function, namely looking at this, say, cabinet and understanding not just that it has drawers that can open and close, but sort of where do we have to act on the shape and how to open the drawer or to close the drawer. And finally, and there's other talks in this workshop that relate to this, I think that the language can be a big help in understanding the structure of shapes, and I think this can be exploited much more. And I think also the speaker after me, how John has done lots of work in the same area that relates to functionality. So I hope we will hear more about that from Hao. Okay, thank you very much. And I'm happy to take some questions.
Okay, yeah, thank you for the great talk and great summary of like lots of the work with like the learning the structures from the 3D data that have to be done more than a decade. So that's a really nice summary. So, and for the audience, if you have any questions, please post the questions on the chat so that then I will go over these things. Yeah, there's one question from the Niloi. Any thoughts about, so Niloi was basically asking about like any thoughts about like how the joint embedding of the images or the text as in the clip can help with the functionality and or the deformation priors?
Well, I mean, I think there's been a lot of work, like all the current work on nerves that focuses on neural representations for essentially for appearance and maybe semantic segmentation. But I think there can be also to the neural representations focused on functionality. So you're trying to learn what semantic operations does the shape support. I think in my mind, the big open issue here is how do you supervise this? That is, in nerves, we get supervision from other views, and these are cheap to get. So we have lots of supervisory data. But when a model function, it's not completely obvious how to properly supervise that and from what kind of data. So I'd be happy to hear more opinions about that at some point.
Yeah, there is also another question about like measuring the distances. Like, so between the two cases, like measuring the distances based on like view-based metrics or 3D-based metrics, which one would be working better in the many cases?
Sorry, between 3D metrics and what's
the view-based the distance metrics? I guess this is the case of like measuring the distance in the 2D some project of the views.
Well, it seems to me that the 3D, I mean, well, it may depend on the application, right? I mean, if the goal is to do view synthesis, maybe a view-based distance makes a lot of sense. If the goal is to do robotics and manipulation, where you need to know the real 3D structure of the shape, 3D makes sense. So I'm not sure if there's a universal, the question of what is the proper distance between two geometries, I think cannot be separated from what is the use that you're going to make of this distance. So there can be more appearance-based metrics and more, 3D-based metrics depending on the application that you have.
Yeah, actually, we have like 1 minute for the Q&A, but actually, I have like quick question actually following the first question. So, because I also feel like there are kind of two sort of like very different directions in terms of like learning some sort of the 3D shapes. Like one would be like learning this kind of some explicit structures, not just kind of like reconstructing shapes into the like points or the triangles, but into even some more like some into some high level some entities that can really encode all these structures, like some primitives or some part level structures, symmetries. But also the other extreme would be like learning the 3D shape into some implicit function, like in a way that even the humans can understand. But somehow the neural net is kind of like learning the nerve kind of the representations, like even like rendering these 3D shapes in a way that the neural net can only see the latent cause. So I feel like these two are kind of very two extreme ways, like in very different ways of like somehow learning some 3D shapes from some other kind of the domain of the data. And I'm basically curious like how we can somehow So how you basically view like all these kind of the very different directions of the research, and how we can also think about like combining these the ideas, and how we can also leverage all these things in the future research.
Yeah, I think that's a very good question, Mihyuk. I mean, I think for any, right, I mean, it seems that it may well be possible to have sort of neural representations of 3D that are not at all explicit, but still can be queried in ways that allow us to do various tasks with them. I mean, it's also very interesting to think of hybrid things that are partially explicit and partially implicit. I mean, there have been several such efforts, mostly on the appearance front, like deep voxels and so on. But one can think of many different types of queries that you want to make. You know, in the old, I mean, in the CAD community, there is this term, geometry interrogation. When I ask certain questions, I get answers about what's there. And as long as I can answer my questions, I can accomplish my task. So what I care is getting the answers, not having a mesh or a point cloud or whatever. And so in terms of getting answers like that, how to best combine explicit and implicit is a very interesting problem.
Yeah, thank you for the great answer. Yeah. So yeah, we are running out of time, so I guess we need to move on to the second talk. Yeah, thank you, Leo, for the great talk.
Thank you.
Yeah, so we're gonna have the second talk by Richard Zhang. Richard, would you please try to share your screen for now so that we can see? Richard, are you going to give the talk? You know,
I'm actually gonna play a pre-recorded video, so I'm just gonna get it ready.
I see. Cool. Okay. Yeah. Thanks. So yeah, I'll briefly introduce our speaker. So Richard is a professor at the Simon Fraser University in the School of the Computer Science, and Richard was a editor-in-chief of the Computer Graphics Forum in 2017, and also associate editor of several other journals. And he has served on the program committee, so all the major computer graphics conferences, including SIGGRAPH Asia, Eurographics, and SGB, and also many others. And among them, he was the course chair at the SIGGRAPH Asia 2014, a paper co-chair at SGP in 2013, and also Graphics Interface 2015, and also CGI 2018. And he has also received many awards, including a NSERC, the Discovery, the Accelerator Supplement Award in 2014, and also Best Paper Awards at the SGP 2008, and also CAD Graphics in 2017, and also Best Student Paper Award at the CPaper 2020 last year, and also a Faculty of the Applied Sciences Research Excellence Award at SFU in 2014, and also a National Science Foundation of the China Overseas Scholars Collaborative Research Award in 2015, and also the SFU Dean of the Graduate Studies Awards for the Excellence in the Leadership in 2016. And Richard is also a IEEE, the senior member. And Richard will give the talk about the unsupervised learning on the 3D shape structures, and he will just play the recorded video for the talk.
Can you hear me?
Yep.
Yeah, thank you very much, Mia, for the kind introduction. So I will play a pre-recorded video. One of the reasons was that this actually have very strong winds here in Vancouver, and in the past, such strong winds actually caused power failure. So I wanted to make sure that everything is going to go over through smoothly, and also I want to make sure that I don't go over time. I'm here, so I will play the video, and as you can see, there are quite a few key terms that from Leo's talk that are going to reappear in my talk. So it's really a very nice follow-up from his great presentation. So I'll be here, and then I'd be very happy to answer questions after the talk. I think it's 31 minutes. Let me do that. Hello, everyone. Before starting my talk, I first like to thank the organizers for inviting me and for initiating such a fantastic workshop. The topic of the workshop is very dear to my heart. Today, my talk is going to be about unsupervised learning of 3D shape structures. I want to start by asking you to think about the major attributes of 3D objects and how predictable they are if you know the object's class. For example, let's talk about chairs. The reason that I care about predictability is because most of the learning tasks that we study today are about predicting things.
And I believe that the more predictable something is, the easier it is to learn it. Now let's go back to these chairs. On the left, you see these silhouette of chairs, and on the right, you have a photo of some real world chairs. Do you think the shapes of these chairs are predictable? How about their topology? Of course, in terms of the holes of the shapes. How about color, texture, or material? Right? Now, if you look at this picture here, again, a photograph of some real world chairs, maybe some designer chairs, perhaps none of these attributes appear to be that predictable. Is this really a chair? What do you think? Now, if you try to compare this chair with known chairs in terms of their shape, perhaps measured using chamfer distance, the most widely used metric for comparing shapes, maybe the answer is going to be yes, but is it really a chair? So what really makes a chair chair? Many of you may already know that this is precisely the title of a CVPR paper from 10 years ago. I won't say too much about what this paper did, but I will extract an important quote from the paper, which is due to Barbara Minsky. The quote says, "There is little we can find in common to all chairs except for their intended purpose, intended use." So I was finally able to track down the source. I turned that to page 123. Aside from that quote, there are so many other remarks that really struck a chord to what I've been thinking about. One particular remark is about the importance of both structural description and functional description. I'm going to come back to this in just a bit. But the main message here is that it seems that there's more predictability in the structures of objects that belong to the same class compared to other attributes such as color, shape, topology, texture, or material. The fact that these shapes belong to the same class is not because they have the same color or texture or material, it's because they share the same functionality. And if you think about functionality, so functionality is characterized by the parts of the objects and their relations. And this is precisely what the part structure or shape structures are. Here you see two examples. On the left, you have a chair which is functional. And on the right, a chair is not functional. Why is that? It's not really because it doesn't have the right parts. It does have a back, a seat, and the legs, but it's not functional because the angles here are wrong. So it's a relation between the parts that makes the chair on the right non-functional. The predictability and the commonality that we have been talking about can indeed facilitate unsupervised learning of shape structures. So let's look at some examples. The first example is unsupervised co-analysis. We call this co-analysis because we're analyzing a set of shapes together. And the assumption here is that this set belong to the same class. There had been a lot of work in computer graphics even before deep learning. And to get a sense of these works, you can refer to this survey from 2013. What is common about most of these methods for unsupervised co-analysis is that you're utilizing this structural consistency with the assumption that the data collection, the shape collection belong to the same class. There is an expected structural consistency. And utilizing the structural consistency, you can perform some kind of an alignment, perhaps in the spatial domain. And this is this early work by Golowinski and Funkhauser on consistent segmentation of 3D models. You could also perform a clustering process, which is what the next example is about. So the problem here is unsupervised co-hierarchical analysis. Right? The goal here is, given a set of shapes, we want to find a unified hierarchical explanation of these shape structures. So one of the main challenges is that there may be a lot of variability in both the geometry and the structure of the set. So here you see this set of vehicles, either with 2 wheels, or it's a tricycle, or it has only a single wheel. So there's a lot of structural variability. Another challenge with studying hierarchies is that if you have a single given shape, there may not be a unique best hierarchy, right? So if you think about chairs again, should you group the seat and the back first, or should you group the seat or the legs first? There's really not a unique answer. So perhaps the best answer really depends on the context. That is what the set of these shape structures are. So in this work, we start with this input set of shapes, right? And then for each shape, we're going to have a set of candidate hierarchies. To be conservative, these hierarchies were simply obtained by random splitting, right? So we're not going to miss any potential hierarchy. And then given this set of candidate hierarchies, we need to select one representative hierarchy per shape, and to ensure that these selected representatives maximize a structural consistency. At the same time, you need to realize that there may be structural variabilities, right? So you actually not group all of them together, but you're going to have different clusters. So each cluster represents one particular structural variability. So we have both a clustering problem, and also there is a selection problem, selecting from the set of candidate hierarchies. So that's why there's a problem which is referred to as cluster and select. But what's important here is that there is an optimization of structural consistency. Again, with the assumption that even though there are these structural variabilities, but at a certain level, so at a higher level of the hierarchy, you have a commonality or structural consistency. Now, fast forward to 2020, we were finally able to come to the shape co-segmentation problem and developing a neural network architecture for this problem. This shape co-segmentation is adaptive. If you see from this example, given the same chair, its segmentation may be different depending on which set of shape it is put into, right? So if the sets change, then the segmentation of the same chair may change. So this was a neural network, was published in CVPR 2020. And the key innovation there was a group consistency loss. So indeed, we explicitly optimize a group consistency loss over a set of test shapes. So for more details, please refer to the paper. So I promised in the abstract of my talk that I am going to review the 3 C's for unsupervised learning of 3D shape structures. So the first C is consistency, or you can say commonality. Actually, both words start with the letter C. So we want to utilize the structural consistency over a set, either implicitly, maybe via some kind of alignment, or explicitly by jointly optimizing a group consistency loss in this latest work. And we consider this structural consistency as a weak prior. It's an assumption, right? Given that the input shape or the training set belong to the same class. So that's an assumption. And with assumption, you have structural consistency, and you can utilize the structural consistency for your problem. Let me remind you, actually, there is another consistency that has been applied prominently for unsupervised learning, and that consistency is cycle consistency. It's, I guess, different from the structural consistency as I just mentioned over a set, but nevertheless, cycle consistency, of course, has played a major role in unsupervised learning, especially for unpaired domain translation. This can trace back to CycleGAN and the DualGAN, both published in SECV. And more recently, we've worked on extending those ideas to unpaired shape transform. So I'm not going to say too much about this particular work, which is called the Logan. But as you can see, the network is able to perform unpaired transform between tables and chairs also between 3D shapes and their cross-sectional profiles, or between chairs that have no armrests and chairs with armrests. Now, aside from this consistency or structural consistency over a set of shapes, what other implications can we draw from this predictability of shape structures? So next, I want to connect predictability with compressibility. So can you compress a random signal or a uniformly distributed information source, right? So I'm pretty sure most of you know that the answer is no. That is because compressibility actually requires some level of predictability. So your data needs to have some predictability or some redundancy for that data to be compressible. By the same token, if you want to review, or let's say you want to learn the data redundancy, and these redundancies actually reflect the structures in the data, then you should really make your representation, the learned representation, compact. A primary example here is autoencoders, which is something that everyone is familiar with. It's one of the perhaps the most applied model for dimensionality reduction. It uses this bottleneck layer here. By restricting the code length here, you're able to learn a compressed representation of your input data. Now, it doesn't have to be autoencoders. So next, I show you a nice example of how this compactness criterion can be used for unsupervised learning of shape structures. But I will start by just quickly go over IMNet. So by now, I guess most people are aware of the recent development of learning neural implicit models. So from CVPR 2019, there was IMNet, there was OCCNet, and there was DeepSDF. So IMNet is a network that learns a mapping from a 3D point XYZ, and it learns the occupancy or inside-outside status with respect to a 3D shape, which is encoded using some encoder. And so given a 3D coordinate and given a shape code and going through a sequence of MLPs, IMNet learns inside outside of the point XYZ with respect to the shape. Now, after IMNet, the first question we actually thought about was whether IMNet can be used to learn shape structures. So this is here the original IMNet, and it is trained using a reconstruction loss with respect to the occupancy. Now, it turns out that all we needed to do was to add a branching layer at the end. So that's really the only change to IMNet. So this branching layer essentially produces these K neurons, where K is something you can determine. It doesn't have to be exactly the number of parts, but we hope that each of these neurons is able to learn to reconstruct one of the parts of this set of shapes. And note that we do the training without using any part labels as supervision. In fact, the loss after this max pooling is exactly the same as IMNet. This is the reconstruction loss, but only that we're adding this branching layer. So this branched IMNet, indeed, the hope is that for each branch to learn to reconstruct a shape part, and it actually did work. And this was called BAENet, and BA stands for branched autoencoder. There are two versions of the network. In the unsupervised version, we repeatedly train the network using a set of unlabeled shapes, no part labels whatsoever, and with only the reconstruction loss, right? And it's able to actually learn different parts in the different branches. I'll explain why on the next slide. And there was another version, which was a one-shot learning version, where we can add just very few labeled shapes, could just be 1, 2, or 3 labeled shapes. And with that, we also added a label reconstruction loss to combine with the reconstruction loss with respect to the occupancy. And here you see on the right results of one-shot learning using BAENet, where you provide one labeled chair, okay, and the network is able to learn a co-segmentation to a very large set of chairs. So why does this work? In fact, the key thing here is that compactness, that we're exploiting the structure of a small implicit field network. Note that this BAENet even has less number of layers compared to IMNet, only has 3 layers. We did try different number of layers. It turns out that 3 layers worked very well, worked the best compared to other choices of number of layers. And we also use few neurons, right? In fact, for the one-shot learning, the number of neurons is actually less compared to the unsupervised version of BAENet. So to look at what this network does a bit more closely, we used some synthetic data sets. So here is a data set which we call elements. So these this data set consists of these patterns, right? You have 3 patterns: a triangle, a diamond, and a cross, and that they're randomly placed on this black background, right? And we used, I think, 4 branches, BAENet, and try to learn to reconstruct these patterns because of the compactness. So with that compactness, you're actually forcing the network to learn a representation that provides consistency, because the most compact representation is actually to reconstruct these parts, right? And at the end, the network is able to reconstruct this element data set. Now we looked things a bit closer. We tried to look into the neuron and the neural activation maps in each of the layers. It looks like in the first layer, the network basically learns these linear gradient fields, as you can see. And then in the next layers, it combines these simple patterns into more complex patterns, eventually learning to reconstruct more complex shapes, more complex arrangement of patterns. So the next idea was simply to try to make this interpretability, because we can actually see what each layer was able to learn. We made this interpretability explicit, right? So, well, it looks like in the BAENet, the first layer learned these linear gradient fields. So why don't we actually make this explicit by making the first layer L1 learn planes, explicit planes, okay? And then next, we're going to combine these planes. They're really half spaces. We're going to combine these half spaces by intersecting them and to come up with convex shapes. And then finally, in the next layer, we're going to merge them. This is really a union operation so that we can get more complex shapes, including concave shapes. So that was our paper from CVPR 2020, which was called BSPNet. Really, the input and output were the same as IMNet, the same reconstruction laws. BSPNet, although it produced meshes at the end, it's really another neural implicit model. What's new was that the shapes are formed using binary space partitioning. This is why it's called the BSPNet, and the planes were defined by the network weights which were learned. So with BSPNet, you can actually easily get structural correspondence between the shapes, okay? Because the planes that were given by the same neurons are naturally correspondent. You can naturally match them together, right? Now, for an application of BSPNet, which was a single view 3D reconstruction given an image. So on the top, you see these images of airplanes, and then it's able to reconstruct 3D shapes from these images. And more than that, if you just give a little bit of a hint, you're able to produce these structured reconstruction. So a little bit of hint is just, you just take one airplane and then you provide semantic labels, which are reflected by these colors, and then all the other 3D models reconstructed from images can copy those semantic labels. And these are the results that we were able to obtain. Okay. And for this single view reconstruction application, the network was trained across, I think, 13 classes of ShapeNet, right? So it's not trained per object category. And later we extended BSPNet to try to get actually more compact representations. So if you recall, in the BSPNet, you have these planes, and then you perform intersections to get convexes, and then you perform union to get potentially concave shapes. Now, what was missing, if you think about this being CSG trees, constructive solid geometry trees, what was missing was the difference operation. So we added a difference operation, actually just one difference operation. And also, we wanted to extend the network to work with CAD shapes, right? Not just the ShapeNet shapes that have clear object categories. So we added, in addition to the planes, quadric surface primitives, right? So, so these primitives are going to be much easier to represent in a more compact way than just having planes as your basic primitives. Okay, so in any case, the goal was to produce more compact CSG trees. Again, we do this all without any ground truth trees to supervise it. So on the right, you see the learned CS trees. On top, this is a CAD model here, and at the bottom here is a model from ShapeNet. So this BSPNet extension was trainable over both ShapeNet across classes and also on the ABC datasets, which has no class labels. So the kind of shapes from ABC are these CAD models like these, like machine parts, right? There's no object label, there's no class labels whatsoever. So this BSPNet extension could be trained over ABC dataset without any class labels. Okay, so the second C is compactness, as you would have guessed, of the network model. And this compactness forces the learning of a best representation. So as we call the so-called Occam's razor, or something similar, which is called MDL, or minimum description length. So in both cases, there's this notion that other things being equal, other factors being equal, the best explanation is the simplest one, right? It's the one that perhaps has the shortest code, right? And these best explanations tend to review the structures in the data because it reviews the redundancy of the data and actually makes the data more compressible. And importantly, compared to the consistency that I mentioned as the first C, compactness is a universal criteria. It is not set or class specific. That is why we're able to train across object classes or even without any class labels, as the case for the ABC dataset. But on the downside, so all the examples that you've seen, and so I can recall all the works that we've done that are related to utilizing compactness. This compactness was baked into the network design. They're not explicitly optimized. For example, I'd love to have a network that is able to produce CSG trees by minimizing the size of the trees. Okay, it's still not very clear how that could be done. Now, the third C is continuity. Right? So this was motivated by this continuity assumption for semi-supervised learning. And on the right, you see an example that on the top, if you have only 2 data points, right, there's 2 circles here, then this would be a reasonable decision boundary. But now, if you have lots of other points, even though they're unlabeled, as the case shown over here, due to the continuity that, assuming that points that are close to each other should be clustered together, should have the same label. So these would be the points here, right? They should be clustered together. And then you have another cluster over here. Then the decision boundary here is actually quite complex, but the decision boundary here is one that is over the low density region, right? So this idea was utilized in one of our earlier works on unsupervised co-segmentation of shapes via descriptor space spectral clustering. So roughly speaking, we start with a set of shapes, and then we do an over-segmentation of each shape to get these patches. And then we'll compute a similarity matrix between these patches, and then we'll perform clustering of these patches in the descriptor space. And after that, we compute a statistical model for each cluster, and then we can segment the shapes. So what's most important and interesting is what's happening in the descriptor space. So here is where the continuity comes in, right? So if you look at this 2 points A and B, okay, so they really correspond to two parts, this one and this one here, which should be clustered together. But in the descriptor space, they are quite distant from each other. In fact, B and C, which do not correspond to the same semantic parts, but they are closer in the descriptor space. However, because of the continuity, just like the example you see over here, that this A and B would be sort of linked together, and they're actually going to be clustered together. And furthermore, by using spectral clustering, this kind of a clustering structure is more pronounced, right, in the spectral domain, as you can see on the right. Now, A and B are actually drawn closer in the spectral domain compared to the distance between B and C, right? The next example utilizing continuity for unsupervised learning is for the unpaired image-to-image transition problem when the two domains have clear structural changes. I call this temporal or transitional continuity. Let's look at this cat. So what dog would look most similar to this cat? So this would be a good answer, but as you can see, even just by focusing on their faces, there are these structural changes, right? The ears are different, and also the shapes of their heads are also different. So if we were to apply these classical techniques, such as cyclogan or discogan, where the translation is done in one step, they could either undershoot or overshoot, right? So cyclogan may produce a dog which doesn't really look like a dog, and discogan may produce a dog which seems irrelevant to the input cat. So our idea is simply to learn a gradual transition. So gradual is synonymous to continuous. So this is actually a more continuous translation between cats and dogs. So after one step, we get this intermediate result, and then I call each one a hop. So after 2 hops, and then 3, and finally after 4 hops, you get your dog. So the key idea here is that because the original task of doing a translation between two domains which have structural changes is challenging, so let's make the task easier by only training the translator to do smaller changes, to just produce as hybrids, right? So the translator doesn't go from cats to dogs directly. It goes from cats to 25% dog and 75% cat, and then 50-50, and then 75-25, and finally going to the domain of dogs. All right, so now let me conclude due to the interest of time. So the first key message was that there seems to be more predictability in shape structures compared to other attributes for shapes such as topology, colors, or texture. And these predictability can facilitate unsupervised learning. So I told you the 3 C's, my 3 C's for unsupervised learning of shape structures, compactness, consistency, and continuity. They're all related in some manner, but then they're all different as well. So I'd say consistency is over a set. You need a set to define consistency, right? Well, compactness is not set or class specific. Compactness is something you say about a model or of a representation. And finally, continuity helps bridge a gap. So this gap makes a problem difficult. The gap could be between data points, or it could be between 2 domains. And without supervision, the problem is difficult because of the gaps, right? And then here's just where the continuity can help by bridging these gaps. Oh, by the way, there are some other concepts and techniques that I've mentioned, which all happen to start with the letter C. Cycle consistency, clustering, co-analysis, and also compressibility. So there seems to be some kind of a magic with the letter C. Okay, now future considerations very quickly. If there are more predictability in shape structures, I would expect similar levels of predictability in part relations, maybe composition rules, and also assembly order, and all function, because they're all related to commonality of functionality affordance. And then there should also be similar levels of predictability in the interactions between agents and objects and in their environments. So then I believe that unsupervised learning of all of these things, parts, relations, interactions, would be possible. And they're worth exploring, certainly. And more interplay between structures and functions. I just keep going back to this book by Marvin Minsky about the functions of structures. And finally, it will be very interesting to think whether compactness can be used as a network loss instead of just something that's baked into network design. With that, I will conclude my talk. These are the main papers that were covered. And I also certainly want to thank my many collaborators.
Yeah, that's it, actually.
Yeah, thank you for the great talk. It was really great summary of the lots of the work of like learning these structures, unsupervised way with the deep insights with also the three keywords with the capital C, like consistency, compactness, and the continuity. And also, I think the ideas about like learning the structures in unsupervised way would be also related to the topics that we are also going to discuss in the next section about the structure discovery. So yeah, I'm going to go over the questions in the Zoom chat. So there's like one question in the chat. Could you extend your continuous transformation idea beyond the discrete steps to actually computing a continuous path through the feature space? And we might define the feature space in terms of some differential equations with the analytic contours.
I think certainly we haven't found a concrete way to do that. Certainly the continuity is supposed to be continuous, right? So when we train these neural networks to perform certain tasks, we have to sort of limit the number of steps. So two other things. So I certainly agree. So it's definitely a direction to explore. Two additional remarks. One is that in this Gunn-Hopper work, the translator is the same. This could change, right? It may be better to have different translators, and each translator is a task to perform a translation for a particular kind of feature. So how to do that is not very clear. Another thing that's really interesting that I didn't get time to talk about is the motivation. Actually, original motivation for this work was not actually unpaired image-to-image translation. Was actually trying to do extrapolation. I'm a sort of big fan of working on creative modeling, trying to go beyond the data distribution, try to generate something which is creative, which is out of distribution. So that's why we thought we need to have a good path, right? So if you have a good path, then extrapolation can follow naturally just by extending that path, right? But accidentally, we found out by finding this good path, which would be a continuous transformation, we actually do better in the much more prominent problem of image-to-image translation. So that sort of is a paper produced by accident. So, but if you have this continuity in your feature space or latent space, you can actually do a lot of things. It should be a very interesting direction.
Yeah, thank you for the answer. And there's also the question from the Leo, which is like asking some comments on the needs or the not of the correspondences for the consistency or the co-analysis.
I'm actually, can you comments on need or not of correspondences for consistent or co-analysis? So I want to make sure that I understand the question. So the consistency can be obtained without having supervision. So for example, the ADA COSAC work, there's no co-segmentation as ground truth to train it, right? it was optimized against the group consistency loss. And if you look at that element data set, also there's no correspondence as supervision. The consistency actually comes from just enforcing this, you can call it like a bottleneck to enforce compactness, right? Because after all, the simplest model, the simplest explanation for those kind of data set is indeed that you have these 3 patterns that are moved around. There's no other better explanation. I'm not sure if this answers your question, Leo.
Yes, I mean, I think the interesting thing is that consistency sort of just emerges because for the network, it's the most efficient way to explain the data.
Yes, absolutely. So first of all, I talk about consistency. It is something you can utilize, right? You can use that as a prior, and you can either do, as I mentioned, you can either optimize it implicitly or explicitly. So compactness may be all you need if I were to steal this maybe overly used term. But the problem with compactness is that it's very much handcrafted, right? So we needed to find out what is the length of the code, right? We had this paper called GRASS. We somehow decided that 80 length 80 vector is good to encode these symmetry hierarchies, right? So why is it 80, not something else? And then for the BAE-net, we just decided that this is a good number of neurons, the number of layers is all kind of a trial and error. So compactness will be more powerful if we have a way to actually optimize it, to define it as a network class. This is something that I think is really, really interesting, but how can you incorporate that into this whole thing, make it differentiable? It's not very clear. So that's, I think, maybe the downside of compactness. But if you are a believer of the minimum description length principle, Occam's razor, I think it could be that compactness is all you need to enforce consistency.
Yeah, thank you for the great answer. Actually, we are slightly running out of time, so we need to move on to the next topic. So yeah, thank you, Richard, for the great talk.
Thank you very much. I'll see you at the panel.
Yeah, thank you. Yes, and we are going to have the 2 spotlight talks. And before we move on to the spotlight talks, I'm going to pass over the mic to the Kai-Chun.
Yeah, thanks, Liu. And also thanks, Liu and Richard for the nice talk. Thanks, Liu, and good night. So it's 2 a.m., very late in Korea, and thanks for hosting this session. Yeah. So the next speaker will be Gopal Sharma. Maybe you can try to start setting up your screen sharing while I introduce you. So Gopal is a PhD student in the computer science department at UMass Amherst. He is advised by Professor Vangelis Kalagiraski and Professor Subrasu Maji. He works on learning interpretable and edible representational shapes using neural networks. I guess Gopal is still trying to share the screen, so we cannot see your screen. It shows that you are still.
I'm not sure why it says your screen sharing is paused.
Yeah, maybe you can try to share again, or.
Yeah, sure. Resume share. Can you see it now?
Yes, it's
okay.
Now.
Okay, so can I start?
Yes, please.
Yeah, thank you. Hello, everyone. I'm Gopal Sharma from UMass Amherst. I will present our work, SparseNet, a parametric surface fitting network for 3D point clouds. This work is done in collaboration with Difan, Subhanshu, Vangelis, Siddharth, and Radomir. So the goal of this work is to parse the input point cloud into parametric surface patches. The collection of surface patches should give good reconstruction for the input point cloud. Furthermore, each surface patch should be easily editable and respect human segmentation priors. Right. So a natural question here is to, why do we need to parse? Well, parsing point cloud into high-level primitives gives us interpretable and editable representation of a shape. They are compact. For example, a sphere can be represented by only 4 parameters, such as center, X, Y, Z, coordinate, and radius. They enable efficient rendering And finally, these surface patches can be used in recognition tasks. So there is a plenty of motivation of doing that. So our work is motivated by availability of large-scale CAD datasets such as ABC and trace parts dataset. They come with rich annotations of parametric surface patches, boundary curves, and all these are really necessary for learning-based approaches to parsing. So in most of the time, the way shapes are acquired are using point clouds, which comes from scanners. So we are interested in parsing point clouds, but point clouds are sparse and noisy. So since we are interested in parsing these point cloud into multiple patches, we need to worry about discrete modalities, such as how many patches do we want, what type of patches. And then there are continuous modalities also, like the parameters of these surface patches, such as scale, orientation, radii, and so on. Then a surface can be approximated by millions of surface patches, right? But we don't want to do that, because users, when they want to edit a surface, they want as minimal number of handles or primitives to edit the shape. So a good algorithm should trade off between compactness and accuracy. So previously in computer graphics, there has been several works that try to parse point cloud into parametric surface patches. However, they produce less expressive representation in comparison to our method. They rely on non-data driven approaches. So they have a hard time learning human segmentation priors, as in how human usually decompose shapes. Furthermore, they also rely on hand-tuned hyperparameters and shape descriptors, which may lead to suboptimal performance. In this work, we mainly focus on 4 geometric primitives: plane, cone, cylinder, and sphere, and along with B-spline surfaces, open and as well as closed. So we mainly focus on, we mainly work with ABC dataset, which consists of a wide variety of CAD models with extensive annotations of parametric patches, and their, their parameters available for supervision. So we start with rendering, sampling points on the surface and adding a little bit noise to simulate a real world scenario. So our approach is basically, it consists of first starting with input point cloud, possibly with normals, and pass it through a decomposition module. And what this decomposition module does is it's basically a network that takes point as input, produces per point embeddings, and then pass it through a differentiable mean shift clustering procedure to basically give us different segments, right? Different color correspond to different segments here. And similarly, we also produce per point primitive types, and combining these two together basically gives us different segments with and their corresponding primitive types, such as B-spline, cylinder, cone, and etc. So note that we do have supervision for these things, like different segment IDs and primitive types. So we can use that to supervise our network. So to decompose a point cloud, basically we use triplet loss, which encourages embeddings belonging to same segment to have similar embeddings and different for different segments. And then we also have categorical cross entropy loss for primitive type prediction. So okay, so first step is done. We started with point cloud, we decomposed it into different segments. Now comes the fitting part, surface fitting. So for each part, each segment that we decomposed, we have a corresponding fitting module. So it could be spline fitting for splines, cones, cylinder, planes, and so on. And we want all these different fitting modules to be differentiable. So in this work specifically, we focus, we introduced this spline fitting module. which is a differentiable neural network. So there are several challenges of in spline fitting. First, there are infinitely many configuration of control point grid, and we also want smallest control point grid for the because they are more efficient and it's easy to use them. Secondly, B-spline surface patches can have variable size control point grid, so which makes it harder for neural network to predict it. So to complicate things further, there could be open as well as closed spline. So we have to take care of all these things. So to basically deal with all these problems, we simplify our spline surfaces. We over parameterize them, and use a special neural network called SplineNet that takes points as input and outputs control point grid. Once we have control point grid, we can basically reconstruct a nice surface like this. So to supervise this SplineNet, we use several losses. First, we supervise it using regression loss at control points. So we want the network to produce correct control points. Second, since we can go from control point grid to the surface using analytic formula, we can define analytic distance between the predicted surface and ground truth surface, right? So that is another loss. Finally, we have a Laplacian loss, which tries to force the local surface properties of the predicted surface to be same as ground truth surface, such as normals and curvature. Okay, so putting it all together, basically, we first train our decomposition module to decompose point cloud into segments. We train our SplineNet to take point clouds and give us splines. And then, since everything is differentiable here, we can train all these things jointly to improve the performance further. Okay, off to the experiment section. So we create non-learning based baselines. First, we see how well nearest neighbor does. And then we have ransack baseline. We also have learning-based baseline, which is SPFN. So in comparison to learning as well as non-learning baselines, our network produces better results in terms of segmentation performance. And further end-to-end training leads to improvement. In terms of reconstruction quality, our approach gives pretty close results to the ground truth while producing variable number of primitives and accurate primitive types. Right. And optimization, post-process optimization is also helpful for producing better results. There are more details, and you can check out the paper for that. Our approach can produce wide variety of segments. A wide variety of good reconstructions. Okay, so that's pretty much about ParseNet, and just looking forward, there has been some really interesting work on primitive instance segmentation for scene level that can work on millions of point clouds. And there is also work SPFN that produces detailed primitive fitting, which is also interesting to see. Finally, once we have reconstructed the point cloud using parametric surface patches, these can be converted into boundary representations, and that can be easily input to 3D softwares. Shapes represented in boundary representation allow downstream shape classification and generation tasks, as is shown in recent papers. However, doing all these things in a completely end-to-end manner, starting from point cloud to generating a program such as extrusion, sketch, is still an open challenge and a good direction to explore. So just to conclude, we propose ParseNet, which is which predicts geometric primitives and surface patches. It gives interpretable and editable representation of a shape. And in the future, it would be interesting to reason about boundary curves and incorporating more primitives to have more expressive representation. Yeah, thank you. I hope I didn't go.
Yeah, thanks, Gopal, for the nice talk. I think we have 2 to 3 minutes for questions from the audience. So while they chat in the question, maybe I will start with several of my questions. So you compared that the primitive fitting performance on shapes and also on scenes. So do you think there are some fundamental difference between your method applying on shapes and on scenes for primitive fitting?
I think so. One of the challenges in scene is just the size of point cloud. So that is one challenge, how to consume that much amount of point cloud. Another problem that I see is that in objects, the capacity of the network to focus on smaller parts is easy to do at object level, but it's really hard to do at scene level. So it makes sense to have a combination of local and global, more like a hierarchical approach that would work better. And I think this primitive net kind of does that. Let me think. I think naive application would be hard. I think more of a hierarchical approach is a way to go.
Okay, thanks. And there's one question from Minhyuk. Would it be also possible to enforce compactness when learning the B-splines, like minimizing the degree and the number of control points of the surface?
Right, so that's a really good question. So the way we approach it, and I didn't describe it here, is that we first over-parameterize the splines. We solve this problem in over-parameterized space. And then we can use this post-process optimization to bring the number of control points down to smaller number of control points, at the same time preserving reconstruction quality. And that can be done using least square formulation. It's really interesting that it works, and it also, like, forcing the network to make forcing these algorithms to produce smaller number of control points also leads to regularization. It smooths out bumps and kinks in the surface. Yeah, thank you. Interesting question.
Yeah, and also one question from Leo. So in the toroidal spline fitting example you showed, how do you regress control points under rotational symmetry ambiguity?
Oh yeah, that's a really good question. I removed the formula here, but the thing is, there are, for open splines, depending on how many control points you have, there are many permutations that are valid. So in this particular setting, there were 80 permutations that were valid. So what I do during training is just iterate over all 80 permutations and select the permutation which gives minimum loss. And for the closed spline, I think there were around 160 permutations. And those permutations can be done easily using some tensor tricks, and finding minimization over all those permutations is also not very time consuming. So you basically choose the one which gives you a minimum loss. Yeah.
I see, that makes sense. Yeah, thanks again, Kopo. And we need to move on to the next speaker, Jason Zhang. Maybe while I introduce you, you can try to set up your screen sharing, Jason. So Jason Zhang is a PhD student at CMU working on single view and multi-view 3D reconstruction. He is advised by Deva Ramanan and Shubham Talsiani. He completed his undergrad degree at UC Berkeley working with Professor Jitendra Malik. Jason has also spent time at FAIR and is supported by an NSF fellowship. Take it, Jason.
Thank you for the introduction. Just to make sure I'm sharing the right thing. Am I sharing the right screen?
Yes. Yes.
Okay, great. So today I'm going to be talking a bit about composing humans and objects in the wild. So in recent years, we've seen tremendous strides in reconstructing both humans and objects, but in almost every case, these estimations are made independently, and it's unclear how we might go about placing them into the same 3D scene when they are in the same image. So given that human behavior is generally goal-directed, being able to properly place humans in the same scene as objects that they're interacting with is important for learning things like affordances, understanding behavior, and generally recovering plausible 3D scenes. So while most works on human mesh estimation generally ignore the scene, I think Prox is actually a really nice, notable exception that does try to place humans into a 3D scene. So given a scanned 3D environment, Prox recovers 3D humans in relation to that scene. And it does so by defining contact regions on the body, which are used to encode proximity between the body and scene, as well as enforcing some volumetric exclusion. And we took a lot of inspiration from some of these ideas. One challenge, though, is that the Prox does require you to have the 3D scenes. And in general, for in the wild data, this is not going to be available. So if we consider, for example, this picture at a park, it's highly unlikely that we'll ever have a dense RGB depth capture of the entire area that we care about. So today I'll be talking a bit about our ECCV paper from last year that tries to tackle this challenging setup of how do you place humans and objects relative to each other for single view images in the wild. And the goal is, given an image of a person interacting with objects, we want to be able to reconstruct both and place them into a cohesive 3D scene. So why is this task so challenging? So let's revisit this picture of a bunch of people enjoying this park. And without understanding how humans interact with objects, one very plausible interpretation might look like this. So even though the sizes of all the objects and people are reasonable, we immediately look at this and we know that this is implausible because people shouldn't actually be floating midair. The challenge, though, is that this interpretation has almost the same 2D projection as the more plausible interpretation at the bottom. And it's obvious for us humans to be able to figure out the difference, but disambiguating between these two interpretations is actually challenging because of the fundamental scale ambiguity when you project from 3D down to 2D. So for example, if you have a small surfboard that's close to the camera and a large surfboard that's further away, they'll end up projecting to the same 2D image. And in fact, there are actually an infinite number of surfboard sizes that would project to the same 2D image. And intuitively, we can actually think of maybe two possible sources of signal that can help resolve this type of ambiguity. So first, we know that the person should actually be interacting with the object. So maybe the surfboard should be near where the person is. And we also have some sense for how big surfboards are normally. So for example, a 2 feet surfboard or a 20 feet surfboard are probably both unrealistic. The issue, however, is that 3D reconstructions in general are estimated in local coordinate systems that do not have metric size. Fortunately, though, the SMPL human mesh model does incorporate a size prior that is in metric units. So if we can place humans and objects in the same global scene, we can actually endow these objects with a metric size by learning the scaling factor that converts from the local coordinate system to metric units, which we call the intrinsic scale. And this would allow us to be able to learn the empirical distribution of objects directly from data. So to do all this, we propose an optimization-based approach that reasons about human-object interaction. So more specifically, given an input image, we first extract 2D bounding boxes, which we feed into a state-of-the-art human pose estimator to get 3D meshes. And we also compute instance segmentations using point rend. And then we fit CAD models to the masks using a differentiable renderer. If you naively place the humans and objects in the same 3D scene, it looks reasonable from a frontal viewpoint, but if you look at it maybe from a top-down viewpoint, you'll see that the humans and objects actually are not interacting properly. So we propose this optimization-based framework where you place the objects into the same 3D scene, and then you can reason about how do you place the humans and objects correctly so that they're interacting the way that you would expect a person to be interacting with a motorcycle or a bicycle. And you can see that from the side view, this looks a little bit more realistic. Okay, so I'm going to start with the part of how do we actually get the 3D object fits to initialize the 3D object poses. So to optimize for the object pose, we're going to take in an input image. We have our predicted instance mask, and we assume that we have access to some kind of exemplar mesh, so some canonical bicycle mesh. And then we use a differentiable renderer that will optimize for the 6-off rotation and translation. And so here's what that optimization process actually looks like. And at the end of optimization, we'll have a 6-off pose that we can use to place the object onto the input image. And so we're not actually necessarily doing 3D reconstruction in that the 3D reconstruction won't necessarily look exactly like the objects, but we instead have like a set of exemplar meshes that correspond to various categories. And then we want to find the right pose as well as maybe the mesh index that we care about, the mesh ID that we care about to fit it to the image. And so to actually do the fitting, we run into some big challenges. So the first is that in general, when you have interactions between objects and other objects or people, there's going to be a lot of occlusions. So for example, in this predicted instance mask here, we see that there are holes in the mask due to the occlusion by the dog. So to address this, we use an occlusion indicator that reasons about where there are occlusions in the image. And then where there are occlusions, we basically just enforce that there should not be any loss. We don't penalize it for making predictions in this area. So now using this occlusion-aware silhouette loss, we're able to compute the pose correctly. So that's it for how do we get the object fits to initialize. Now let's talk about how do we reason about humans and objects jointly. So we propose FOSA, which is perceiving human object spatial arrangements, where given 3D human estimations, as well as 3D object estimations, we want to minimize this loss function with respect to the 6-off pose and the scaling factor for each object and human in the scene. So the loss function consists of the occlusion-aware silhouette loss, some way of figuring out how humans and objects are interacting. We incorporate a scale prior to reason about the distribution of object sizes, as well as some ordinal depth information that can be recovered from the instance segmentations. And then finally, interpenetration loss that penalizes objects and people from colliding. So to model human object interaction, we take some cues from procs, where we label parts of the humans that are likely to be interacting with objects. And then similarly on the objects, we label areas that are likely to be interacted with. So for example, we know that people usually grab baseball bats by the hand. And so we want to bring the hand and the candle closer together. So to identify the human object interaction, we use 3D bounding box IOU. So for example, if we look at this image of these tennis players playing a match, we can see that initially the humans and objects are not properly interacting, but they are close enough where the 3D bounding boxes overlap. We identify this as an interaction, and then we use an optimization that pulls these two, the people and the objects closer together, and we can visualize this from 360 degrees to see that this produces a more plausible looking scene arrangement. But one issue is that in order to actually be able to compute this 3D bounding box IOU, we have to have a reasonable scale initialization. So for example, if I have this person and the surfboard, if the surfboard is initialized to say 2.5 meters, then in 3D space, the bounding boxes will overlap. Whereas if I have a very unreasonable scale initialization, say 10 meters, then the 3D bounding boxes probably won't overlap, and it will be difficult to recognize this as a human object interaction. So to bootstrap this process, we initialize object sizes to be something reasonable using internet search. So for example, baseball bats might typically be 1.1 meters long. But then over the course of optimization, these scales will change. And so here we're visualizing the empirical distribution of object sizes learned by FOSA. And we can actually see that these are pretty reasonable. Like you see that, for instance, that bicycles vary in length from like 0.7 meters to 2.5 meters long, depending on the type of bicycle. And then we can actually compute a new distribution, a new initialization. So here we have actually learned an empirical mean object size using this supervised by human object interactions. Let's look at some qualitative results. So here are some in the wilds reconstructions on the COCO data set on the test set. Here are some more 3D reconstructions with various objects like motorcycles, surfboards, rackets, bicycles. And to evaluate this approach, we use a forced choice evaluation. So here we give users two different options, and we ask, is option A or option B better? So 50% would mean that fossa and the thing that we're comparing to are essentially at chance. So we compare fossa against an independent composition that doesn't reason about human-object interactions, and we find that fossa outperforms it 75% of the time. We also ablate all our loss functions to see that they're important. So if you remove the occlusion-aware silhouette loss, or the occlusion-aware silhouette is very important for initializing the objects. The interaction loss is important for getting humans and objects to be interacting. And then the scale prior and the depth loss help give a small boost. We actually found that the collision loss had a negligible or sometimes even negative effect because it was prone to getting stuck in local minima. Here are a couple more in the wild reconstructions on the COCO dataset. And so, okay, so I think this was an initial first attempt towards getting humans and objects interacting in the wild. And as such, there are still some limitations. So first of all, the interaction types needed to be manually defined. We had to say, like, humans and benches should be interacting in this manner. Ideally, we should be able to learn these types of interactions automatically from data, although this is challenging, especially in the wild. Secondly, the interactions that we're learning are rather coarse. And what I mean by this is we're saying that the hand should be close to the object, but not necessarily the hand should be grasping the object. There's already been some follow-up works that have been trying to address this. So Jia has a paper at ICCV this year on human hand-object interaction from single images. Jana has a new paper on hand and objects from videos. And finally, the exemplar-based 3D reconstruction that we're learning is really exemplar-based. So we're not actually learning an image-specific 3D instance. It's rather just some canonical mesh that we have. We've actually I wanted to plug some new work that we had on recovering shape, texture, and illumination from multiple viewpoints in the wild that tries to address this. And so here we're able to get a very high fidelity 3D reconstruction of the object given just a few images without camera poses. Thank you very much. I'm happy to answer any questions. And the project webpage for the paper for fossa is available at this link. Thank you.
Thanks, Jason. Any questions from the audience? We have 2 to 3 minutes for the question. So let me start with first question. So we tried to invite Jason because we found Jason's work is kind of like in between about 2 sections. One section we are working on the object to object part, and the other section from object to scene. And you are kind of in the middle, like you play with a group of multiple objects, and we think that is a good complement to the workshop. So my question is, how do you think your model will generalize either towards scene level or down towards the object part level? So is the same framework also apply?
Yeah, so I think that's a fantastic question. I think there's fundamentally different, there's slightly different challenges here between being able to reconstruct a scene using object parts and then also being able to learn the parts of the object automatically. So I would say, like, with scene level reconstruction, we have a lot of existing machinery like mask RCNN or like these large scale COCO data sets that can give us supervision, like this here is a bench, this is where the human is, and so on. So I would say that maybe even scene reconstruction might be a little bit easier because you can take advantage of existing supervised approaches. I'd like to think that a lot of these insights can still be generalized to learning object parts, but because it's more challenging to be able to get the parts, like we don't really have good like supervised wheel detector, or like we've moved past a lot of like the traditional like parts-based approaches for object detection. And so now we don't actually have as mature machinery for learning those parts. So I think some of the insights can be generalized. The main issue is that a lot of these approaches will have to be more unsupervised and learn these automatically. Yeah, but that's a great point.
Yeah, thanks for the reply and thanks for the talk.
Yeah.
And I think if no other questions, we need to move on to the last session. And Paul and Songfang, take it.
Yeah, thanks for giving over, Kajun. So I'm going to share my screen and give a small introduction. Okay, great. So welcome everyone to the final session, session 4 of our workshop. So the central theme in this final session is the discovery of structure and compositionality in unstructured data. This will be the last session of our workshop that has keynote talks and spotlight talks. Afterwards, we'll still have a panel discussion and the final poster session, so please stick around if you're interested. So in the previous sessions, we have seen that structure and compositionality is useful in various settings, both for objects and for scenes. But much of the data that we have available in practice is unstructured, so does not have a structural annotation. And usually it's because it's just easier to capture the data that way. So for example, in ImageNet, the objects and scenes that we see in as images do not have a structural annotation. Similar for point clouds and meshes. So we have many data sets with point clouds and meshes that do not have structural annotations. So these cannot be used directly in many of the methods that we heard of in the previous sessions. And implicit functions are also becoming more and more common. For example, distance field, occupancy fields, light fields. And so far, these kinds of implicit representations of shapes do not come with structural annotations either. We know from our everyday experience that when we look at the scene, our visual system automatically discovers a structural representation of the scene for us. So for example, if you look at this image, this natural scene, then it's hard to see the scene as just pure abstract geometry. So usually we automatically perceive objects in this scene, parts of objects, often with some semantic label attached to them, and the relationships between these objects, like repetitions or symmetries. And this structural understanding of a scene is a necessary component for many of our everyday tasks and actions. So the central question in the session is, how can we discover this structural representation from an unstructured data source? There are many different types of structural representations we can discover. So for example, they differ in the types of parts they use. And the part representations can be represented, for example, as cuboids, as superquadrics, and or as more complex parametric primitives, and in the types of relationships they use. So for example, there can be hierarchical relationships between the parts. There can be symmetry relationships and other types of relationships. These methods can also either be supervised or unsupervised, or fall anywhere in between these two extremes in the spectrum. And for example, StructureNet that we saw in the previous session falls more on the supervised side, whereas many of the methods that we're going to hear today in this session are going to fall more on the unsupervised side of the spectrum. And one interesting question to ask for this unsupervised side is how do we specify the desirable properties that these structures should have when we train them without supervision. So the talks in this session are all related to the central topic of structure discovery to various degrees. And similar to other sessions, we'll have 2 30-minute keynote talks and 2 10-minute spotlight talks, and we'll have time for questions after each of them. So without further delays, let's get to the talks. The first speaker is Thomas Fankhauser.
Hi, I'll share my screen here.
Sounds good. So Thomas Fankhauser is the David M. Siegel Professor Emeritus at the Department of Computer Science in Princeton University. He's an ACM Fellow, member of the ACM SIGGRAPH Academy class of 2018, and the recipient of several awards, including the SIGGRAPH Computer Graphics Achievement Award in 2014. And he's well known for his work in shape analysis and will be giving a talk about explicit, implicit representations of shapes. Please take it away.
Okay, can you can see my slides?
Yeah.
Great. Great. Okay, yeah, so I'm going to talk about explicit/implicit representations of 3D shape, which is not the high-level structure that you just described, but is more how can we decompose implicit functions with implicit structures. So as any project or talk, I think you should identify what your goals are. And so in this talk, the goals are to build a 3D shape representation that can represent any shape accurately and concisely, can scale to support any kind of shape, both objects and scenes, and can do the operations you care about efficiently, of course. And we aim to have these 3D shapes in this talk for 3D reconstruction or completion or analysis. Okay, motherhood and apple pie. So for decades, people have used explicit 3D shape representations. As you all know, examples of that would be meshes or point clouds or voxels or things like that, where the shape is represented by a set of geometric elements that cover the surface of the volume. Okay, and those are very general and scalable. So if you have a set of geometric elements, you can make more complex or larger shapes by adding more elements. And you can represent any kind of object with a set of very small elements and get them as accurate as you want at the cost of conciseness. So you have this conciseness accuracy trade-off, and they're not necessarily so compact or efficient at representing things, especially if you have you basically are not able to take advantage of priors or learned common structures in a representation that's just enumerating little tiny geometric elements. So alternatively to explicit representations, there's, as you all know, implicit representations where the shape is defined implicitly through a function that the value of that function defines, say, inside or outside. Examples of that would be some polynomial function like an ellipsoid equation or a sine distance function. And then, of course, more recently, there's been work on using a deep network to represent that implicit function. So the decoder is a network that takes in an XYZ, so that f of XYZ is computed by this network, and then the value of that is interpreted as a shape function. And possibly, optionally, you have a latent code that goes into the network as well. Okay. And so if we look at the properties of these kinds of representations, these implicit representations, they can be very concise, especially the latent code could be just like 1,000 numbers or 256 numbers representing an entire shape. And the decoder could be shared across many different shapes. So you've kind of factored the common parts of the objects in the decoder versus the specific parts in the latent code. So they can be very concise, but in general, they're not accurate, as accurate as explicit representations. Even just autoencoders don't necessarily reproduce the same shape that is their input. And they're not usually general. So, working for a wide, if you train on chairs, you don't get something that can represent airplanes. They're not scalable usually, like the size of the latent node is fixed. And, there's nobody who is using this kind of method to represent an entire city. And they're not so efficient because you have to evaluate a function for every point. But they've been very effective, state of the art at 3D reconstruction from observations like depth images or RGB images, and for 3D completion. So they're very, very promising. And just as an aside, these kinds of networks can be trained either in an encoder decoder setup, where the observation is given to an encoder that produces the latent code, and then you co-train a decoder, or they can be trained in an auto decoder, where the observations are only given, there is no encoder, and the observations are right there in the loss that is training the latent codes and the decoders jointly. The auto decoder setup is advantageous for applications like completion, where the entire shape is not available for the encoder to produce the right latent codes. And so the auto decoders are often very advantageous. Okay, so with that as background, the challenge that I'd like to talk about is how do we use these learned implicit 3D representations that have good properties about leveraging priors and learned structures and things like that, but for highly accurate and detailed reconstructions that can scale to complex scenes and generalize the shapes that were seen during training. And I don't think anybody here thinks that we can just have this simple architecture that learns one decoder for all possible scenes and, you know, all encoded in one latent space. So the question is, how do we do that? And so the approach that I'll talk about, which is not unique to me, is that we'll have hybrid 3D representations, where we'll take explicit representations that enumerate geometric regions or geometric primitives, and then associate latent codes with them, or learn networks with each of them, and decompose shapes into components that each can be represented by an implicit function. This is a rather common approach, but I think it's worthwhile, you know, calling it out explicitly as a good idea. It's a necessary idea. And so the question then is, like, you know, how do we decompose, and then what benefits do we get? The benefits are related to the fact that if we have smaller regions or smaller, simpler components of a whole scene, then the shape space that you need to learn is easier. And therefore you can reproduce more accurate reconstructions given a fixed size encoding, latent vector. If you have simpler shape spaces for each of the components, then the decoder networks are more efficient. If you have scales of your components that are reusable parts, then you get generality. And if you can compose multiple local components into an entire scene, you could represent an entire city. So I think this is just necessarily a good idea. There are many people who have investigated ideas like this. This is 6 out of tens or maybe even 100 different projects that people have combined explicit and implicit representations just in the last year or two. So this idea is not unique to me, but I think it's, again, useful to think about and call out, because we could ask ourselves, which explicit representations are there that would be valuable to think about combining with implicit representation. So as a first approximation, you could take every explicit representation, and for each of the geometric elements, you could assign an implicit function. And so there is as many hybrid mesh methods, trivially, as there are explicit methods. And I'm going to investigate 2 such things that we've published in the last couple of years. The first is quite straightforward, and the second one maybe not so obvious. So I'll start with the first one, local implicit grids. And this is a project that was done by Max Jiang at CVPR 2020. And so the idea is a quite straightforward implementation of this hybrid explicit implicit idea. The idea is that rather than having one latent code for the entire shape or the entire scene, we're going to decompose space into grid cells and represent each of those with a latent vector. And then in this case, there's a shared decoder for all grid cells that are used to reconstruct the shape. So when training, the first thing is to choose a grid size. We try to choose a size that's at a reusable part scale. If it's too small, then it's trivial and there's no real shape space, everything's flat. If it's too big, then it's not going to be generalizable. So we try to pick a human, based on human sizes, a part scale that's generalizable. Of course, during training, we break the world up into grid cells, and we train an inside-outside function based on point samples. We use an IMNet that Richard talked about a couple talks ago for decoding the local regions, and to produce an inside-outside function for each of the grid cells. And then during inference, we evaluate that IMNet at each of the 8 corners of a 3D grid cell, and then interpolate to produce our final function. So the benefits of this are that we get some of these properties that we were looking for. And so in any project, you want to set out what your goals are and evaluate whether you achieve them or not. So in this case, for generality, one of the goals of the representation was we can visualize the learned embedding space of our latent space for these local grid cells and see that there is a mixing of different semantic classes of objects that appear near each other in the class. And then we can do experiments where we, in this case, train only on ShapeNet chairs. So all the training examples were chairs, but then we do autoencoding of other classes like airplanes and cars and things like that as well. And other representations like OCNet or the original ImNet or things like that would only produce things that were in class. You can see that in the ImNet column here. Whereas, of course, we've decomposed things into generalizable parts. And so we don't have that problem. And then we can also do scene reconstruction by breaking up a scene into little grid cells. In this case, we train on ShapeNet parts, ShapeNet little regions, objects, and then test on scenes. And so we can do a reconstruction. It's not perfect, but it's preferable to, like, if you try to do one big decoding of the entire scene. And then if you compare the hybrid implicit explicit to the typical explicit methods like Poisson surface reconstruction, there's benefits there too. And if you measure the difference, the hybrid method is outperforming the explicit, traditional Poisson surface reconstruction on tasks where you start with a very sparse point cloud at different sparsities and then try to do 3D reconstruction. Okay, and then the other last benefit is that it's more efficient. So because the shape space for each of the parts is more, it's simpler and smaller than whole objects or whole scenes, we can use an ImNet that's much less, it's much smaller than the original ImNet. And so ours has 1/16 the number of parameters. So each evaluation takes 1/16 amount of time. Okay, so that was a very straightforward implementation of this idea of having explicit/implicit methods. That was like the first of its kind, really, at that time. But so at ICCV, this conference, we have a paper about multi-resolution implicit functions that are taking the same kind of idea, but it's not explicit. It's not explicit spatial decomposition. It's explicit frequency decomposition. So the idea here is that the decomposition isn't going to be, let's break the world up in different regions of space, but it's going to be, let's break it up into different frequencies and then use implicit functions to describe the residuals in this case at different frequencies. So the decomposition is like a Laplacian pyramid, where at the top level you have a low frequency representation of the global shape, and then at each level you are storing the residual of the implicit function at with respect to the reconstruction from the previous levels. And the advantage of a Laplacian pyramid is that there's strong priors for values being 0 near smooth regions. And so that's a simpler function to learn potentially than learning a full reconstruction at every level. Okay, so yeah, so saying that here there's multiple levels. Here it's just 2 levels are shown, but in general we have more, where the top level has a latent code, and then that feeds into a decoder like I've showed before, and you get back a coarsely detailed implicit function that defines your shape. And then the second level breaks the world up into 8 in 3D, 4 in 2D subregions that are each has a latent code of the same size. And so it's going to be a more detailed representation of the shape, similar decoder, but instead of the function producing the actual implicit function itself, it produces a residual with respect to the previous level or respect to the sum of the previous levels. Going in more detail, it looks more like this, where we have an encoder that produces features that produce these latent codes on each of the grid cells. And then there's a decoder that's learned separately for each level, these gray Ds on the right. And then each of them is producing a residual function within smaller and smaller grid cells, providing more and more detail with respect to the previous levels. One of the tricks in getting this to be useful for applications like completion is to train the system with latent code dropout. You have this tension here of how could you prevent the system from producing zeros at all of the early levels and then producing the full shape function in the last level or something like that. So anyway, we train the system with these dropouts that cause it to learn to encourage the low levels to be able to do completion even when stuff's missing. And then we can deploy the system either as an encoder decoder or an auto decoder, which is an advantage of it. So when testing this compared to previous implicit representations, we find that the auto-encoding accuracy can be much greater than previous methods. That's a little bit about being able to represent these residuals on a regular grid at a fine resolution. So this result actually isn't that surprising, but it's it's encouraging. We find that it generalizes well to other methods. Again, it's leveraging some of the same ideas as the latent implicit grids, in that the residuals that are learned can be at part scale or even smaller, and those are generalizable. And so if the top level can produce a gross approximate shape that is the right thing, then the shape details get filled in a class in a generalizable way. So if it sees a surface that's almost a sharp crease in the low frequency, it knows to try to sharpen that crease in a class independent way. And then it's also more efficient. Of course, this is a multi-resolution method where you can have as many levels as you want. And so the size of the representation, the number of kilobytes in the latent vectors is variable. You can choose wherever you want to be on a spectrum of accuracy versus size. These plots here show the red curves are the spectrum of accuracy, chamfer distance versus size of latent codes. You want to be lower on chamfer distance and higher on F-score. And compared to other methods, they don't have that necessarily, at least aren't tested against a spectrum of results. But anyway, and then the bottom shows examples of what the reconstruction would like if you have different levels in your multi-resolution hierarchy. And you can see that basically the higher levels are filling in more and more and more detail. So one of the applications that you could apply this for is super resolution, where you start with a very coarse grid and then you try to complete it. And again, if you've pre-trained your higher level decoders to fill in details according to priors of what details look like relative to coarser levels, then it can hallucinate details that aren't in the original data to do super resolution, which is kind of cool. And then it also can do completion, because again, since we trained it with this dropout, it learns to complete when the data is not there. And so we get quite good completions for synthetic range scans of ShapeNet models. And these pictures, the green points, which are difficult to see in the left column, are the actual scan. And then the completions comparing of different methods are in gray, and the errors are colored in the third and fifth columns. And we see that the MDIF, which is this multi-resolution deep implicit function, does well for getting the exact shape in the cases where there's not huge errors, but not as well in the cases where the shape is weird and it just gets it wrong completely. So this plot is distance to the ground truth versus what fraction of the predicted points are within that threshold. And so the left part of this is measuring how well you do on cases where you're getting approximately the right answer, like are you getting the details right? And the left part of the right part of the curve is basically how many shapes do you get even close on. And here we're quite a bit off. So in the right here, this is basically saying and the weird shapes, how do you do? Anyway, so we did a user study to kind of better understand these gap completion results by asking people, here's a picture on the left of an observed shape, and then here are two different possible completions of it, or reconstructions of it, where we show it both from the same view and from some opposite view, and ask people to pick which ones they like better. And the results were that 54% preferred the multi-resolution method that I talked about, versus 31% preferred the competition in this case, and 13% couldn't decide. So anyway, so that was encouraging for these depth completion results. So concluding, I just advocating that we should admit / think about the fact that we are generally, when we build 3D shape representations that use implicit functions, the only way to make them scalable, generalizable, so on and so forth, is to combine them with explicit representations. I don't think anybody thinks that we're going to have one big implicit function with no structure to it that's going to represent the entire world. And so it's interesting to think about how do we need to decompose those functions into components that are each represented by implicit functions at most to get the properties that we want. I described two decompositions. One's based on grids, one's based on a multi-resolution Laplacian pyramid, but there are many others. Kyle Genova is going to talk about decomposing into mixtures of Gaussians later in this session. But I think that we really ought to think explicitly about what we're doing there. And of course, the reasons that you would want to do that is to represent shape more accurately and with fewer parameters and more generalizability and higher scale. As far as future directions go, obviously inside-outside functions are not the only possible function you'd want to represent with implicit functions. And so all the same things apply to other implicit functions. Of course, people are mixing explicit and implicit representations for radiance fields. So I'm sure you're all aware of NeRF, which takes in an X by Z and a phi theta and outputs RGB and sigma. And many people have expanded upon NeRF in the last year to use octrees or other representations to store implicit codes that then feed into NeRF and so on and so forth. And so just the same kind of thinking of what are the right explicit representations that can apply, that can work for other implicit functions is, I think, a very active and open research area. The decompositions that I looked at in this talk are purely spatial they're semantic agnostic. They aren't really learning structure in the way that many of the other talks in this session are. So then the question is, how can we combine these hybrid methods where we're actually learning about semantics and temporal effects and spatial relationships and things like that. There is work that's recent. Neural scene graphs for dynamic scenes is an example of learning, an implicit function for each of the semantic objects. But I think that this basically all the talks that are in this workshop could think about how to combine what they're doing with implicit functions to produce shape representations that are, more flexible than with just explicit representations or just implicit. And then another thing that I think is important is thinking about other applications that would benefit from hybrid implicit and explicit representations. Robotics tends to use explicit representations where they'll do 3D reconstruction and then planning of grasping or things like that. But I think it's perfectly reasonable to think about implicit functions that measure affordances or predict physical properties. What is the elasticity of the object at this position? What will happen if I push it here? Those could easily be implicit functions. And then, of course, we have this whole thing about how do you mix explicit and implicit functions. So I'd just like to end there and by thanking the co-authors that went to the papers that are here, and thank you for listening.
Thanks for the nice talk. Maybe while we wait for questions, I have one question myself, and this concerns the maybe the trade-offs that come with implicit representations. For example, it's possible to capture implicit representations directly from some images or directly from real-world sources. Do you think implicit representations have any inherent advantage or disadvantage with respect to being able to discover a structure from them compared to other explicit representations?
I mean, I'm going to give a high-level answer, which is with infinite data and a perfect optimizer, then and a expressive enough function representation, then you can learn any structure through data, and that's always better. And so the reason that we encode structure explicitly or add losses that encourage discovery of structure is because we don't have infinite data, and we don't have infinite data and a perfect optimizer and so on and so forth. So I think there's always this trade-off of you'd like to add as little handcrafted structure encouragement as possible, so that the network can learn the structure that exists in the way it is most useful for its task. But yeah.
Thank you. So I think we have several questions from the audience. So the first question is, would it be possible to learn a part level implicit field similar to voxel local implicit fields?
Would it be possible to learn what?
Learn a part level implicit field. So an implicit field for individual parts. And would that have better generalization capabilities? Or would it have similar ones?
Yeah, I think if you, I think if your decomposition was into semantic parts, then presumably the shape space that you would need to learn for each of those parts is simpler and more consistent, and so that's definitely a good thing. That's similar to the scene graph. I'm sorry, the neural scene graph paper that I described in the second or third to last slide, where you decompose into objects and then you have a simpler shape representation that maybe can be pre-trained and things like that for each of the semantic categories. But then you've mixed discovering that structure and representation together, and which is a good thing to do. Yeah, absolutely.
I think there's a follow-up question from Kai-Jun. If there's a way to automatically discover what these regions should be that are represented by individual implicit functions.
Yeah, yeah, and there is work on this. So again, Kyle Genova is going to give a talk later on about local deep implicit functions. That is at inference time is figuring out where to put mixtures of Gaussians, and each of which is associated with a latent code in exactly the ways that I was describing. And so it's actually decomposing into overlapping local regions at inference time, rather than in predefined decompositions like I described. And he's not the only one. There are people who try to do object discovery and things like that as well. But I think that's a great direction of work.
Ethan Payne was asking, I'm not sure if this is a question or comment, but that chemistry and biology anatomy also would lend themselves to implicit representations.
Yeah, that's true. That's certainly true. I don't know whether I can say anything really smart about that. I mean, if you think about molecules, if you want to, I used to work on predicting structure from 3D, I'm sorry, function from 3D structure in proteins. And what a protein, what determines what a protein does is the properties of the field that it induces on electrostatics, on hydrophobicity, things like that. So you could think about there's actually is a 3D implicit function that's implied by the structure of a protein that is actually directly affecting its function. And so, yeah, it's I think a lot of people think about proteins as surfaces, but they're really, that's, I think, an implicit function through all 3D is actually a very reasonable way to think about proteins, for example. And I'm sure that's true of biology as too, because the volumetric function that you get from MRIs and CAT scans and X-rays and things like that seem like not a surface-based approach. Yeah, but I'm not so familiar with work that's ongoing in that direction.
I suppose one interesting thing would also be how one can operate on this representation, right? Once it's represented as a network, what would be the operators that you can apply to this function to, for example, find where molecules attach to each other and things like that.
Right.
Then from Niloy, one question, in this hybrid view, how can we perform shape interpolation as there is not a single latent space?
That's a good question. So we did not do experiments in shape interpolation in either of the two projects I just described. Is that true? I think that's true. If the decomposition shares a common structure, then I think it's possible. So in the multi-resolution setting, there is a common structure to the decomposition. And so you could think about interpolating functions there. I think that because you've decomposed space or frequencies, you might actually end up with an interpolation, making it hard to interpolate across the boundaries of the decomposition. So like move one frequency into another in the interpolation in the multi-resolution case. Kyle Genova again is going to talk about this local deep implicit functions, and he's going to describe something where the decomposition is into mixtures of Gaussians, and that you can reason about correspondences between them. And so they're not like a fixed decomposition, but there is still a correspondence between different examples with a decomposition, which does make interpolation possible. So I think it's about having a consistent decomposition in a way that allows mixtures of the type you want in interpolation, if that makes any sense. So you don't like decompose things in a way that now you can't interpolate between them because you separated things that need to be interpolated.
Okay. So it depends determining what you want to interpolate before, and then putting these things into a common implicit function.
Something like that, yeah.
We have a bit more time for questions. So,
but just to follow up on that, on the we didn't do it, but in the multi-resolution, it seems that it would be possible to interpolate latent codes in the higher levels, the lower frequency levels, and get kind of cool effects where you've interpolated the global structure but kept the details, or vice versa. You interpolate the details, and so that would be interesting. We didn't do that, but it seems like that would be possible.
Yeah, I think one interesting thing is probably would every combinatorial possibility, or like every combination of these latent vectors produce something interesting or something good looking, or would there be some errors that you would get if you would interpolate some combinations of would use some combination of latent codes?
Yeah, so interpolation is a weird problem, a weird application for me. I think interpolation of latent spaces is incredibly informative with regards to, are you actually learning something, or you're just memorizing your data set, things like that. But there's very few interpolation tasks that interpolation of chairs in a shape space is a good example, where there are not multiple modes, arms versus no arms, and that everywhere in the shape space makes sense. Like halfway between having arms and not having arms is just a nonsensical place in the shape space. So I think the interpolation makes sense where it's unimodal, as faces, or I mean, maybe even faces isn't right, beard versus not beard, glasses versus not glasses, whatever. But I think that it's like a application that we do as researchers to show that our learned representations are sensible, but I don't know that it's really a reasonable application.
Maybe something more discrete is needed there.
Yeah.
That's good. I think we have time for one more question.
Just as a minor comment related to that, which is I think a lot of times we as researchers imagine that we're running like latent shape spaces where every point in that space is producing a reasonable result. And that's just generally not true for the data sets that we work with. So like you learn a latent space of chairs and then you optimize within that space. It's really easy to get results that are off the manifold. I mean, they're on the manifold, but are nonsensical. This was actually a problem in the latent implicit grids where we would train it. Our intention was to train it on ShapeNet models where you have, perfect cubes and perfect spheres and sharp creases and things like that, and then test it on real data, like sparse samplings of real scenes. And then ideally the decoder only produces things that look like they came from ShapeNet. And so you get, even though you started with a point cloud that is very, very, very coarse, you're still getting sharp creases and things like that. But the problem is that when you go between, things are either a sphere or they're a cube, and there's nothing that's in between, but the shape space still has those in betweens. And so we ended up getting blobbier structures than we wanted because the shape space had things that were interpolations of the things that were actually in the training data. There's these dead spaces between the reasonable places for them in your shape space that are mixtures of them. And so our optimizer for the latent codes was able to find those places to better fit the very coarse input data. Anyway, it's a little bit of a, yeah. Anyway, I think that we as researchers just imagine our latent spaces as all everywhere is good, but they're really, really not.
Yeah, I imagine there are some transitions that you can't avoid even if you make them very small in the latent space.
Right, exactly.
Right? Yeah.
Yeah, and the optimizer can find them. Yeah.
Yeah, maybe it would be good to learn a network that can identify where these transitions happen to actually.
Yeah, we had this project. We had this project a few years ago that was the goal was an interactive tool where the person could with like Minecraft basically produce an input shape and then hit a button and says make this real, and it would project it onto a latent space And then it would move within that latent space to a place that a discriminator thought was very likely, with an explicit representation that most places in the latent space were not good. And so then they could take that and then edit it further. Anyway, so that's an example of that.
Okay, thanks. I think we should move on to the next talk.
Right, thank you.
Songfang, do you want to take over?
Yeah. Hi, Hao. May you share your screen while I introduce? Okay, Professor Hao is Hao Sui is a professor at the Department of Computer Science and Engineering in UC San Diego, also affiliated with the Institute of Learning-Enabled Optimization at Scale Artificial Intelligence Group, Contextual Robotics Institute, and Center for Visual Computing in UC San Diego. His work of ShapeNet, PointNet series, and graph science have significantly impacted the emergence of and growth of the 3D deep learning. His talk today will be about compositional learning in 3D shapes. Hi, how you can take it.
How? I think you're muted.
Sorry, you hear me? Can you hear me?
Yeah, we can hear.
Okay. Yes, let me start. Okay, thank you very much for the introduction. I'm going to give a talk on the compositional learning of 3D shapes using paths. Okay. First of all, the motivating factor for us to study computer vision, especially deep learning for 3D data analysis, is because of the many success of machine learning, right? We know machine learning are very successful for all kinds of applications in pattern recognition field now. Somehow this is made possible by a lot of data, right? For image classification, you need a lot of images with labels. And for shapes, we also have similar kinds of ideas to have a lot of 3D models that are synthetic or real with labels. While we are able to actually get a stronger and stronger ability to analyze data, in fact, to do this kind of prediction tasks using neural networks, one of the issues is when we are using the traditional machine learning paradigm, we're assuming the training and tested data, they are from the same object categories, right? This is usually an assumption that we make. If there's no concept of object involved, still we're assuming that the tested data and the training data, they are subject to the same distribution. It's like the generalizability is talked under the assumption that the tested data has the same distribution as training data. But this is not always true when we're building machines to face the real world. The real world has combinatorial complexity. Okay, so like here, when the case are playing with the Legos, they try to use the Legos to build complex objects, sometimes even the fictional objects, right? So the task that they face to manipulate the object, right, to assemble an object, they're not the ones that they're trained on. Okay, what you learn may not be what you are tested. So how to conquer this kind of complexity, right? When you test the data, it's not the same distribution of the training data. A very natural idea is, in fact, compositional learning. Right? This is how our humans learn from baby, right? From becoming a baby, right? We are born and trained, in fact, grow maybe in the single house, right? Or even a small room. Somehow we are not facing a lot of real world problems. But in this just a small environment, we're able to learn to solve a small set of problems so that we learn the basic scales, right? It's kind of like the basic scales decompose and allow us to solve more and more complex scales. And this is somehow an idea of, and I think in my mind, is the only possible way to deal with the case when the tested data distribution is different from training data distribution. Okay, And we repeat this kind of process on as we're growing up, right? So like when we learn physics, in middle school, we learn the Newtonian physics, and they are only 3 simple rules, right? The simple rules explains a lot of things. So we learn those Newtonian rules from the classroom, and then as people grow up, they're able to use them to analyze much more difficult problems like civil engineering. So come to the 3D problems, it would be my curiosity to ask, what are the reusable skills or units? So one of the opinion that I have is like paths and the relationship of paths. They are the path, they are the element that reappear in all kinds of data. It's like in the training data and test data, maybe they are very different in terms of the global shape. However, if you decompose and to the level of paths and the relationships that are the shared ingredients. Like here, this is an example that I'm going to show you. We have certain applications that we will use chairs to train the algorithm, but when we test, we're on either for analysis tasks or for synthesis tasks, we will be on other object categories that are not chairs. Although they are different in terms of like the semantics, their geometry structure, when it comes to the more elementary level of paths and relationships, you see the similarity. So this kind of a level of similarity allows us to transfer. Okay. So in fact, the power of 3D path understanding, to my opinion, is extremely important. This kind of a transferability, although we're discussing for a fundamental question, it actually has very important real-world application implications. Okay, for example, it's useful for analysis, right? If we're building a robot, it might be in a different environment. Not only robot, like for human, if you're browsing the Amazon for new products, you don't know them, but you're able to actually already being able to segment them into pieces. And the pieces are the ones that you're familiar with. And the familiar paths, they actually carry certain functional information. So we're here using paths or path relationships to transfer the functional information of new objects. And probably for reconstruction is also important, right? Like the object may have weird shape in global, but when it comes to become paths and path relationships, the canonical space is getting smaller, and that regularize our objective of reconstructing from just, for example, a single image, which is an underdetermined case. And then the paths also allow us to do some low-level controlment when we're trying to synthesizing or editing shapes and images. So for today's talk, I'm going to give 3 work in my lab or applications that showcase the problems distilled from the 3 challenges of path understanding. The first one is the segmentation problem of unknown 3D point clouds. Okay. And of course here, because they are unknown objects, the segmentation may not be fully aligned with the ground truth. However, as long as we are able to see some functional, reasonable results, we think it's good. It serves as a proposal or part of discovery for downstream applications. And then the second is a reconstruction. Like if you have only a single image of an unknown object, are you able to reconstruct a 3D? There are certain ways that says predict the depth image and lift it to 3D, and this has certain generalizability, alternate distribution generalizability, I mean. But we are going to show that using paths is a completely different route and is able to achieve some of the fascinating results. And third one is the synthesis, like with controlment. Okay, so paths allow us to decompose and then control the appearance or the shape of each individual piece. Okay, and we will showcase by the portrait image synthesis example. Okay, so the first task to segment a 3D point cloud of unknown objects into parts. So first to review the classical setup, right? We have been working on 2D and 3D segmentation problems quite a lot, especially the recent years. We're seeing all kinds of neural network architectures and improvements to find the state-of-the-art object segmentation algorithm. But basically, almost all of them assume the training test data are from the same semantic category. As I mentioned, this limits the effectiveness of the algorithm when it faces open world. So for our task, we're more interested in the setup when the training and the test set, they are just objects from different semantic categories. We hope that more people will be interested in the problem. Okay. So if you are working in a classical 3D shape classification field, there are actually a number of good lessons that you will fully believe and immediately apply to a new challenge, right? For example, a very basic pipeline of classical approaches, like you will use certain local method like convolution or like in .NET++, the set abstraction to extract per point or per region features. And then you will build a very deep neural network to allow messages to pass and fully mix. And then there's a kind of a belief in the deep learning community that a deeper network is the one that gives you stronger performance. Okay, so you have many layers of convolution, and there are many works of this style, right? Back to the kind of earlier work on shape classification to the more latest. So one of the challenges, if you are in a setup of generalization to unseen object categories, in fact, such kind of standard practice may have certain issues that many people are not aware. For example, when you're building a very deep network, the global context is involved. But when you are involved in the global context, that is against the kind of philosophy that we would like to find the reusable local pieces, right? Because when the context is bigger, you see too much, that you're seeing things you are not familiar with. And networks are not so stable. Like we know there are adversarial examples, many kind of phenomena that will affect the performance. Right, of course, one way is you try attention, but then the attention network will have to take to look at the whole image, and then like the generalizability of attention network becomes a problem. Okay, so somehow we're interested in asking like whether there are other kind of possibilities other than the very deep convolutional neural networks. And here is some the result from our preliminary attempt, which is taking using an approach that is completely different from the fully convolutional segmentation network standard pipeline. Okay, so on the left, sorry, first of all, we only use chair to train. Oh, sorry, first of all, we use chair, storage, and the lamp, the three categories to train. And then for the test, they are on the bed and the faucet. Here, we want to emphasize that the train and test data, they are very different object categories. On the other hand, because we are using the ShapeNet chair, storage, furniture, lamp to train, these three categories, in terms of a part diversity, is very rich. So we see all kinds of parts. Even for beds and the faucet, for most of the cases, we recognize the parts and partial relationships, like a parallel relationship or orthogonal relationship. Okay, so using the approach that I'm going to introduce, we're able to outperform the baseline that is based upon the fully convolutional network much better. Okay. Okay, so this is, I'm not saying that this is like already a very good solution to the problem. On the other hand, it's more like a scientific study. It's like trying to be a kind of orthodox to try a different kind of route. Okay, so you can think that the traditional approach is more like a top-down approach. Okay, but we are trying to use a more bottom-up like approach. Especially, we will be very conservative in dealing with the receptive field. Okay, it's like or say try not to use anything in a context at all. If we are able to not use the context information, we just don't use it. This is point one. And the second point is, so here I would first confess that for the new pipeline we're introducing, it's quite a slow inference process. But I think this kind of a slowest is probably not that wrong. Because think about when we are seeing something very new with a novel shape like humans and seeing something very new, in our mind, we will have a complex inference procedure. We kind of will try to use a trial and error process, try to group different regions all together and see whether they make better sense than isolating them. So like when reasoning a structure of novel objects, we in our mind make a lot of search and hypothesis testing. So for this procedure is also a hypothesis testing kind of a procedure. And but so here we're just using a kind of a naive version, which is still a greedy approach. Now let me show you the approach. The approach where the hypothesis testing based approach is in fact a bottom-up framework that in structure, the algorithm structure, I mean, kind of align with agglomerative clustering. So here's just the pipeline. Now at the very beginning, we're using certain heuristic to generate superpixels from shapes. By superpixels, they are the region of homogeneous region, the homogeneous region. And then we have a policy module. Our policy tries to suggest to merge some of adjacent paths, okay, or adjacent superpixels. There are many possibilities, like for every pair of adjacent paths, it might be mergeable. But then we try to generate a score for all the pairs and then pick the one with the highest probability. We try to merge them. This is a hypothesis generation. And then we have another network that will do verification. Like we try to take the hypothetically merged version and then verify whether this seems to be a reasonable part. Like this is testing. So combine them together, this is really a hypothesis testing procedure. And you use a neural network to generate hypothesis and a neural network to test. Do this iteratively. If we think that the best pair can be merged, then we merge them and then remove the original subpaths from the pool and add the new pair to the pool. And then we repeat the procedure to suggest some pair to suggest, and try to predict until we reach a status that none of the next pairs are mergeable. We stop. So this is the procedure, and that is the procedure that gives you superior performance in the out of class generalizability test. And we see from here that first of all, the philosophy that deeper is better may not just apply for composition generalizability. Instead, we probably could think more like this kind of hypothesis testing procedure, which might give you slow inference speed because there are obviously a lot more complex algorithm in the reasoning. On the other hand, if you think that humans are also slow, when you're facing new cases, you probably feel more comfortable. Okay, that's the first work. Then the second work is using path priors to reconstruct the 3D of unknown objects from a single image. Okay, so just use a picture to show the setup. Like the training is the chairs, right? The chair data, and we are given a single image from a single view of a chair, and we know its 3D structure. Here, the 3D structure is represented as just a combination of cuboids. And in next project, we will describe like, okay, I mean, even if the primitive is simple, it's possible to actually, this is the perspective to make it with a lot of details. But let's stick to the one here, which is the 3D structure is represented by the combination of cuboids. Okay, but the training data are chairs. On the test data here, example is a bed. Okay. So how can we do this? Again, there are already a rich literature of work that allow you to predict the 3D out of single image using an end-to-end approach. And most of the existing research will study the representation, like surface representation or volumetric representation or like point cloud representation or implicit field representation, right? You hear all kinds of this kind of trials, and many gives you very fancy visual effects. On the other hand, I would argue that although they perform relatively well, few are, I mean, they just focus on the same tacker setup. Now, if you jump into the out of distribution setup, which is a very hard, difficult problem, probably the low level of 3D representation, like whether it's a point or surface or input function, they really do not matter that much. Okay, so we come back to the case, which is more like a semantic way of thinking about 3D representation, which is part. Okay, so as we mentioned, we think low order information, local information tends to be more transferable in general. And again, we're kind of against the idea of simply doing convolutional or up convolution network for compositional generalizability. Kind of, I'm not completely confident. But here we actually also conduct a number of scientific studies. Okay, the goal is to identify transferable modules that will well capture low order or local information, but with good transferability. Okay, the experiments are done on the PartNet dataset. The PartNet dataset has a lot of 3D objects with very fine-grained paths. Okay, as I mentioned, because we're working with novel object as the inference type, the 3D reconstructed structure may not exactly align with the ground truth. As long as the shape is globally, that's fine. We think it's good. Okay, so here, first of all, I'm going to show you a very much modularized pipeline. This is very much from a high level, this is the idea in a pre-deep learning time. Okay, so it's like we will first detect paths on 2D images and form masks and path mask, and then we will predict the orientation of each mask, and then we will predict the size of each mask, and then we'll predict their relative position of each mask, and then assemble them. Well, the majority of the efforts that we're spending is actually, we assume that we're taking this modularized pipeline. However, we ask, for the modules, there are so many ways to design them. Can we design them so that they get good transferability? Or to compare existing or some of the reasonable designs in terms of the cross-category transferability. Okay, so like the first question we ask is, we have decomposed the whole system into a number of sub-problems. So are these sub-problems transferable across categories? If they are, then composing them is probably a better idea than doing fully convolutional or up convolution. The answer is in general positive. Let me show you. The first submodule is the path segmentation module. Okay. Okay, so here the training objects again are chairs. Okay, but the test data, training data are not shown here, the chairs. But the test data include the table and the bed. And you see these are the input images, which actually are synthetic ones. The training data are also synthetic ones, all synthesized from shapenet data. And you see the ground truth part mask according to the PartNet annotation. And then the last column is the master RCN prediction. So basically, I'm saying that on a 2D part segmentation task, it seems like even the existing 2D approach like mass RCN seems to be a good job in terms of segmentation. But we also observe that it's not perfect. Okay, there are still like issues that could be fixed, but the result is actually a lot better than we thought at the beginning. Okay. But for some of the 3D tasks, I think the okay, sorry, I think I need to mention. Now, one reason for mass RCN to perform well, we actually think investigated and realized that is because like this kind of approach is in fact a two-phase approach, right? The mass RCN, in fact, first detect the bounding box and then use the bounding box to segregate the region that we're interested in out of the rest. And within the bounding box feature map, there's a second stage to do per pixel segmentation. So for the generalizability out of the categories of mass RCN is probably largely relevant to there's this kind of like isolation procedure. But without this isolation procedure, we also tested some naive fully convolutional networks. They won't generalize as well. Okay, and then the second module is the path rotation. The input is the image and the path mask, and we want to use a deep neural network to predict the orientation or the rotation of the path. So in fact, for this part, we find is quite a challenging problem, and we have discovered certain tricks to make it better. And I will just describe the tricks later. But at a high level, our idea is, okay, we will use the so-called axis set parameterization, which is a way of representing the equivalent cost of rotations. Okay. So in fact, even for the ground truth, we are assuming that input is a point cloud. So for the path, they are also point cloud, and we use PCA to find a bounding cuboid, not bounding cuboid, a canonical, sorry, a proxy cuboid for each part, Now here is a transferability. Of course, it's using the axis sets representation we propose. The trainingness chair and the test are like table, bed, and cabinet. And you actually would see that with the path mask to imply the region of the path of interest, and with the axis set parameterization, we are able to predict the paths of objects. Well, the paths as cuboids. Okay. Okay. So we actually have already predicted the orientation of the paths, and next is we want to predict the size. Based upon the axis set representation, which is actually just a representation of the cuboid in terms of the 3 axes of the PCA frame. Okay, we will predict for the 3 axes of the PCA frame, the length or the thickness of the cuboid along them. And this is the so-called size prediction. There are also certain tricks I'm not explaining here, just to show you the results, and I want to show you that. Yes, so you under the axis set representation, the size prediction is also exhibits good transferability. Okay, and then the last is we have the orientation and the size of the paths. We would like to predict how we are able to assemble the paths into an object. And here we actually use a contact point-based representation. Okay, so for adjacent paths, they have a contact point, and we are predicting the relative the relative position of each part to the contact point. And then we convert the relative position to the contact point to become the relative position of the two parts. Okay, in this way, we're able to assemble the parts with orientation and size together into a whole object. Okay, so again, the transferability test gives us positive results if we are using this kind of relative position prediction. If you're using the absolute position prediction, that's not giving us a good performance. Okay, so here, again, relative position test, like the transferability can pass. And here I want to show you two interesting examples. If you feel that we might like a fake, right, put some test data into the training because the ShapeNet data may not be so clean. Now there are two fabricated objects, two fake objects we created. The first is 5-angle star. The second is I don't know if it has a name, something like a door. Yeah. So using the part cuboid based approach, the model is still trained from chair. It's still trained from chair, but we're able to reconstruct the 3D structure for this object that the model never sees. Okay, so I'm just using a little bit of time to introduce the key technique for orientation prediction. Okay. Yeah, let me first be even more explicit about the axis set parameterization. Okay, so the common way of representing orientation is by rotation, right? But because our ground truth rotation is from a PCA, there are ambiguities. And in fact, is there's just no good way to get a canonical orientation. Okay, so and at the bottom, look at the two bottom figures. I'm showing that, in fact, even if you're able to get a more canonicalized way, or like a not the kind of, you're able to resolve ambiguity. Okay, it's still, and use the rotation matrix to represent orientation. It might still not be a good idea. Like here for the chair legs, the two legs are very similar orientations, in fact, but the PCA will flip the axis and gives you very different ground truth labels. If you give a neural network this kind of data, that will cause big trouble. So what we did is we treat the rotation, we use the rotation to rotate the frame at the origin, and then extract the 3 axes, and then treat the 3 axes as a set. That's why it's called the axis set. Okay, for the ground truth, it's a set. For the prediction, it's also like to convert the quaternion representation rotation to the set of axes. And then between the two sets, we will use the commonly used differentiable matching loss, right? It's a loss that many people are now using to compare sets. For example, you can use Earth-Moore distance or bipartite matching to build it. Okay, so but this is not solving the full problem, because the axis set is in fact just a reparameterization of rotations. In fact, it's the equivalent class of rotation matrices. However, it actually inherits some of the bad numerical properties of rotations. We do know that the rotation is not a diffeomorphism to the open set in Euclidean space, right? That means using a neural network to parameterize them, there'll be issues, right? So the story is pretty long, but if you're interested, you can read the papers I'm putting below. But basically, I'm saying that because of the topological difference of rotation groups, hence the axis sets, there will be severe local minima issues for network training. Okay. Now, one way we find very effective in overcoming the limitation is to use a mixture of an expert network. It's like for each input image and part, we predict some of the axis set candidates, and then also predict the likelihood to select this this axis set prediction and compares the ground truth. Okay, so that's the key for the success, or for success to build a strong rotation predictor. And here we see that a comparison with the baselines. If we are using the mixture aspert axis set representation as the top row, we're able to do the prediction well. But without those kind of careful tricks, we're not able to do it as well. Okay. Here's our some visual results for the single image to 3D part-based reconstruction. And the chair, which is not as interesting, is basically like the training and the test are same categories. You see a lot of approaches can do reasonably well. And genre is the one that first predict the depth and then lift the 3D. From the observed view, it looks good, but from other views, it's not looking so good. And then bad is actually a general out of distribution test category. And we see that using our design, a part-based approach, is able to predict the rough structure reasonably well. Now, as a baseline, if you think that okay, so using paths to do prediction, why don't you use graph neural networks, right? People may think graph neural networks are very natural ways to build graphs and do prediction. Now here's the approach. That's the naive graph-based neural network. It's not using the improved representations. We just hope neural network is able to learn some very powerful things with this very straightforward approach. Straightforward loss and straightforward design gives you good results, which is not the case. Naive GCN just will not generalize as expected. However, if you will modify the graph neural networks, which is here, the version is a NeurIPS 2020 version, with improved part level designs, the performance is improving drastically. So the lesson is, while end-to-end is a good thing, the most fancy ideas, when put them together, may not give you all the desired results you want to have. Okay, the last part, I think I don't have much time, so I just scratch the surface of the problem, which is the controllable synthesis of images with 3D paths. Okay, so this is actually an improvement over the generative adversarial network, the 2D GANs, right? We know that there are a lot of 2D GAN work, but why is that playing? Yeah, but the 2D GANs gives you images. But here, the example is, what if you want to generate images with like certain view consistency or part level control, spatial view? Yeah, if you want to get a view consistency, you need certain 3D representation. Now, if you want to get part control, then you need part information. So for this approach, we actually, although it's an image synthesis task, we actually have built a 3D representation. Now this 3D representation is projected to the image space. Okay, and if you are familiar about like NeurIPS or the cost volume approaches, you might have a guess of how we did it. So basically, we will have a 3D space that controls the geometry. In fact, it's the geometry of the paths. Yeah, we'll have a 3D space to control the geometry of the path. Let's find a good picture here. The geometry of the paths, and then that corresponds to a geometric code. And then we have the camera pose, which is another latent vector that we will specify to control the orientation. And then we also, like the 3D path structure are projected to the image plane. And then we somehow use a texture code to stylize the geometry. That's a high level idea. And here, see that the SOF is a 3D path-based representation of the face. And then this SOF is we use the rematching to project it to like the part masks onto the image. And then we stylize the part mask using some improved image-to-image translation technique, right? With GAN as the loss. So combining them together with the 3D centric representation, you actually are able to achieve the view consistent morphing as well as like a part-based geometry control. So this is a kind of a disentangled representation of a face to allow more controllable synthesis. Okay, so maybe let me just play some videos that people like to see. Yes. Maybe we geometric space. This probably. And this is actually just a video we just seen. Like we see the view consistent GAN results and allow us to actually also control the paths. Yeah, and more examples. And here the last video, and we will finish after this video. Okay, so maybe I can give us the conclusion of the whole presentation. Well, neural networks save us some efforts from feature and predictor design. If you want to achieve the desired out of distribution generalizability, composition generalizability is still important, especially when it comes to 3D geometry. Paths are important. So identifying the modules and their interface to connect is very important for the performance. So end-to-end should be like, in my view, we need to find the right form of modules for downstream tasks instead of like simply being interpreted as using gradient descent. Okay, that's it for my talk.
Thank you for the great talk. As we are a little bit tight for time, so 1 or 2 questions. You can type your questions in the chat window. Okay, a general question maybe. I know that Professor Hao have recently worked a lot on the robotics applications. So can you share your perspectives on the compositional learning in the robotics applications area?
Oh, thank you. I'll be quick to the question. I think that will, I mean, if it comes to robotics, then you actually give one more dimension of a compositionality. And here we're basically talking about the spatial compositionality, like the paths. And then when it comes to robotics, there's also the temporal compositionality, right? Because there will be like the basic skills to be composed and complete complex objects. And then the spatial and temporal compositionality, we actually will couple, because sometimes some of the skills are only relevant to some of the parts of the object. So yeah, if you want, I mean, when it comes to robotics, right, tasks is getting even more complicated. So if you really want to solve many tasks, then I think compositionality or yeah, spatial and temporal and their interactions it's just something that everyone will finally go along the route. Yeah.
Okay, thank you. Hi, Paul, do you want to take it?
Yeah, thank you. So the next speaker is going to be Kyle Genova. So Kyle is a research scientist at Google. He completed his PhD at the Department of Computer Science at Princeton University, advised by Tom von Kaus, who we had heard speaking earlier. He has published several well-received papers that combine implicit functions with structural representations, among some other works in shape understanding and shape priors. And he will talk today about local deep implicit functions. Kyle, please take it away.
Hi, so I had pre-recorded the talk so I would know it would come out well. So how should I share that?
Yeah, exactly. I think it's easiest if you share the screen with the talk and check the audio sharing option so that we can hear your audio as well from your desktop.
Hi everyone, welcome to this structural and compositional learning workshop talk. My name is Kyle Genova, and I'm going to be talking about local deep implicit functions, or LDIF for short. So the outline of the talk is the following. First, we're going to discuss the background necessary for LDIF, and that's going to involve a discussion of structured implicit functions. Then we're going to move on to LDIF, the key idea of that approach, the details of the LDIF representation, the inference pipeline we use to go from some other encoding or depth image to the representation, and then the results and key takeaways. Okay, so let's start with the background and structured implicit functions. So, what is the structured implicit function, or SIF for short? Well, as the name implies, it's an implicit surface function. So
Kyle, we can see the panel. Can you move it a bit to the side?
Of some continuous function.
We can see the panel on the right with the viewers. If you move it to the side, to the edge of the screen, then it doesn't cover the presentation. Yeah.
Apologize. Okay. Big F. So that means that, for values of f greater than L, those are like points inside the shape. Values of f less than L, outside the shape, and then right at L is where the surface is. Okay, and it is also a structured representation. So that is, you can decompose this function big F into a lot of little functions. And in particular, we're going to use Gaussian anisotropic axis-aligned radial basis functions with a leading constant. So this is a Gaussian, which is always positive, so that it just adds influence to space with the smooth radial basis function decay. And then we have a constant C sub I that is learned that is going to allow you to smoothly turn on and off shape elements, and actually C sub I is made negative to get the inside-outside property to be consistent. And then that essentially gives you the ability to analytically represent a surface with this set of parameters to each of the small f functions. So why would you represent shapes in this way? I think that this table really makes the case, which is that this is a way of representing shapes that has nice properties. So, on top of things like it's concise and human interpretable, two important properties are that it can continuously change topology, so it's smoothly adding and removing holes from shapes, and it is deformable. So as you move the basis functions around, you can smoothly change the shape. Okay, so the way that a SIF is derived from an input shape is that a network, CNN, is fit over a shape collection, and this network takes in an input shape encoded as images and directly regresses the analytic template parameters, which defines a shape and a shape reconstruction. So that reconstruction is evaluated as a loss function and is the primary training signal for the structured implicit function. That is, there's no supervision on structure or consistency or anything like that. There's just supervision on reconstruction. But when you fit an entire shape collection at once, due to the shared network parameters, which would like to smoothly change the analytic parameters across the data set, you actually end up with structural consistency. So the left leg of the chair is always represented by the same element. The elements are colored based on their order in the final fully connected layer. Okay, so this visualization really, I think, highlights this key property, which is the whole benefit of SIF. So we've got ShapeNet in the entire ShapeNet 13 embedded into on the left there, and then we've got the parameters as we move around the ShapeNet space, and then the ISO surface. And you'll notice that while it is true that in between shape classes, the parameters, the shape, there's no real correspondence. Within a class, you get nice, smooth correspondences, and the classes themselves are sort of learned. There's no supervision on that. They just happen to group into classes because that's the right way to organize the data for the MLP, and so you're able to smoothly understand the correspondences between the wing tips and the wheels of the car, and so on. Okay, so then this is the key property, but you can use it for interesting things like coarse 3D surface correspondence, in particular correspondence where you're able to detect whether or not there is a correspondence for a particular point on another shape. Here we've got a consistent threshold on multiple shapes, and you can see that it correctly identifies that the source shape doesn't have a dish or a rear engines or fourth engine, third and fourth engines. Okay. The other piece of background for LDIF is deep implicit functions or coordinate networks, which you're probably likely familiar with. So those take in some 3D location, XYZ in space, optionally some shape features, and then output a relationship between that point and the shape. So in particular, we're going to talk about occupancy networks because our approach builds directly off of that, where it classifies each point as inside or outside the shape and takes in a shape feature vector. Okay, so OCNET has been shown to be very useful for single view 3D reconstruction with a learned shape prior, and it's better able to reconstruct the details of the shape than previous approaches. So the key idea of LDIF, which is now we're sort of ready to discuss, is to represent shapes as a global template and local latent codes. That is, you can think of it as a set of latent codes that are localized in space. The latent codes that have a position and an extent in space. And this is similar to structured implicit functions because the shape space is defined by this global template, but distinct because now we're going to attach latent feature vectors to each shape element. And it's similar to occupancy networks, except that we are going to add structure rather than having a global latent code. Okay. So to be a little more specific, the LDIF representation is a sum of local analytic functions G, which are modulated by a learned residual F. So G is going to be a Gaussian radial basis function as before, although we're going to relax the axis aligned restriction, and so now it's just going to be a general affine transformation per shape element, and then F is going to be a fully connected network with a similar structure to OCNET, except that it has far fewer parameters. Okay, and then to derive an LDIF from an input, our pipeline takes in one or more depth images. So if you have a known shape, we render a dodecahedron of depth images, which would look like this, or we'll take in a single depth image for some experiments. Then these depth images are passed to a template extractor, which is a CNN similar to SIF, that regresses the analytic parameters with a fully connected layer at the end. And then that gives us the structure, and then we would like to attach a local shape vector to each shape element. And the way we're going to do that is we're going to turn our depth image into point samples with estimated normals. This requires assuming the camera extrinsics and intrinsics. And so for each shape element, we're going to transform the point cloud into the coordinate frame defined by the element's parameters, and crop it to the local region. And we do this in turn for each element. If you concatenate the analytic parameters with the deep feature vectors, that is the LDIF representation. But if you would like to evaluate it at some query location, then what you'll do is for each of the coordinate frames, you will evaluate the analytic template influence and then a local decoder network, which is shared across all of the shape elements, but is evaluated in the local frame and modulates the analytic